workshop, CNI workshop on codes, sequences, and information theory. It's a broad range of topics which Vijay has worked on over the years, and this is like workshop celebrating his 70th birthday this year. We started thinking about this workshop like 2 months ago, maybe like end of August. And thanks to CNI for the support. Thanks to my colleagues from various places. One for help with organizing the workshop. The second for all of you to come here. And I'm really grateful to all of you for accepting our invitation and agreeing to give talks here. So it looks like, I mean, as you can see, the program is extremely packed. We wanted to kind of end at by afternoon tomorrow, and that is the reason it is so packed. So we will stick to time, dot time. Okay. So with that introduction, I would like to invite Gautam, who is going to be the session chair for the first session before tea break for the next three talks.
Good morning, everyone. Let's start the first session. So for the online participants, please feel free to post your queries in Zoom chat. So our first speaker is Vijay Kumar. So he is a distinguished professor at ICTS Bengaluru. He is going to speak on information theoretic lower bound for quantum search.
Good morning. I'm grateful to the organizers for the opportunity to speak at this occasion. I join you all in wishing Professor Vijay Kumar. I mean, he's been an inspiration to many of us. I used to work at the Tata Institute of Fundamental Research in Mumbai before, and we have relied on his opinion and advice on several occasions while building that department there. So I'm grateful and very happy to be able to speak to you today. So yeah, my talk is about quantum search. I don't know if this works. Yeah, so does this work, or I need to click on this? Oh, okay, yeah, yeah, good. Yeah. So there will be hardly any quantum in the talk, except at the very end. But I'll try to explain everything. So this is joint work with Rohit Sharma Sharkar, who was a postdoc at IISc, but now he is in Barcelona. Okay. Yeah. So this is probably the first problem that one tries to impress people with in quantum computing, and this is about searching a database. So a database for us is just an array like this, and it has only zeros and ones, and you are presented this database and you're asked, does this have a 1 somewhere? Okay. Or where is the 1 in this database? Okay, so these are the sort of questions, and it turns out that quantum can do this better than classical. Okay, but there is a slight twist in what I'm going to say. So let me just go over what we know about this problem. So the goal is our algorithm is going to probe a location, it's going to find out the value, and then decide to probe another location, and so on. And how many probes into this database do we need before we can say whether there is a 1 after all in this database, or locate the 1 in the database? Okay. So just to understand what it means to probe this database. So any algorithm on a computer, if it is unwound and we try to see what happens in the first clock cycle, second clock cycle, and so on. So initially, the algorithm does some computation of its own, arranges its memory in some way, and then on its strategy makes a probe to the database. Okay. Now I have written Fj here. What I mean by that is the database which has a 1 in the jth location. If I write F0, it means it has no 1s at all. Okay, so there is F1, F2, Fn. F0 means there is no 1 at all. Yeah. So anyway, so it makes a query to the database, it gets an answer, it thinks about it for some more time, then queries the database again, and in the end, after a certain number of queries, it says it feels confident to give an answer, and it gives the answer. And the number of queries we make is what we care. Yeah, so we want to minimize the number of queries to answer this question. And I mean, you probably can immediately imagine that if you don't want to make any errors and you want to do things deterministically, then you have to probe all the locations, because everything you saw was a 0. Can you really say that everything is 0? Maybe the last location is 1. Yeah, so yeah. But if you are allowed a probability of error, I'm of course wrong here, it should have been 1 minus epsilon here. So yeah, so you could pick some 1 minus epsilon n locations at random, probe them, and if you don't find a 1 among them, you just say that, oh, there is no 1. And you'll make a small probability of error depending on the epsilon. Yeah, so it should have been 1 minus epsilon. So this is how classical, this is what we know about classical, and we can also prove that these things are optimal roughly along the lines I mentioned. Okay. Sorry, this meeting is being recorded. Okay, I know. Okay, thanks. Yeah, got it. No, oh, you can do it yourself. Okay, okay, yeah, yeah. All right. So now this is where the charm of quantum lies, or one of the charms of quantum. That is, in quantum circuits, everything looks the same, except what you have here are, okay, what travels on the wires is not a probability distribution over states, but a superposition over states, whatever that means. And then at each step, we perform a unitary transformation instead of a stochastic transformation. And then we probe the database in superposition. The states of our registers or the memory changes. Then we perform some more unitary operations, a probe, unitary operation, a probe, and in the end we want the answer. Now, sorry, yeah, probably everybody knows this, but I'm just insulting you as if you don't. So Grover's, so we know that if you want to search a database of size n, you can do it using just square root n probes. So you don't need a linear number of probes. If you do quantum, you can get away with square root n probes. And this square root n is optimal. Okay, so you cannot do fewer than square root n probes. Okay, so this is where it was, and this is now, what, 30 years old. Yeah. So what is new? Suppose I tell you, so we don't have quantum computers, and we believe that the biggest obstacle is to keeping the superposition alive for very long. So suppose we have this model where we are told, so D is a fixed number, and after every D uses of the database, all your registers will be measured and they will become deterministic. That means you can somehow keep the superposition alive only for D steps. And after that, somebody will come and measure all the registers. Or you get to measure all the registers, and then you can start all over again. Okay. The question is, can we still get this sort of an advantage out of a quantum circuit? For example, you're allowed to start with a superposition, make a query, and you have to immediately measure. Yeah. Can you still get square root n? I mean, one would think that, if you're just going to make one query and immediately measure it, all right, how much advantage do we have? Okay. So this is the sort of situation that I'm concerned with. And so let me just define. Yeah, so I'm thinking of a quantum circuit which consists of little blocks like this. Each of these blocks has this property, so that after every D probes, into the database, a measurement is performed. So at each of these checkpoints, what you have is a random variable distributed over the possible states. Okay, there is some intermediate quantum intervention. Quantum does something, and then you measure. You again get a distribution. You feed it to a quantum circuit. It kind of lives its quantum life for d steps. Measure it again, and presumably d is very small because perhaps our technology is not so good that we can sustain quantum superpositions for long times. Okay, so that is the motivation. So the question is, if we are restricted in this fashion, that is, after every d steps you are forced to measure, then how well can you search the database? Okay, and the answer I want to present today is that the answer is n over d. Yeah. So which means, in particular for that special case that I mentioned, that is after every quantum query, if you are forced to measure, then you will need linear number of queries. So you don't get any quantum advantage if you cannot your superposition for long. So to confirm this answer, we need to prove two things. One is show that n over d is possible, and then show that nothing better than n over d is possible. Okay, so these are the two things. Yeah. So the upper bound is more or less standard and obvious. So what you do is you divide, so the set of locations, there are n locations. So you divide them into groups of size d squared, yeah, and dedicate one circuit to search only those d squared locations. Now, when you want to search a location database of size d squared, Grover search would do it in square root of d squared, that is with only d probes. Okay. Then you move on to the next block, and again you do Grover search on those d squared things, and you have enough resources because you can sustain superposition for d steps. Okay. So you search each of them either in parallel or sequentially, and in the end you will know. If there was a 1 in any of these blocks, you would have detected it and everything would be fine. And how many total number of probes did you make? Well, per block, you did these many probes, and then there were n over d squared blocks, and that comes out to be n over d. Okay. So, all right. So n over d can be done. It's basically riding on Grover search by making the domain smaller so that Grover search can be implemented even in our shallow quantum circuit model. Okay. So yeah, the next step is lower bounds. So yeah, how do we prove the lower bound? So I'll now have to slightly remind you of how the lower bound question. Yes, so maybe that's right. N over D stages are used in the following sense, that there is this block 1 which is dedicated to addresses 1 to D squared. Yeah. And then there is a block 2, there is a circuit which is dedicated to D squared plus 1 to 2D squared maybe. Yeah. Yes. Or, sorry, a classical algorithm? Order of n total, yeah. So, yeah, we are making good use of the limited quantum resources that we are being provided. If you just say that I'm taking away quantum completely, do it only using quantum, only using classical, you will need n. Yeah. you will not get any advantage out of this D. Yeah. Thank you. Yeah, yeah. Please keep asking. Yeah. Sorry. Yeah. So how did the lower bound work? Or so actually it turns out that the lower bound was proved before the upper bound in the 1990s. But anyway, the idea was that we keep the algorithm guessing. Yeah. So there are these D+1 possible databases. What do I mean by that? There is a database which has no ones at all. There is a database which has one only in the first location. There is a database which has one only in this end, in location n. Now we have somebody has a quantum circuit. Yes, yes, please, please. The algorithm is required to be correct on all possible databases, but we will show that differentiating in all of them from the empty database already requires square root n. Yeah, the problem is much harder. I agree, there are maybe 2 to the power n databases. Yeah, but we are only going to be talking about these n+1, and you have a quantum circuit here which has lots of gates, but it uses databases, query to the database at some crucial places. Okay. Now all these databases can be instantiated to F0, or all these databases can be instantiated to F1 or Fn. And then the initial starting state, let's say, is all zeros. Then some sort of a distribution or a state will arise at the end. Okay. And that state has a name, that is psi j. Psi j, when the database is instantiated to Fj, what is the output state produced here? That is called psi j. Okay, good. So, and then one shows something like this. That I'll try to explain this. The database, an upper bound here means the circuit is not able to tell the difference between this state and this state. It is in the L2 norm squared, is bounded by this. So if you pick a random database and feed it to the circuit, if the circuit is making only D queries, then typically your states will be pretty close to the state where there is no one in the database. That is, the circuit is not able to tell the difference between this state and this state. Okay. On average, yeah, you might have be able to catch F1, tell the difference between F1 and F0, but all the location. Okay, that is the spirit. Yes, please. Yes, that's right. Psi j can have any number of qubits. So let me explain. Yeah, no, a quantum, the database is a chip, yeah, to which if you feed an address, it tells you whether that location has a 1 or not. Okay. Now it has to be done in a reversible way. Those are technical details, doesn't matter. Okay. Now you have a huge workspace, any number of qubits. You perform a unitary and design the superposition that you wish to feed into the database chip, and it is entangled with the other memory that you have, and you move on. Okay. And now at this point, you apply another unitary. It rearranges the memory based on your strategy, and then it probes again. And this goes on for t steps. At the end, you are supposed to produce the answer. Our query is a superposition on the wires that feed into this database. Yeah. So you could suppose this was a randomized computation. Yeah. So you said, oh, I'm going to read uniformly in the first 7 locations, but I will also remember which location I'm feeding. Yeah. So you might keep some information in your workspace. You fed the address to this chip, it gave you 0 or 1. Okay. And then now you said, oh, I haven't found it in among the first 7 locations. Let me adjust my guess for the next location. That is done by this unitary. In classical computing, it would have been done by a stochastic operation, which takes the past data and produces the new question. Log n. There, because an ad, no, this is just the address. Suppose you have a database with n locations, so the address is only log n. Yeah, that's right. Yeah. No, output is superposition again. No, so suppose you fed 1 over square root n a equals 1 to n, let's say. Yeah. So this means I'm doing uniformly, I'm feeding everything. And there is a place where the answer is supposed to be recorded, it is 0. Okay. Yeah. So here is a chip which takes an address and a place where the answer is supposed to come out. This is where the address is, and the answer right now I've initialized to 0. Okay. What does FJ do to it? FJ looks at the address, let's say, leaves it as it is, and in this it puts FJA. For example, in classical computing, you had an address X, you fed it to the chip. What will be the new state? The new state will be a uniform distribution on all addresses, but the address will get tagged with the value of the database at that address. So the address has got tagged with the value at that. Okay. And now you can do nasty things to this and again feed something. Yeah. And so on. Okay. Yeah. Don't worry, I'll finish on time. Yeah. So, all right. So, yeah, so this is how, so if your algorithm is such that it gives the answer in the end, then it must be that the states produced when the database is FJ and the state that is produced when the database is 0 must be well separated. But this says that if you don't make enough queries, then it cannot be well separated. And you match these against each other, and it will tell you that you need square root n. Okay, so that's the spirit of this. Yeah. Now, what are we supposed to do? Yeah. Now, we are not in that situation where it is one big quantum circuit. After every d times, we are doing a measurement, and what we get is the sequence of random variables distributed over the states of all your registers. Okay. Now you have a j on top. That means that is when the database is fj. If the database was f1, I will write 1 here. If the database is f2, I will write 2 here, 0, then I'll write 0 here. So this is what is the classical information that the algorithm obtains at the end. And what we would like is that when the database is f0 and when the database is f1, these states should be well separated because they need to be told apart. Okay. The spirit is still the same. Yeah. So the idea is we have to bound the progress made in separating states after each block and show that the progress is small, but we need to make a large progress towards the end. So we will need a lot of blocks. Okay. So what we know is that any one block given any state cannot do too much. This is already there in the old proof. Yeah. But now, after every block, there is going to be a measurement and we are going to get all these random variables. So it turns out that the fact that two quantum states are close also implies that any probability distribution you obtain from them by measurement will also be close. But the problem is, what does close mean? Okay, and one thing is, based on what we do, total variational distance. I mean, we have been taught that when you are dealing with random variables and you want to do, say, determine how well a process can separate two hypotheses, L1 distance is the right thing, or the total variational distance. So if we can show that from the L2 inequality, if we could somehow conclude something like this, yeah, so some function of d will show up, then since the progress per block is only epsilon d, the number of blocks you will need to create a total constant progress is 1 over epsilon d, but each block already consists of d queries, and you would get a lower bound like this. And to get the desired lower bound, you will see we want a lower bound of n over d. So if we could prove such an inequality with epsilon d as d squared over n, we will be in business. Okay. Now the trouble is this is false. Okay. So trying to analyze this using L1 doesn't work. And yeah. So then what do we do? Well, yeah. Okay. Yeah. Now, I mean, sure. Okay. Yeah. No, there is. I mean, L1 would have worked very elegantly if it worked. For example, it works in classical when all the queries were classical. So anyway, I try KL. The thing is, it also doesn't work. Okay. Yeah. But it works better. Yeah. So okay. Yeah. So from the inequality with L2 squared, you can, let us say now we are able to get a bound like delta d, and you get 1 over delta d times d. And the trouble is, KL, as you know, I mean, can go out of control if, yeah. So it turns out that there are situations where if you try to use KL without, any perturbations, then things are unbounded and you get nothing out of it. With a little bit of work, you can salvage something. So it's almost n over d, but we are getting a worse lower bound because we have a log factor here. But the good thing about KL is that there is the chain rule, yeah, which works beautifully, yeah. So what actually works in the end is Hellinger distance, okay, and so yeah. So this is the Hellinger distance. Everything is classical. The Hellinger distance between two random variables. So it's actually the distance between their distributions. And it turns out that the inequality about L2 squared actually gives this for Hellinger square. Again, we are trying to separate the database which has 1, 1 against versus the database which has no ones at all. And then there is a chain rule. And this, I believe, is not that commonly known. So there is a chain rule for Hellinger distance, yeah? And if you apply it right, you do get a lower bound. Now this, I want to advertise this chain rule for Hellinger distance. So this is due to Jairam Tatachar, and it was proved around 2009 for communication complexity area. So it is something like the chain rule for KL, except it is only an upper bound. In KL, it is actually an equality. Yeah, you just, the chain rule just is an equality. Here, it is an upper bound. There is a factor of 4, but don't take any of the constants, I say, seriously. And it has a very beautiful proof. So I would like you all to take a look at Jairam's paper, and there is there are other lecture notes by others which describe this. Yeah. So yeah, so that's all I wanted to say. So let me summarize. So I'm trying to study a quantum problem which is not fully quantum, but only quantum to d steps. Okay, it can hold its breath only for d queries. After that, it becomes classical again. Now, the result that I show is that for a database of size n, we get a lower bound and an upper bound which looks like n over d, which is optimal. This is not new. In 2023, more general results using other methods were shown, not based on Hellinger distance. It's a big framework called the quantum adversary method. Okay, and so using that, colleagues in IISc showed this lower bound. And yeah, so our upper bound was based on Grover's algorithm, and the optimal lower bound used Jairam's chain rule for Hellinger distance. And yeah, so I want to stop here. So best wishes to Professor Vijay Kumar, and maybe I should say it more formally. Yeah, so this pi I should define. Pi is a projection onto a subspace spanned by happy states. And I expect, hoping that the projection of Professor Vijay Kumar onto these happy states happens with probability 1. Okay. Thank you. Thank you.
Maybe we can take one quick question.
Questions? Yes. Yeah. Yeah. Thank you. Yeah. 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 So what really happened? Yeah. So after you make, let's say that we made one query and measure. Okay. So after one query, this is the state psi 0, and this is the state, let's say psi 1. And their angle is something like 1 over square root n. Yeah. So now that's why, yeah. So L2 squared is like 1 over n. Yeah. Now, if you just measured it in the standard basis, in this case, you get a distribution which looks like 1, 0. And in the other case, you get a distribution which looks like 1 minus epsilon, or 1 over 1 over 1 minus 1 over n, comma 1 over n. Okay. So this looks very classical. You have a coin which is always heads, and another coin which is heads with this. How many times do you need to toss this coin? Well, you need to toss this coin n times to tell the difference between this and this. Okay, because this. On the other hand, it turns out that even though the angle is 1 over square root n, there is another measurement that you can perform. Okay, and in that case, you get a coin which is half plus 1 over square root n, half minus 1 over square root n, let's say, and half. Yeah. Now here, if you look at the total variational distance is 1 over square root n. So it is not working out very well. Yeah. But in this case, if you look at the Hellinger distance, it is still coming out to be 1 over n, or the fidelity between these two distributions, it's coming out to be. So it looks like fidelity is the right measure, but you can say that, well, KL divergence would also have done in this case. Turns out that because of this 0 here, KL divergence goes out of control. You can do some perturbation things, but it turns out that a measure which will work for this as well as this is fidelity or Hellinger distance, and that's why it works. So anything that can deal with this and this on equal footing, any measure, any inequality is worth trying out. Okay. So I should give the mic to the next speaker.
So our next speaker is Satya Lokam. He is a principal researcher at Microsoft Research Bengaluru. The title of the talk is Celebrating Professor Vijay Kumar. Subtitle is Model Protection and Inference Integrity.
So should I advance slides here, or is there a pointer? Oh, this one. Okay, thank you. All right. So let me start by thanking Professor Vijay Kumar for several useful, very productive interactions over many years. And although we haven't really written papers together, I've worked with several of your outstanding students, and my students benefited from talking to you many times. So thank you for all your contributions to the many fields, and thank you for your mentorship over the years to outstanding students and collaborations. All right, so today I'm going to talk about delegating inference computation in machine learning models. So from a trusted entity, whom we call Charlie. In cryptography, we always give human names to machines. Charlie is a trusted party who wants to basically run inference on an untrusted party, who we call David. So for instance, Charlie could be a cloud service provider, protected cloud service provider hosting a model, and David could be an edge device where the cloud wants to use the edge device for computing the inference. Or Charlie could be a trusted execution environment on your device, like your laptop, and David could be an accelerator on your laptop, which is sometimes, actually more often than not, untrusted. Okay. Now, of course, the challenge with offloading the entire model down to David is that Charlie could have invested a lot of money in building this model. It could have precious intellectual property, and that could be stolen. So that's the first concern. But even if you're not worried about David stealing, or some attacker attacking David stealing the model weights, David could actually tamper with the computation of the inference and produce incorrect or malicious results, and thereby the model and the model provider actually gets bad name. Okay? So these are the challenges that we want to address, while enabling Charlie to take advantage of David to do bulk of the computation. Okay? That's the problem. Now, before we talk about model protection, by the way, actually, sorry, even though the title actually says model protection and inference integrity, I'm only going to talk about model protection for today. But before we talk about model protection, let's ask this question: how much of a machine learning model do we really need to protect? Is every bit of a machine learning model as precious as every other bit, right? But ML intuition tells us that for almost all the models that we see in real life, the essential content, the information theoretic content of a model is much, much smaller than the size, the number of parameters would indicate. And there's a lot of empirical evidence to this. And we want to operationalize this intuition that if you want to protect intellectual property of the model, you don't really have to protect everything in the model. Okay? And we decompose the model into two parts. One we call theta c, which we'll give to Charlie. And this is a very small but information theoretically dense part of the model. And then there is a big but information sparse component called theta d, and that we give to David. Okay, that's the setting that we're going to work on. To give intuition, let's just look at linear layers of pretty much any model and consider the singular value decomposition. And it turns out that the singular values really fall off extremely rapidly. So the bulk of the information of linear layers is really contained in maybe even like the top 1 to 2% of the singular components. And so just for linear layers, it's actually easy to show that you can capture almost all of it information by just extracting the top few singular components, and therefore a very small rank matrix out of the weight matrix. Okay, so this is sort of the first idea. So I'll go here, and I mean you can experimentally validate this by analyzing singular value decompositions of lots of models, which we did, and you can also actually analyze different parts. For example, here we look at one of the large language model. Actually, it's not a large language; it's a language model, small language model. And the decoder blocks of these language models actually have very widely varying sensitivities to the performance of the model. So the middle layers actually are almost useless. Okay, so based on these sorts of experimental evidence, we formulate this hypothesis called safe decomposition hypothesis. What this is saying is a model inversion adversary. A model inversion adversary is someone who has black box access to the model. They can give inputs to the model, observe the outputs, and then they're trying to recover a model that is a good approximation to the original model. Such a model inversion adversary, if given in addition to the black box access to the model, also this theta d, so which in our case, in this case, for example, the remaining, the tailing components of the singular composition, does not have a significantly better probability of getting a good enough approximation to the original model if we didn't have theta d. Okay? So in other words, giving him theta d, giving this adversary theta d did not help much, and therefore theta d is not giving too much of additional information to such an adversary, and that is why theta d is essentially useless. That's kind of a formulation, and this is an assumption or a hypothesis we are making about all models. Of course, this is not a mathematically proven fact. This is something that we observe empirically and create this hypothesis. And once you have this hypothesis, then how you want to do offload inference is fairly obvious, and we call this split model inference. Like I said before, you give the dense but information theoretically dense but computationally minimal piece of the model or part of the decomposition to Charlie, and the rest to David, the other part to David. And then, of course, they have to talk to each other in order to compute the inference, because it has to be done on the entire model. And that's where we run a secure cryptography protocol. And that protocol guarantees that information about Charlie's part does not leak to David. That's important, right? And of course, mathematically, the output of the model, output of the protocol is identical to the output of the model, right? So that's the basic setup. And we also have this algorithm or cryptography protocol, and it's again, this is just a pictorial explanation for what's going to come next. So Charlie, and I'm actually illustrating this for a multi-layer perceptron, which is just linear layers followed by nonlinear layers followed by linear layers, etc. Okay, which is the easiest to describe, but this can be applied to other models as well. Okay. So, so trivially, the input coming to the linear layer, you compute on Charlie's part of the model. This is just a simple linear transformation, but it's important that it's a low-rank linear transformation, and therefore this can be computed really efficiently. Okay, and the other part, David computes, but we need to encrypt the input to it. And you see why we need to encrypt the input? And the reason is that suppose we didn't encrypt, okay, and now look at the previous layer. If you look at the previous layer, and if you didn't encrypt its input, and this output is visible, then basically, by simple manipulation and some luck, because there's a nonlinear layer, and we don't know what to do with nonlinear layers, but many nonlinear layers are actually invertible. Okay, therefore, David could basically, if this encryption didn't exist, David could basically, reverse engineer the output of this module, matrix multiplication. And it's a very low rank matrix, so there's a very small number of variables here. Okay, so the David, by observing multiple inputs and outputs to this module, because he could recover those, David could basically recover or basically invert, right? The inversion, David is the inversion adversary here. You could get WC, and all bits are, yeah. In the protocol, yes, but I'm saying why we need the encryption, right? The need for encryption from this diagram is not clear, but only if you look at what happens in the previous diagram, right? It becomes a previous layer becomes clear. Yeah. Yeah. Sorry, there's no model is given to you trained. It's inference. We are focusing only on inference. Yeah. right? Before you do the inference, that's the framework we are talking about. So the first step is to do this decomposition and then give the two parts to Charlie and David. Yeah. Okay. And luckily for us, and in fact, this is the only thing we can do today, is efficiently anyway, to do a linear homomorphic encryption on the input. Okay, and because this is a linear transformation, when you multiply, the linear homomorphic encryption of Q, which is Q hat, with the matrix, what you get actually is again encryption of WD times Q. So that property is all we are using here, and then you decrypt to get WD times Q, and you're done. Okay, so but this is simple enough, and this is actually the idea that we would like to pursue, if possible, to a larger extent, rather than just restricting to linear layers. So imagine if you could do not just linear homomorphic encryption, but fully homomorphic encryption, which we know theoretically how to do today, right? Then, any decomposition that splits the model, any safe decomposition that splits the model, can actually be put into this template, right? Where instead of using linear homomorphic encryption that we did here you have like potentially an arbitrary machine learning model, including nonlinear layers, but a small model, because we are decomposing the smaller than the big model, but still bigger than what Charlie has, right? But bulk of the model is actually living on David, and if you could do fully homomorphic encryption efficiently, then you could take any decomposition and put it into this template and you're done, right? So theoretically we have a solution as soon as you have a safe model decomposition to offload inference. But of course, fully homomorphic encryption is extremely inefficient today. Yeah. Right. Right, yeah. So again, only because of the cost and only because of the protection, right? So the fully homomorphic encryption requires the circuit to be available to David in plain text. Only the input is encrypted, right? So David needs the model to be available in plain text in order to do the computation. But of course, he's blind to the input and all the intermediate values, but not to the function. Right? And we are trying to protect the function here. So there are other kinds of cryptography you can do, functional encryption, which is even harder than fully homomorphic encryption. But in any case, the point I'm trying to make here is if you can improve cryptography to the point where you can run efficient homomorphic encryption on nonlinear layers of machine learning models, that's a very simple problem to state, but it's been very difficult to solve efficiently, in the sense that the overhead that you incur in order to do encrypted computation on linear layer learning models, it's hundreds of times more, if not thousands of times more, than plain text computation. And this is just a deal breaker for any kind of real world computation that we do today. Okay. So the simplicity of the solution is to kind of point out the humongous gap between the simple solution and what we really want, and that gap is, closing that gap is really an interesting challenge at the intersection of crypto and machine. Yes, yeah. I mean, I can actually make it even simpler. Anytime you have inequalities, ReLU is basically just an inequality, right? Anytime you have inequalities, cryptography seems to really fall face down. And there are actually theoretical results that say if you can solve inequalities homomorphically, then you're actually halfway there, if not more. Okay, so that's the challenge. Okay, all right. So, well, I mean, we have a simple enough solution. In fact, this is really practical. I mean, I can vouch for the practicality of it. Uh, but there are, so first of all, you can actually offload more than 95% of the computation to David for almost all real world models. And you still essentially, at a very heuristic level, protect most of the IP, right? But of course, it is heuristic. And it's based on ML intuition. We don't have sufficient mathematical justification to this hypothesis, safety composition hypothesis that I said. And again, as somebody pointed out, the model needs to be, pre-processed before we can do this. The model needs to be analyzed, and every model will have a different type of decomposition. So we actually have to build a decomposition tool before we can run the inference on the models. It's possible, again, heuristically it is possible, and what you do or how well you protect your model really is very, very sensitive to how well you're able to do this analysis and do the decomposition, okay? So we want to solve this problem with a little more rigorous approach, not particularly well established, but still, yeah. And the key for that is actually this problem. Again, sort of a homomorphic encryption type of a problem, but much simpler and restricted to just matrix vector products, okay? So the problem is that the encrypted matrix vector product problem is that Charlie has a matrix M and a vector X, and he just wants to compute that M times X, but he doesn't want to do it. He's too lazy to do this simple computation. He wants to use David to do that, okay? So what he would do is he would encrypt both the matrix and the vector, unlike just the vector in our previous scenario, but keeps a secret key or a trapdoor, tau, with him. And then David just multiplies the encrypted matrix with the encrypted vector and sends the product back to Charlie. And using his secret key, Charlie recovers the original, the product of the original matrix and the original vector. Okay, so that's the problem. And obviously, you want to do this both securely, in the sense that David should not learn anything about X or M, and still be able to help computation. And Charlie should be able to recover this faster than he could do matrix times vector. Those are the challenges, okay? So there's a fairly new cryptography primitive. I mean, of course, the definition is natural, but it has been solved only like in the last couple of months. And more importantly, beyond inference computation, it has been used for solving a lot of other very important cryptography problems. And the construction comes from applying some amount of coding theory, as I will explain now, okay? And it depends on, the security here depends on some new cryptographic assumptions on being able to distinguish or not being able to distinguish, if you're a polynomial time adversary, between noisy code words and uniform vectors. Again, I'll elaborate on this, okay? So that's kind of the main, yeah. I'm sorry. Oh, well, then first I have to define what private information retrieval is. But if you know what private information retrieval is, the client who is querying the database can actually do some computation on the query and keep some secret key with them. I mean, this is kind of, almost explains it. But anyway, they can keep a trapdoor or a private key that depends on the query. And when the result comes back from the database, they can use that to recover the correct answer. And because of that secret key, the database will not know anything about the query. Yeah. It's private information retrieval, but the recovery of the response depends on the secret key that the client has. Okay. All right, so, but then actually this problem has a fairly simple solution, and I'll explain that now. And of course, we can use, once you have this, once you have encrypted matrix vector product, it's also pretty clear how to do the split model inference without splitting, actually. So we call encrypted model inference, where, Charlie just now, there's no need to split now, right? Charlie could just encrypt the entire weight matrix and the input, and then recover using the encrypted matrix product algorithm, okay? So this will actually, protect the model without relying on the heuristic aspects of model decomposition. But then, yeah, we'll come back to what caveats we have here. But let's focus on the encrypted matrix vector product problem. And here is a very simple solution. If you are willing to do pre-processing, there's a very simple solution. You just add a random matrix R to your matrix W, and this is just basically a one-time pad. So that protects W, and W hat is the encrypted, and then similarly you protect the query by adding a random vector. And now if you just look at the product of the encrypted matrix and the encrypted query, right, you have some extra stuff that you need to get rid of. And this W delta and R delta, where delta is this noise vector or that you added, can easily be removed if you pre-compute them. Okay, so we are not charging for pre-computation; we are only charging for online computation. But the online computation needs to compute R times Q because Q comes online. But R times Q is again as expensive as computing W times Q. So the purpose of doing all of this is lost if you have to do that, right? So we don't want this. And the solution actually comes from, again, a very recent notion called trapdoor matrices. What is a trapdoor matrix? A trapdoor matrix is one that looks random. It's indistinguishable from a random matrix, but it has this beautiful property of being efficiently computable for a matrix times vector product. Okay, so typically if you had a truly random matrix R times Q would take, if it's an n by n matrix, it would take n square time. But if R is a trapdoor matrix, it's not only indistinguishable from random, but R times Q can be efficiently computed in time something like n times polylog, or even n to the 1 plus epsilon for some very small epsilon. Okay, so that's the property. And so now it's obvious what we want to do. We don't want to use the random matrix, but we want to use a trapdoor matrix, right? So that's it. You understand the solution now. So using trapdoor matrices, we can actually have a template solution, a solution to the problem that I described in the previous slide, where you can basically use this, but with pre-processing. And we want to actually avoid pre-processing if possible, and this is where coding theory comes, right? So what we do is actually don't take W by itself, but then encode the rows of W with a good error correcting code D. Here it is sort of the, rows are code words. Typically, I don't know, at least to me, it's the other way around. But anyway, D is a generator matrix whose rows are code words. And then you add a trapdoor matrix like before. And for Q, there is some extra stuff just because you have expanded the matrix to take care of that additional, columns in W times D. You pad the query vector with zeros, but then you add a code word in the dual code to the code generated by D, and that is C, right? So now you'll see the WD times C, which was kind of hard to get rid of earlier, the noise, right, which needed the pre-processing, can be avoided because WD times C is 0 now. And of course, because you padded with zeros, WD times the expanded query is basically just WQ. Okay, so now this is good, right? Now you don't have to do pre-processing. The trapdoor matrix allows you to recover WQ because this R times Q hat is easy to compute given that R is a trapdoor matrix. So this is good. Okay, but what's the catch? Yeah. Yes. Yeah. Typically. Yes. Yes. Yeah. Okay. I did not mention that. Yeah. All the models we do after quantization. Yes. Yeah. If you don't, you have to do quantization in order to make any of these finite field algebra to make sense. Yes. Yeah. All cryptography is done over finite fields. Yeah. Right. So what's the catch? The catch is that Q hat. Why is Q hat, secure? Right. In our earlier solution, Q hat was secure because we added a random vector, right? Delta. Now delta is not delta, but it's a code word. And why should this code word protect Q hat, right? So that's the problem that we want to solve again. And I'm almost out of time, so I will just explain this definition from this paper. And the way that I would like to explain this, although it may not be the way that it's written in the paper, is basically when you look at this, it's just a code word and you have added a shift vector, right? And in cryptography, we know, or we have long believed, I should say, that if you take a random, if you take a random code, random but good error correction properties, and you perturb the code word by adding some noise, then that is indistinguishable from a random vector. And this is sort of the basis for a lot of homomorphic encryption using LPN, learning with parity or learning with errors type of assumptions. And this is sort of the same flavor, except what you do is just to connect to what I just said, think about S being just n. So each of them is just being a scalar. Then what we are doing is really adding a shift vector. Okay, but for a variety of reasons, primarily to make it cryptographically secure, what they do is not to individual coordinates, but chunks of the code word. So you chunk each code word into S blocks, and in each block you add a vector, a shift vector. And these vectors, the shifts, can be anything actually. That's the beauty of this assumption. And there are some scalars that you multiply with, again, for technical reasons that I won't go into. And the primary assumption that's being made here is that this sort of perturbed code word, so you take the original code word, chunk it into a bunch of pieces, and in each piece you add a vector, any vector of your choice, and multiply with some random scalars, and that new vector that you got is indistinguishable from uniform random vector. Okay, so again, this is an assumption. In cryptography, the only way we know how to give security is by making very crisp, well-defined mathematical assumptions about hardness. And here the hardness is that this vector, this perturbed code vector, is indistinguishable from a uniform random vector for any polynomial time algorithm. Okay, so once you do that, then mapping this to this should be fairly straightforward. There are a bunch of manipulations that I'm not going to go through, but this is basically the code vector, and this query, which could be adversarially chosen, is the shift vector, the delta that we are talking about, and then there are some scalars that you need to get rid of. Okay, so that's the main idea, and so that's about it. That's all I wanted to say. I know I'm out of time, but basically, there are a whole bunch of questions. So we have, I motivated this problem of offloading inference. There are two approaches. One, primarily based on ML intuition, making a new assumption which hasn't yet been tested mathematically to decompose the model and offload bulk of information, and is practically very usable. Then you have a more cryptography-centric solution using encrypted matrix vector product. Again, you make an assumption, but this is more mainstream crypto assumption, relatively new. It's also not tested by time, but more along the lines of standard assumptions. And using that, we can actually do better in terms of theoretical guarantees, but practically it is much less efficient, because even a polylog factor like log squared for dimensions that is of the order of thousands in machine learning models is more than 100 times, right? So getting rid of these polylog factors in encrypted matrix vector product is actually an interesting question. Okay, and there are other questions that I wrote here. So I'll stop there and answer any questions if you have. Thank you.
Any quick question? Thank you.
Okay,
Sanjay.
all right, thank you.
Can I start?
So our next talk is online talk. So our speaker is Jong Sun No. So he is professor emeritus at Seoul National University. Apparently, he was the first PhD student of PVK from USC. Over to you, Jong Sun.
Okay. Good morning, everyone. And Vijay, and congratulations on your 70th birthday. And I'm very happy to give a talk in such a memorable workshop. Title of my talk today is Cross MPT, Cross Attention Message Passing Transformer for Error Correcting Code, which was co-work with my former student. Next page. Next. Content of my talk. First, what is a neural decoder? And then model-based and model-free neural decoder. Then I'm going to introduce briefly transformer. Then error correction code transformer called ECCT. Then I'm going to introduce our research result, cross MPT, cross attention message passing transformer. Next. Cellular communication system, we have two different channels. First is forward channel called downlink, which is the channel from base station to mobile station, and high transmit power from base station. And generally, it is good channel characteristic. But in the reverse channel, I mean the uplink, which is the mobile station to base station. So generally, a mobile station has low transmit power, and it is a bad channel characteristic. So in cellular communication system, this reverse channel is a bottleneck. Base station has high computational capability, and various received signal from many mobile stations. So it is desirable to lower the packet error rate to save airtime due to retransmission from mobile station. So good error correcting codes are required in reverse channel regardless of computational complexity. So what about the neural decoder with good error correcting capability in this situation? Next. What is a neural decoder? Neural decoder is the application of deep learning technique to the decoder of error correcting code. So objective is overcome the limitation of a conventional decoder. For example, Billy propagation decoder and min-sum decoder. There are two types of neural decoder. First one is model-based neural decoder, and second one is model-free neural decoder. Next. Model-based neural decoder constructed based on the conventional decoding method, BP decoding and min-sum decoding. So it maps the iterative decoding process into neural networks. So problem is that there is a performance limit due to the restrictive architecture. Next. However, a model-free neural decoder employs an arbitrary neural network architecture, such as recurrent neural network and transformer architecture. It is not relying on the conventional decoding algorithm, but it is difficult to learn how to correct errors, and it has strong potential. And also, universal decoder can be implemented using model-free neural decoder. Universal decoder means that it can decode most of the code class with the same structure or same algorithm. And then transformer-based neural decoder has shown great performance. Next. I'm going to introduce here briefly what is the transformer. Transformer is introduced to capture the long-term dependency by attention module and positioning encoder. Next. Attention mechanism is that finding relevance between query and key and reflect the value. So query, key, and values is denoted by Q, K, V, which can be obtained from the input embedding, such as received signal. In here, the G. But WQ, WK, V is a trainable Wayne matrix, N is number of token, and D is embedding dimension. Next. So here is the block diagram of attention mechanism is here. So left side, we have the input embedding. Then using the WQ, WK, and WV, we can obtain the QKV, and finally we have a softmax of that. Next. There are two different types of attention. First one is self-attention, and second one is cross-attention. Self-attention use the same sequence to obtain Q, K, V, but in the cross-attention, we have two different sequences, G sub 1 and G sub 2. So Q is obtained by G sub 1, WQ, K is obtained G sub Q2 and W sub K, and V is obtained G sub 2, W sub V. So in our application of decoding, G sub can be a magnitude of received signal, G sub 2 can be a syndrome vector. So we focus on we focus on finding relevance between tokens of the different sequence. Next. Then the second topic is what is the positional encoding? Transformer takes an input sequence at once with positional encoding, then give positional information to each embedding vector, and then added before attention module, then elementary-wise operation is needed. So in here, so for our application of the decoding, positional encoding can be obtained by the training. Next. What is the transformer? It is good at long sequence, and all input can be done in parallel. and it offers interpretability through attention mechanism, and it can handle multimodal data. So we use the decoding of the error correcting code. Right side of this page, this is a general transformer, but there are two parts, left part and right part. We only use the left part to decode the error correcting code. Next. So first, error correction coding transformer, ECCT, is introduced 2022 by those authors. Title of the paper is Error Correction Code Transformer, which was presented NeurIPS 2022. Next. So in here, I'd like to introduce what is the error correction and code transformer. It is universal decoder, so can decode most of the code class with the same structure, I mean same algorithm. For example, using the same algorithm, LDPC code can be decoded, and also Polar code can be decoded. But in the parameter may be little different. But using the same parameter, we can decode both LDPC code and Polar code. Transformer can learn the relation between bits of code word, initial embedding by using magnitude and syndrome of received code word Y, then decoding by masked self-attention model based on Perestreng matrix. This ECCT is composed of the following three blocks: initial embedding, decoder layer, and output layer. So received signal Y is equal to X plus G is X times G tilde. In ECCT, we trying to find the G tilde by training. So next. Then what is the overfitting issue in model-free decoder? ECC decoding is a kind of classification problem of 2 to the k classes in NK code. But it is impossible to train all code word even for moderate K, because each K we have many samples. Each value of K, each code word we need many samples to training the ECCT. So, and also it is poor generalization to unseen code word. But the solution is that syndrome-based approach. Decoder's performance is invariant to the code word. Next. So what is the preprocessing? Syndrome-based preprocessing is that set Y tilde equal to magnitude vector of syndrome and received signal, and 1 minus 2 syndrome vector. 1 minus 2 syndrome vector means that we convert the 0, 1 data to plus minus 1. So received code word is Y equal to X plus G is equal to X times G tilde. So magnitude is given here. So because it does not depend on code word, because code word composed of plus minus 1. And syndrome S of Y equal to H times error vector, it does not depend on code word. So all code word instead of 2 to the k code word are sufficient for training. So Y tilde is equal to Y magnitude, and 1 minus 2 SY is the The first part is n-tuple vector. Second part, syndrome part, is n minus k tuple vector. So it is 2n minus k vector is sufficient statistics for maximum likelihood decoding. So transformer learns the multiplicative noise G tilde by using this preprocessing. Next. So here is the initial embedding layer. Project each element y into d-dimension embedding. So phi sub I is equal to y sub I magnitude times w sub I for I is less than or equal to n. Otherwise, it is becomes a syndrome part. So Wi is on trainable initial embedding. Next. In decoder layer, standard transformer encoder using self-attention, feed-forward network, and normalization. And also masked self-attention focus on important relation within all 2n minus k position. Then we repeat n times in right block diagram. So left side, it is a attention map. So magnitude is composed of magnitude and syndrome, 2n minus k by 2n minus k attention matrix. Next. In decoder layer, mask matrix constructed based on PCM using domain knowledge. So in the left block, it is parametric matrix, and right block is bipartite graph. So first node is not directly connected to second node. So two component of this matrix is masked, black out. But first node is connected to third node by distance 2. So 1,3 component is used. So this is the mask matrix of ECCT made from this bipartite graph of parametric matrix. It facilitates the training process by focusing on important relation within 2n minus k position, and mask in this matrix, we mask the unimportant relation. For example, 1,2 component, because in bipartite graph, first node is not directly connected to the second node. Next. In output layer post-processing step, we do the fully connection layer 1, make 2n minus k by n 2, 2n minus k by 1, and fully connection FC layer 2 makes 2n minus k by 1, 2, n minus k. So output is the then estimation of the multiplicative noise Z tilde. Then we multiplied component wisely with the y. Then we obtain the decoded x of b hat. Next. So, and here, what is the pros and cons of ECCT? Pros is it can do the universal decoding, which means the same decoding algorithm can be decode for most of code. And it works well for short length and high rate code. Cons. What is cons? Training is very difficult for low rate code. Decoding complexity is higher than model-based decoder. So novel architecture to improve both decoding performance and computational efficiency. Next. So we proposed cross MPT, cross attention message passing transformer, which was presented in ICRR this year. The right side, we describe the whole block diagram of cross MPT, basically, which we use the transformer, I mean the left part of transformer. So next. Motivation one is the motivation one. Two inputs are multimodal data. One is a magnitude. Second one is syndrome, S of Y. So magnitude means the reliabilities of all bits. And syndrome is information of erroneous bit position. Then embed magnitude and syndrome separately without concatenation. The motivation two, inconsistent mask matrix construction in ECCT. So in ECCT, they use the mask matrix by in magnitude to magnitude depth connection in tenograph, and syndrome to syndrome only, which means there is only self-relation. But in our cross MPT, we use the magnitude syndrome by using obtained from PCM, pedestrian matrix. So in ECCT, use the self-attention, but we proposed cross attention in cross MPT. It is the first application of cross MPT in error correcting code transformer. Next. So initial embedding utilize distinct informational property of multimodal data, then embed magnitude and syndrome separately without concatenation. So magnitude embedding is in here, and syndrome embedding is given in the last equation. Then block diagram is given here. So from received word Y, we have magnitude embedding and syndrome embedding differently. So it is a multimodal data. Next. So iterative update of cross MPT, iterative update of cross MPT module. First, cross attention is the left part of this block diagram. Update the magnitude embedding. So we obtained Q1 from magnitude embedding, K1 from V1 from syndrome embedding. In seconds cross attention, we update the syndrome embedding. Q2 obtained from, at this time, syndrome embedding. And K2, V2 is obtained from magnitude embedding. So it is a cross attention. That's our key point of our cross MPT. Next. So in first cross attention, we obtain M prime using here in the softmax, and we obtain the Q1 and K1, V1. Then next. In second cross attention, we use the S prime using Q2, K2, V2, where Q2 is SWQ, K2 is M prime WK, V2 is equal to M prime WV. So left part is first cross attention, right part of this block diagram corresponds to second cross attention. Next. So this is the iterative update of cross MPT in the previous page. Next. Next. So, no, previous page, please. Yeah, message passing algorithm can be understood in the left part, but in our cross attention MPT can be understood in right part of this block diagram. So this is a block diagram of the cross MPT algorithm in the previous page. Next. Here is the no, this is the mask matrix for cross MPT. First one is mask matrix of ECCT, but the bottom mask matrix is for the cross MPT. So this mask matrix of cross MPT is very simpler than the mask matrix of ECCT. Only use the we do not use amplitude to amplitude and syndrome to syndrome. So we only use the mask matrix, the magnitude syndrome. So it's much simpler. Next. This is the performance of the performance comparison with BP decoder for 121 AD LDPC code. So the cross MPT, our proposed cross MPT is show the best performance compared to ECCT and BP algorithm of iteration 2050 100. Right diagram show that the performance of 64854 IEEE 8.11 and LDPC code. So our proposed cross MPT is much better than other algorithm. Next. Here is the decoding performance of BCH code. So cross MPT is also better than other algorithm, other BP algorithm for this BCH code, and also right part show the decoding performance of turbo code. Here also cross MPT is better than ECCT. Next. Here is also decoding comparison of 12170 LDPC code. So the cross MPT is also better than BP and other BP algorithm and ECCT. The right part is the decoding performance comparison of 128 and 86 polar code. Here, also cross MPT is much better than other decoding algorithm. Next. Here is the decoding performance comparison. This transformer is a universal decoder, so can decode many class of code with the same algorithm. So left part is the BP-based decoder. Right part is model-free decoder, such as ECCT and cross MPT. In here, cross MPT is better shows the better performance than other decoding and other decoder. Next. So complexity analysis, reduction in flops and in inference time and training time. So more complexity reduction for longer code. So in the third column and fifth column compares the uh, computational complexity of cross MPT and ECCT. Our proposed cross MPT is better than ECCT, and also shows the comparison of inference and training and mask density and also memory usage. So in our proposed cross MPT is better than other ECCT. Next. His comparison with the ML decoder of BCH code is slightly worse than ML decoder, but is better than ECCT for 16 BCH code and 3121 BCH code. Next. Here is decoding performance of long code of Polar, WRAN, and LDPC code. And also, right part shows the performance comparison in relay fading channel. So our proposed cross MPT is better than other other code, even in the relay fading channel. Next. Conclusion, transformer-based universal decoder such as ECCT and cross MPT. Cross MPT is novel transformer architecture inspired by message passing algorithm and regard the magnitude and syndrome as a multimodal data. And we use the self-attention, cross attention in cross MPT, and iteratively update of the magnitude and syndrome embedding and improve both decoding performance and complexity. And also leverage down domain knowledge of coding theory, syndrome-based preprocessing, and masked attention mechanism by using parity check matrix and syndrome message passing. Next. Can you go up to second page or third page? Third. In cellular, the previous page, please. Previous. Yeah. This cross next. Cross MPT require a lot of computation, but generally in base station has a high computational complexity. But in this situation, what is the most important thing is lowering the packet error rate, because which can save the air time due to retransmission from mobile station. So air time is a bottleneck in cellular communication system and is very important. So neural decoder with good error correcting capability can be useful in cellular communication environment. Okay. I think I ran out of time. So if you have any question, then please email me. Then I can answer for this one. Okay. Thank you.
I think I have a quick question. Uh,
I think he left.
Hi, Johnson. Can you hear me?
Yeah.
Thank you for an excellent talk.
Yeah, thank you.
So based on your cross-MPT decoder, what codes would you employ for the uplink? What would you suggest for better performance?
Actually, we do not specifically consider any specific code. We just study the cross MPT, and it can be useful in cellular communication system, but we do not think about yet the specific code for uplink. But it can be useful in the cellular communication system, and Huawei in China telecom they very interested in this our cross MPT.
Very good.
Okay.
Yeah, thank you.
Congratulations on your 70th birthday.
Right. Thank you, Jungsen, and I'm so glad that you could make it. Thank you.
Okay, thank you. Okay. Then I close my talk. Thank you so much.
Hello all. Hello all. Good morning. So this is the second session today of CodeIT workshop. We have a sequence of 3 talks. First talk would be by Professor Sundarajan. I don't think he needs any introduction. He'll be talking about function correcting codes.
Okay, thanks Lalita for inviting me and LP for introducing me. I have been known Vijay for online viewers, right? Yeah. Okay, so I have been known Vijay for more than 3 decades. Initially in IISc venues, where he used to take us for veg food and things like that, right? After that, I don't know whether Vijay remembers or not. I applied to him USC for admission, and I wrote to you also. You may not remember. You must be getting so many applications, right? So at that time there was no funding, so I wasn't lucky, but I became very lucky afterwards, being his colleague for 2 decades with adjacent rooms, right? A lot of my students did his courses and they all benefited, and indirectly I also benefited. Thank you. Likewise. Okay, fine. So I'm going to talk about function correcting codes. It is it's okay now. Okay, so it's a joint work with my colleagues Charul Rajput, Ragnar, and Camilla in Alta University. This outline. Function correcting codes has come up in 2023, that is just 2 years back, and it is a generalization of error correcting code in theory itself. Any results you derive with function correcting codes with a specific function, if the function turns out to be a bijective map, then it becomes error correcting code result. Okay, those function correcting codes are always, till now, they are systematic and non-linear, and why they are systematic and why they turn out to be non-linear, I will explain soon. Like linear codes are described as generator matrices, and cyclic codes, the generator polynomials and things like that. These codes are specified in terms of matrices because they are non-linear. You have to give the distance distribution between any code word to all other code words. So they are dealt with so-called distance requirement matrix and function distance matrices. And okay, so all the function correcting codes available in the literature so far, they protect the function values. The transmitter knows the functions to be evaluated at the receiver, and the receiver wants only the function values in particular. However, it is supplied data also. That is how the code becomes system. I will explain why data is also transmitted. And what we do is that we provide function correction capability along with protection for data also. This is the new contribution, and already we have results available at IIT. What happens when the function is a linear function? So I will conclude with some open problems. Okay, so this is the paper I'm talking about. This came in 2023, and the formulation is this. I will come back to this. This is the formulation. The encoder does systematic transmission. It transmits the information vector u as well as the check vector to the channel, and the output y is fed to the decoder. The receiver is primarily interested in the function of the information vector. However, it will be supplied u also as a systematic form. This is the code word. Fine. So the F has mapping from FQK to the image of F. The size of image of F will matter a lot. Okay. Now there are T errors, and the decoder output is FU, and the image of F, the cardinality of it is called the expressiveness. Okay. Now what I want, if there are errors, say T of them in the channel, my function value should remain intact. Okay. Data wise, what the receiver will do is it will do decoding as if it is an uncoded data. It will do the recovery of that. Okay. So now I will go back. Since the code is going to be systematic, I will quickly want to recollect the classical error control code systematic forms. So this is what we have. There is no function here now. Now the transmitted code word is UP, N is K plus R. R is the redundancy, M is K power K because it is systematic, and the D I will receive 2T plus 1. Generally what one says NMD code, right? No, here what we will do is that we will translate everything to RMT code. Okay, RMT code is same as NMD code. Then the well-known bounds, singleton bound translates, I am rearranging everything, keeping only R and T, so you get this. Similarly, Plotkin bound, when rearranged, becomes this. I am giving everything as a bound on the redundancy. Why? The target in a function correcting code is that I want to minimize the redundancy. The point is that I will be able to manage the whole show with lesser redundancy than you use a classical error control coding for the error correction and then evaluate the function value. You will be able to manage with lesser redundancy. So I will be always worrying about lower bound on the redundancy. So I have reformulated everything. We will recover this from a known result later on. Okay, so this is a function correction setting. Okay, now, okay, why even if the receiver doesn't need the information bits, it will be supplied. The reason is that nowadays you don't find point-to-point communications isolated. They are always part of a network, right? So now consider this wired network. This wired network, we have a server and there are 10 nodes. Say all the 10 nodes have their own functions to be evaluated. A1 is interested only in the function value. It's not interested in any data. Data is irrelevant to them. For all the 10, the data is irrelevant. Yet, the server needs to send the information bit also to A1 because how will A6 will get from A1 the function of interest it wants? A1 has to supply. How, say this is F1 and this is F2. How will A6 get F2? It has to get from A1. But if A1 doesn't have the information bits, it cannot calculate F2 and give it, right? So, along with the function of interest to A1, which is F1, the server will transmit information bits also. So that A1 can use those information bits to calculate the function of its children in the network, right? Similarly, A6 may be forwarding some data to other nodes that follow, and there also this guy should have the information vectors. Only then you can calculate the function that is of interest to it, right? So that is why the formulation is that you have both information vector and the parity vectors designed. The parity vector is designed solely to protect the function values. Okay, so what is the formal definition? Systematic mapping. K bits are mapped onto K plus R symbols, and what you want in a classical error control coding is that the Hamming distance between two code words is greater or equal to 2T plus 1 for any two code words you want, right? Now you see the advantage, where is it coming from? Now I want this condition to be satisfied only for those cases where FUI is not equal to FUJ. If FUI equal to FUJ, the function values are same. You transmit that code word, you wrongly get to another code word for which the function value is same, but my function value is same, I am protected against the function errors, right? So this leads to saving in redundancy, correct? The conditions now required are lesser in number, where in the classical error control coding, you wanted for every pair of code words certain distance, minimum 2T plus 1, but now I don't want. consider the set of information vectors, group them together, giving the same value, right? Among them, if the error happens and gets transacted, you transmit one vector in that group and go to wrongly decode to another vector. My function value is same, so I am safe. Correct? This leads to advantage in having a smaller redundancy as far as the function values are concerned. So how should I now, this is for the, see, along with this requirement translates to the Hamming distance between the check symbols vectors, check vectors need not be greater than or equal to 2t plus 1. You can remove the, you can relax the restriction by subtracting the Hamming distance between the information part, right? So what is it that we are designing? We are designing only the set of check vectors. How many of them? E power k, because the code is systematic. So this is generally a nonlinear code, and this is nothing but the error correcting code of length r. R is the redundancy, right? So what is it that I want? I want to design my check code. I call it a check code with smallest r such that this is satisfied. This is what is done. And why error control coding is a special case of FCC? Suppose F is a bijective map. Then what happens? There is a one-to-one reversible correspondence between UI and PI, right? One-to-one correspondence. So there are q power k information vectors, there are q power k function values. If I recover the function value, I am recovering the information vector also, right? So what we will do, we will derive results for FCCs, and then we will get complicated expressions sometimes. Then we put the restriction that the F is a bijective map. Then what happens? It falls back onto the known results. That is what is the advantage of working with FCCs. Okay, example. Consider the case. I want to transmit 2 bits, and the redundancy I am adding is 2 bits. How many errors I want to correct? 1 error. What is the function that is of interest now? The entire theory is strongly dependent on the function. For some function, we have optimum codes constructed. For some functions, only bounds are known. For some functions, nothing is known. Okay. So consider this function R. U1, U2 belong to 0, 1. The receiver is interested in R of these two. Now, what does this mean? U1, U2, 4 possibilities, because k is 2, 0, 0, function value is 0. For all these 3, the function value is 1. Right? So what happens? If now I have got listed 3 codes. Take the first code. This code, I am adding parity 0, 0 to this and 1, 1, 1, 1, 1, 1 to all these 3. Now this code, you can see that it is nonlinear. Okay? What does the receiver do when it wants to recover the information bits? First 2 bits only it will consider and it will take it. Then, as far as the function value is concerned, suppose 1 error occurred. You can see that the distance between all these 3 from all 0 is 3. Each one of them has distance 3. So, whenever 1 error occurs from any one of these 3, the received vector will continue to be closer to function value 1 only. It will wrongly decode. Say I transmit this and the decoder receives this. Now error has happened, but function value remains same. So function value is protected. What is the minimum distance of this code? 1. So it is not giving any protection for the data. But it gives one protection error for function value. You transmit 0. When will you get the function value to be erroneous? 3 bits have to go wrong. Only then it will happen. If 1 bit goes wrong, it will still continue to be close to 0. Okay? So the function value is protected against 1 error. So far so good. Okay, another code. Same job it does. All 0 have say distance 3 each. So each one of them is at a distance 3 from here. But this is also a nonlinear code, but the minimum distance of this code is 2. That means you can detect 1 error for data now. Right? Function correcting code 3, same. Now different from this, I changed this here. Different from this, it corrects 1 error for function value, but it cannot correct an error for data, but it can allow you to detect. Okay? So, all the 3 codes are correcting 1 error. However, these two codes are better than this guy because it seems to give some kind of a protection for data also, right? The papers didn't bother about this. They went on doing only protection for function values without worrying about can you augment the error correcting capability for data also along with that, right? So yeah, all the three codes correct one function error. Now, okay, then tends to think you want to correct one error for the function value, I will use single error correcting code. I will get it corrected. One error is corrected and then I will evaluate the function value. Then what you will do, you will transmit a k equal to 2 code, t equal to 1, correct? The minimum length required is 5. Whereas now I am managing with 4. So I have saved bandwidth, correct? So this is the basic about function correcting codes. This is now has been done for, we are discussing Hamming metric substitution channel, correct? First thing we are worried about Hamming metric only, then substitution channel, no intersymbol interference, right? But the results have already been published for other metrics, for symbol pair read channels, B symbol pair read channels, which are nothing but ISA channels type. Okay, for them also the metric is now different. For those metrics, classical error control codes are already there, but function correcting codes are now reported. There are the things, but all the works that have been reported so far do not explicitly say that. I am showing you the slides, the same codes I am showing. This code, I am now going to say that it is 4413 code. What is this? No more NMD codes. We always hear after it is NMDD-DF code. What is DD? Minimum distance as far as the whole code is concerned. That will indicate the protection against the data. But what is DF? Distance between two function values. How is it defined? Distance between these two values is cluster all the vectors which give the value 1 and this guy. Between these two clusters, what is the distance? Pairwise take it, find the minimum. Now you can see that here it is 3. Here also it is 3. Here also it is 3. So this code I will call it 44NMDD2 DF3. This is also 4423. This is 4413. Now the question is, I want to minimize R. Okay. One would think that if the transmitter knows the function values and the receiver is interested only in the function values, why don't you simply let the transmitter calculate the function values, encode it and send it? In which case, for this case, you would have managed with 3. You take the function values 0 or 1, no, take 3, 0, 0, 1. But now what happened? The receiver lost the data. So in a network situation, that receiver cannot do any more service to its children. So from the networking point of view, you have to send U so that the receiver calculates other functions that are of interest to the other receivers which are going to get the information from this receiver. Correct? At the same time, I want to minimize the bandwidth requirement. That's what I am doing. You want more protection for data, you get the data as it is and higher protection for your function value, and then you give higher protection function value for the next guy. You can adjust it. So there could be a nice trade-off, right? Okay, so the original paper lists very clearly what happens for different functions. There are 2 more functions is listed, but I have removed them because it becomes congested and becomes difficult to read. Okay, now you see, these are the binary function. I will explain what's a locally binary function. This no, it's a Hamming weight function. Given a vector, what is the Hamming weight of it? That function. Okay, so for any binary function, the lower bound for FCC is 2t. But if you first have classical error control to correct t errors, and then you will see what is the redundancy. It is t log k. You can see the proof for this in Roth's book. What it means is that the amount of redundancy you do by sending classical error control coding and then extracting the function value for the information after extracting the data bits from there, the redundancy depends on k, not just on t. So as k is large, you are going to pay through your nose. Okay? Okay, I will do this. I will transmit the information bits, then I will independently code the function values and then augment it and send it. So that you are happy now? No, that is going to depend upon E. What is E? cardinality of the image of f. Correct? That is going to hit you this. So now it depends on TNE, whereas function correcting codes, amount of redundancy you can manage with is 2t. How? I will explain for this. Take any binary function. I have got k-length binary vectors. Take any binary function which gives only 2 values. Okay? Maximum or minimum. Say max min only. So you can say 0 or 1. Repeat 2t times more. Send it. Done. So amount of redundancy is 2t. What is the length of the information vector? Who cares? I don't need to care, right? That's it. So independent of the message vector, the amount of redundancy is 2t, which is independent of k. If it is classical error control coding, which is independent of expressiveness if you do coding on the function values. So this is the new area, right? Now I do develop results for these functions with some arbitrary functions, say linear functions. I calculate this. So what is this table says? This table says lower bound for this function is this, and what they are reporting, the explicit code construction is this. So they achieve the lower bound. For this function, they achieve only 40. Their construction is not necessarily good, and lower bound they are giving is this. Okay, so there is room for improvement. Whereas for these two, there is no room for improvement. It is achieved. Okay, so there are two more functions which they claim that it is useful. It is useful for machine learning and storage channels and things like that. So I'm running short of time. So what I will do is, I have 10 minutes more. Okay, so this we have already seen. Okay, just to show you that you can have data protection as well as function value protection simultaneously. This is an example. See carefully. It takes 4 values. So expressiveness is 4. What are the 4 values it takes? This is nothing but your Hamming weight. Hamming weight of the vector is, this is a 3-length vector, so it can be 0, 2 or 3. Now I want to provide 1 data error correction for data and 2 error correction for function values. So I want DD3 and DF5. Do I have a code? Yes, this is the code. See all the 8 things I have written here. Consider these 2 columns only. You can see that the minimum distance is 3. It's a linear code with minimum distance 3. That means already with the 9-length code, first 6 locations themselves is giving me distance 3. That means 1 data error is correctable irrespective of what I am going to add for the next 3 bits. Next 3 I am adding this. You can see that the distance among them is 2. 2 for 2 function values you should take. You shouldn't take these 2 because the function value is same, so I don't mind. So this and this 2, this and this 2, this and this 2. So this is my overall code. I have achieved single error correction for data and 2 error correction for function values. So a lot of open problems. So what is the formulation now? NMDDDF, right? Given DF specified, maximize DD. Given DD specified, maximize DF. All are open problems. And okay, now what happens to the basic structure? You have this, right? Now in the receiver, you will have the formal decoder for your classical error control coding, minimum distance decoding, Bellicam message, whatever you have it. But for function values, you need a separate decoder. Okay? So that is going to be strongly dependent on the receiver, the function you are employed. Correct? So we have now 2 decoders. Within the receiver, they are going to work in parallel and strong dependence on the function. In some sense, what is it that is getting done now? Originally what you thought, you will send the data encoded with classical error control coding and then receive the data and then follow it up by function value evaluations. Communication and computing are now separate. Correct? That will work for any function. Whereas now what I have done? Now the code design itself has merged both. So it is in some sense like coded modulation. Modulation and coding has been merged. Similarly, this is now joint communication and computing. Okay. So, okay, this is nonlinear code. Okay, the first interesting theorem does the Lenz paper, the original paper proves is that for any function, as long as the expressiveness is more than 2, the lower bound is 2t. We all know very well that binary error correcting codes, which are MDS, apart from non-trivial ones, do not exist. Correct? But here they do exist. Meaning by the codes meeting this bound exist for several functions. In some sense, this is the MDS bound, right? That is why I reformulated our classical things also in this way. See that? This is nothing but my Hingleton bound. Okay, so MDS bound function correcting codes, MDS codes do exist. The first two functions, they do exist. You can see that. Okay, so I'm running short of time. So what I will do, I will quickly explain what is meant by locally binary function. You have k-length symbols. Take one vector, draw a sphere of radius 2t. Okay, calculate, see the function values that is taken by the vectors of all the points within the radius 2t vectors. If they are only one of the two values, then we say the function is locally binary, right? For such functions, you can achieve with minimum redundancy 2t. How? It's very simple. You transmit one u, okay? Say t errors occur. What will happen? You will receive another vector which is at a distance t, right? What the receiver knows, it doesn't know the transmitter vector, but it knows the received vector, right? Draw a sphere of radius t around that. In that t radius, transmitted guy will be present certainly, and it will be taking only two values because it is within the sphere of radius 2t. Correct? So what the way I will transmit is that I want to transmit u. Okay? I will say the sphere of radius 2t takes two values. I'm interested only in the function value at u, right? It takes two values, say max and min. I will say 0 means min, max means 1, use repetition code and send it. How much redundant bits I am adding? 2t. Correct? The receiver now has got only received vector, right? It computes the function value on the received vector. It can be either max or min because it is within the, it's a binary 2 value, not locally. So it has got t, 2t. Now t errors occur, majority logic gives the answer. Okay? You don't recover the function, but you do recover the function values. With how much redundancy? 2t. Independent of the locally binary function can take 10 crore values. Doesn't matter. My redundancy is only 2t. Very good. So this no time. So I will skip this formal ways of defining these things. Okay. Plot-in bound. So how does the code get described now? Now it's not a linear code, so you can't say that distance distribution seen from a code word is same for all the code word. You can't do that. So all pairs of distances has to be taken into account. Correct? If you take that, that is your distance matrix. It is a matrix of size q power k by q power k. Pair of every pair of vectors, between them there is a Hamming distance, that is the vector matrix. That matrix entries is ijth element. Now the plot-in bound for a function value, you can rewrite it. Rf of kt. This is a lower bound. Rf of kt is this much. This is the plot-in bound. Plot-in bound does what? You simply take the minimum distance and do the plot-in bound. Nah? You don't take into other distances. Next to minimum, all such things you don't take into account, right? This is generalization. Correct? So, what we have, one paper has come 2 months back from one of my students, and in this paper what we did was that we focused on linear functions. Apart from other results, we focused on linear functions. Okay? Now what happens? The function is now linear. Since the function is linear, I need not consider all the values of the image values of all the vectors. We know that linear functions, all the information is absorbed in the kernel. Correct? So, what happens is that the bound, which was very complicated, in general, for linear function turns out to be very smooth. You see, I have a closed form expression now. Right? So, what happens? Minimum redundancy required is this expression. What is S? See carefully what is S? S is sum of the Hamming weights of all the vectors in the kernel. That is a single number. Okay? So, I don't need the entire distance matrix of all the pairs of code words. I don't need it. For the function, I will see the kernel, see the vectors in the kernel, see their Hamming weight, and sum it up. That is a number. Finished. Why I am saying This is a generalization of classical error control coding. Now, if my function is onto, here it is this now. If my function is now onto, what will happen to the kernel? It will have only 0 vector. What is the sum of the Hamming weights of the 0 vector? 0, right? So put S0 here. You see that this is nothing but your classical plotting. Like that, you go on deriving Hamming bound, all the bounds you derive, and then make this. For linear functions, you derive all the bounds. Then make the linear function onto. Now it becomes classical error control coding, so you will recover all the bounds. Okay? So our Hamming bound we tried, but it became very complicated. Right? So I have 2 minutes more. Okay, so what is summary? The framework of function correcting code is a generalization of error control code was discussed. Even in classical error control coding course, what do? You start with nonlinear bounds, 1 or 1.5 classes, and then you get into linear codes. Correct? Now, where are we at what stage we are in function correcting codes? First 1.5 classes. All codes are nonlinear. All the bounds you can deal with, no problem, right? And deal with functions which can be specialized to bijections. You will get your old results back, right? Then the results known for several classes of functions with Hamming metric was summarized. FCC for data protection was shown. What now we are shown with that example is that you can have data protection coupled with functional correction, and the simplifications arising from considering the function to be linear was presented. I showed simply a example types. So what are the possible directions for further work? Simplifications for linear function for other metrics like the symbol pair metric. Symbol pair metric FCC has been reported already. It is there in TIT, but they have not done it for linear functions. You can take any discrete memoryless channel, find a matched metric, have codes on them. Now do function correcting codes for that metric. For every metric you will have function correcting codes, and for that metric, for every function you will have codes. So there are a lot of directions to go forward with. FCC for other metrics match to known channels like binary asymmetric channel, you can do that, no problem. Then code constructions with low complexity encoding and decoding also can be attempted. We never bothered about encoding and decoding complexity. We are at the stage of constructing codes, good codes, right? So improving known bounds like 1. So while the work was, this is still under consideration. This is there in archive, yes. So these people have tightened the bounds which was originally reported by Lex paper. Original paper said 10 by 3 t minus 1 lower bound, right? These people have tightened it out, right? Even stricter bounds for function correcting codes for certain functions. And more importantly, from the communication point of view, you can do soft decision decoding of function values, hard decision decoding, right? So a lot of directions are open, right? Some of my students are doing some of these open problems. Thank you.
I think maybe we have one quick question.
Yes, Sergey. Where's Vijay? Yeah. Different functions. Yes. Of course, yes. See, that is the function, the information bit is sent to that guy. See, take A1. None of the nodes are interested in data. Everybody has his own function of interest, correct? Now, server will do what? It will send a systematic code. So A1 recovers its function value with protection, gets information vectors without protection possibly. Now I am saying with protection also you can give. Now A1 has the information vector, calculate F2 which is of interest to this guy. It will use another code which is function correcting code for F2. So go along. No. You have network coding, nah? Right? Ling and that guy's paper. Classical network coding, what flows? Information flows, right? Now what I am saying, apart from information flow, let it flow and then superimpose redundancies for function value corrections for all the nodes. Network coding, every node is an encoder. It has its own code to generate and then forward it. So Now you can have network coding with function flow. You can have, no problem. Now here also some interesting thing happens. You see here, this is wired network, right? This is a common line and then come, right? It's wireless. Now you'll have to be very careful to give this guy something. This guy has to be supplied something, but whatever function error creating code you employ here will go to all the four. So now we have to possibly design something else which is more efficient. Otherwise, a function value for these four guys one at a time division. You have to do that. Yes. Any other question? Yeah. No, I'm not doing that. That is what you should not do. That's what I have been telling for half an hour. Yes?
So,
You should not do that.
Can I ask you to take the question offline maybe?
Yes, no problem.
Fine.
Yes.
Yes.
Sorry,
Balaji, maybe you can talk to him afterwards. So our next speaker is Professor Sudhir Gopade. He's going to talk about nice class of codes with nicer weight distributions.
No, you could ask me.
Yeah.
Okay, good afternoon. So first of all, I want to thank the organizers for having me at this nice conference to honor Vijay. It's a pleasure and privilege to be here. I think I have known Vijay for, I was just thinking, about 28 years now. We first met in Lumini in France and then in Los Angeles and of course Bangalore several times. And right. So, Vijay, as we all know, is not only one of the strongest researchers in coding theory, but also one of the nicest person I have known. So he's, kind, generous, and a thorough professional. I always think we have a lot to learn from you, Vijay, and hope you have many happy returns of the day. So, I'm sorry for sort of funny title for this talk, but I'll explain what this nice code is and hopefully convince you that it is not, it's nice. So this is a, this is sort of, is it on? Oh, I have to, I wanted to use the pointer. Oh, okay, thanks. So this is a joint work with Mahir Bilenjan, who is a professor at Tulane University in New Orleans, and it sort of builds up on something that we did about a decade ago with Peter Bielen at Copenhagen and my former student Sartajul Hassan, who is now at IIT Jammu, and then a follow-up paper with Peter Bielen. So I'll just get started. I don't need to tell this audience what a linear code is, but just to set the terminology, by a code I will just mean a classical linear code or block code with the Hamming metric, and I'll use the notation NKQ code to mean that a query linear code of length n and dimension k, which is of course you call it a non-degenerate if it's not contained in the coordinate hyperplane, and there's the Hamming weight and the minimum distance. And I'm generally interested in this weight distribution of a code, which is kind of telling you what are the possible values of weights that the code can have, and how many code words have that given weight. Okay, so in other words, you kind of want to know this sequence A0 to AN, where AI is the number of code words of weight I, or you could write it as a one variable polynomial or a two variable homogeneous polynomial. Sort of think of it as knowing the horoscope of the code, and it's usually very difficult, but of course very interesting. So this is something which many people have looked at for over the years. So this is one classical result. If a code is MDS, then we of course completely know the weight distribution. This is very classical. Suppose the the NKQ MDS code, so minimum distance is n minus k plus 1. Then the only non-zero weight are the consecutive ones from D to N. So they are distinct, strictly increasing, and this is the number of code words of weight I, where I is anything between D and N. If I come to something like Reed-Miller code, for the binary Reed-Miller code already of second order, this is the work of Sloan and Berlekamp in 1970. And you can, I'm sorry, this is, I don't know if it is readable. I don't really want you to read all these formulas, but these are the Hamming weights. Well, here J is varying from 1 to integer part of M over 2, and this is the corresponding AI for that weight I. So already for a binary Reed-Miller code, it's somewhat involved, and for the query Reed-Miller code, in fact, the weight distribution was proposed by Michaelis actually in 1969, and rather recently people found that there were some mistakes, and sort of a corrected version or a precise formula are given in a paper of Chuxing Lee, which was published in 2019. And again, I don't want to read these formulas, but these are the, by the way, these tables are borrowed from the paper of Chuxing Lee. I just, rather than type them out, I just reproduce the image. They do involve some parameters which I have not defined, this V2J plus 1, which have to do with number of quadratic forms of certain rank or a type and so on and so forth. But the point is that this weight distribution is completely known for second order query Reed-Miller code. And that's more or less the state of art as far as the general result is concerned. For third order and higher order, we don't know that in general. I think for third order, Naveen has worked on this, and probably he knows more latest. Maybe for one knows up to 3.9 or 3.10, something like that, and maybe 4.9. And that's there's a paper actually this year published by Marco and Borisov, and so that's more or less. So we don't know the weight distribution or the spectrum of general Reed-Miller code, even in the binary case when the order goes beyond the second order. So, all right. So, so now what is this? What is this nice code that I want to talk about? So the nice code actually comes from some classical objects which come in algebra, geometry, algebraic geometry, invariant theory. So they have to do with what are called determinantal varieties. So determinantal varieties are the objects which will give us these nice linear codes. I just quickly explain to you what these are. What you do is you start with a matrix whose entry is variable, independent, indeterminate. So L cross M matrix, let's say. Okay. I look at the ring of polynomials in those L times M variables, and with coefficients in my finite field Fq, and this is for me the set of L cross M matrices with entries in Fq. By the way, it's a good exercise for those who like determinants but also algebra to prove that if you have a square matrix whose entries are variables, then the determinant is an irreducible polynomial. That means it doesn't have non-constant factors. A glorious generalization, and quite non-trivial one at that, is the fact that if you take a rectangular matrix and you take all minors of fixed size, so here I say t plus 1 cross t plus 1 minus. So in general, there will be many such. You look at the ideal generated by them in the polynomial ring, then it is a prime ideal. This determinant is an irreducible is a very special case when t plus 1 equal to L equal to M, right? So that's actually something which came originally in the context of invariant theory, what's called second fundamental theorem of invariant theory. But so now if I kind of look at the locus cut out by these polynomial equations which are coming from minors of a fixed size of generic matrix, then that defines an algebraic variety called a determinantal variety. In fact, if you think about it, the FQ rational points of this, what are they? I mean, those are matrices with entries in FQ for which t plus 1 cross t plus 1 minus are all 0, which basically just means that matrices whose rank is at most t, because rank is at most t is just same thing as saying that t plus 1. So this is the locus or the variety cut out by them, at least in the affine case, is just a collection of matrices. But because these minors are homogeneous polynomials, I can also look at the corresponding projective algebraic variety, which just means that I forget the 0 vector and identify vectors which are proportional to each other, and I will denote it with a hat. So always d hat t will denote for me the projective object corresponding to, so I have, maybe I'll write it here. I have a, so this is X L cross M matrix, and I have this dt, which is matrices rank less than or equal to t. So that's sitting inside fq to the power lm. I have d hat t, which is the corresponding object in the projective space of dimension lm minus 1 over fq. Okay. If I have time, you can also sort of think of complementary objects, which are sometimes called open determinantal varieties, or these are not exactly algebraic varieties, but they are quasi-affine or quasi-projective, where you, instead of saying rank less equal t, you say rank strictly greater than t. Okay, so and the corresponding projective thing. Okay, so I hope the object is clear. How do you get a code out of that? You get a code out of that as follows. You look at the homogeneous polynomials in matrix variable of degree 1. Okay, and you just so let us suppose you have the cardinality of this set is n. So then you have matrices, n matrices, L cross M matrices whose rank is less than or equal to t, and so these are tuples of length lm. You take these polynomials in the matrix variable and you evaluate them at each of these matrices of rank less than or equal to t. Okay, so if there are n of them, I have this evaluation map, which is obviously a linear map of vector spaces, and therefore the image of that is going to be a linear subspace of fq to the power n. This is what I call a determinantal code. Actually, it's sort of an affine determinantal code. If you like, because I can look at this projective object where I take matrices up to proportionality and ignore the 0 matrix, and maybe the number is n hat, and I take their fixed representatives corresponding to the points of this projective space inside this determinantal variety, and I take a homogeneous linear polynomial in the matrix variable and evaluate it at that. Yeah, Lakshmi. Oh yeah, fqx1 is the space of all homogeneous linear polynomials. So fqx1 typically would look like set of all polynomials of the form, maybe say fij xij, I varying over appropriate parameters. So fij's are in fq. Okay, thanks. Okay. So here I use n. I will always use hat for the projective object, and this d hat t is what I call a determinantal code. Okay, and you can of course do it instead of evaluating at points of the determinantal varieties. You could take the open object and you will have some kind of an open determinantal code. And of course, determinant of a matrix is same as determinant of its transpose. I'll assume without loss of generality that my matrix L cross M is satisfies L less than or equal to M. And of course, when I'm taking minus of size t, I'll allow t to be at most L. Okay. I mean, rather rank less than, I mean, obviously rank is less than or equal to the minimum. Okay. So that's the assumption. So I hope the definition of the code is clear. Now let us try to understand the parameters. Okay. So let us suppose I just call this affine thing as C and the projective determinant code as C hat. If I know the length, dimension, minimum distance, or the spectral values AI for this code, or the corresponding ones for this code, the hatted ones, then they just determine each other. That's very easy to see because in this object you have extra 0 and you are adding non-zero scalar multiple of everything here. So the length is like that. Dimension remains the same. The minimum distance just gets multiplied by q minus 1. And the spectrum, if you know the spectrum of this one, you know the spectrum of this one, and vice versa. Okay. So here everything, all the sort of AI which will survive, which will have to be divisible by q minus 1, otherwise they are 0, and they are given by the corresponding value here. So you know these two things determine each other. So the problem that I'm interested in, okay, I have an interesting, nice or not, I don't know, a class of linear codes. What is the length? What is the dimension? What is the minimum distance? And if I'm a little bit ambitious, what is the weight distribution of the code? Okay, very good. So now let us try to understand what is the length. The length is going to be the points at which I evaluate. So let's see. So this is giving rise to the code that I call C or CDIT. It's the evaluation or okay, let me write the image of the evaluation map of linear homogeneous polynomial on fq to the power n. So just f going to f of m is in dt, and I have the c hat, which is where I evaluate at representatives of points of the projective things, image of that. Okay. So the length, yeah. Yes, we will see that. They are. So it's clear therefore that the length obviously is the number of matrices of rank less than or equal to t, just the cardinality of this set in the affine case, or the number of projective matrices of rank less than or equal to t. Question: of course, we all know how many non-singular matrices are there of a given size. Do you know a formula for the number of matrices of a given rank? That's the next natural question. Well, whether you know or not, this was known more than a century ago. So this is probably goes back to Landsberg in 1893, who showed that if you want to know how many matrices I have of size L cross M and rank J, then it is given by this formula, which I'm just going to denote by mu J Lm. So if I'm interested in the rank less than or equal to T, and I'm forgetting the zero matrix and doing up to proportionality, then I take this number divided by q minus 1 and add it up as the rank goes from 1 to t. Okay. If I'm interested in the length of this one, then I just take the sum of this as j goes from 0 to t. Okay. So length is known. Looks a little bit complicated, but you know it explicitly. You can write it down. You can also rewrite it using what is called the q binomial coefficient, which I have recalled here, or the q factorial notation, which I expect many of you would be familiar with. Okay, so that's as far as the length is concerned. What about the dimension? Okay, let's look at the examples as Lalita sort of asked. Suppose I take the special case when t is equal to L. So rank is less than or equal to L. It's an L cross M matrix, L less equal M. So rank less equal L is basically a set of all matrices. So I'm just evaluating at the points of all affine space. So if you think about it, this is this d hat t. The length will be the cardinality of the Lm dimensional projective space, which is this, and the dimension will be L times M, because that's the evaluation map is injective, and this has dimension Lm, and this is actually nothing but the simplex code. Okay, and therefore the minimum distance is q to the power Lm minus 1. So you also know the weight distribution. The simplex code is a constant weight code, right? On the other hand, the sort of next non-trivial example is, suppose I take a square matrix, L is equal to F, and T is 1 less than the size, which means T plus 1. So then the you know, rank less than or equal to T would mean basically that I'm forgetting the matrices which are of full rank. In other words, I'm taking from the space of all matrices the complement of the general linear group. Okay, so therefore the cardinality is length is easy to write down because you know how these things are. This is the cardinality of PL square minus 1, and you subtract the cardinality of GLF. And in this case, finding the minimum distance, what does it correspond to? So if you think about, so it's really one you know, non-vanishing of just a single determinantal polynomial. So it's like you are sitting inside PL square minus 1 dimensional projective space, and the vanishing of that is like a hypersurface. So if I restrict, so see, finding the, okay, how shall I say this? Finding the minimum distance exactly corresponds to maximizing the number of points on the hyperplane section of this variety. Because you know, if you think about it, what is this? I mean, how do you calculate the minimum distance? You want to know where f is not equal to 0. So this is like a linear form in the matrix variable that defines a hyperplane. So you are cutting this determinantal variety by a hyperplane, and you want to minimize the number of zeros, non-zeros. That means you want to maximize the number of zeros. So you want to maximize the number of zeros which are on a hyperplane and which also lie on the determinantal variety. So so hyperplane inside PL square minus 1 is like projective space of dimension L square minus 2. By the way, Sir, who was there at the conference where we met in Lumini many years ago, he proved a beautiful inequality about the maximum number of points that can lie on a hyperplane in a projective space. Okay, that if you sort of translate that bound to this situation, because this determinantal x equal to 0 is a hyperplane, it translates to this, which of course gives you a bound on the minimum distance, except that in this case the bound is pretty crude. It is almost never met except in a very special case when I take 2 by 2 matrices and t equal to 1. Okay, so there the minimum distance is q square. So Serre bound is great, but that is usually for hypersurfaces which are highly reducible. For this kind of irreducible hypersurfaces, usually there will be a tighter bound. Okay, all right. So, so naturally, you know, when you sort of think about a problem, you first try. Let's you know, Peter, Sartaj, and I, we made this simple observation that my code words are going to correspond to a hyperplane like this, or some linear polynomial in the matrix variable. F is summation Fij Xij. Okay. Now, so the code words are parameterized also by hyperplane or by linear polynomial, and that themselves correspond to a L cross M matrix, namely the coefficient of that linear polynomial. So let's say capital F is the coefficient matrix of this linear homogeneous polynomial. Then it turns out that the Hamming weights of this code word depend not really on the matrix F, capital F, but just on the rank of it. Okay, so that sort of elementary linear algebra will in fact show that they are completely determined by the rank. Okay, so then what I do is, when I'm given a L cross M matrix and I want to find a matrix of rancor, I like the simplest possible matrix of rancor. What is the simplest possible matrix? I have an identity R cross R in the left top corner and 0 everywhere else. That has rancor. You know, any sort of matrix of rancor is actually equivalent to that. So that means, and when I look at the corresponding homogeneous polynomial, that would be like x11 plus x22 plus xr. In other words, some kind of a partial trace. So the weights are basically the Hamming weights of these partial traces. Okay, so that's a little lemma that we proved, and so what that tells you is that obviously this R will go from 0 to L. So the positive weights are W0 to WL for the affine thing, or for the determinantal code, W hat 0 to W hat L. Okay. And once you know, if you somehow know what these weights are, then it's easy to find how many code words have that weight. Because I just have to find how many matrices capital F I have of size L cross M whose rank is R. But that's given to me by Landsberg. That is the function mu R. Okay. So once you know, so you knowing the weights here actually gives you the spectrum also because of this Landsberg formula. Okay, so I hope that is clear. So we have the weights for these, which I am now calling W0, W1, WL, and for W hat 0 to W hat L. Very good. I started at 12:15, no? Okay, 6, no? Okay, all right. Okay, so the first result that we proved, this is with Peter and Sartaj, is that suppose you look at the case variety given by vanishing of 2 cross 2 minors, which means matrices of rank less than or equal to 1. Then this W hat 1 to W hat L are given by a very nice formula, which is Q to the W hat R is Q to the L plus M minus 2 plus Q to the L plus M minus 3, and going down to L plus M minus R minus 1. So here R goes from 1 to L. So it's obvious that the minimum distance would be the one corresponding to R equal to 1, which is Q to the L plus M minus 2, and all these W's are distinct, etc. For those of you who know about determinantal variety would recognize this object as the dimension of the corresponding determinantal variety. And so this kind of shows that the minimum distance is asymptotically like the length for Q large. Okay, but of course the rate is bad. Okay. Now, what about the general case? So we were thinking about this and we actually found some formulas, except that as it so happens when you're dealing with classical objects, we realized that some formula was already known in a completely different context. So, so Delsart in 1978 wrote a paper which is now very famous, especially for those who do rank metric codes, where he was looking at the association scheme corresponding to bilinear forms, and he gave a he determined the characters of what is called the Schur ring, and he showed that this fracture WR. What is the fracture WR? This, roughly speaking, correspond to rank is equal to R or rank is equal to T. So the usual weights will be the sum of this factor WR, where at S at Lm, where S goes from 1 to T. Okay. So he sort of found a formula for that in the context of this association scheme of bilinear forms. Okay, and it turns out that Alberto Ramnani, who is now in Eindhoven, he has given an alternative approach to Delsart's formula using, not surprisingly, McWilliams identity for rank metric codes. Okay, so but now you look at this formula, or you can look at Ramnani's formula, which is this. I'm not going to read it out. Peter and I also found some other formulas which look like this. So these formulas are beautiful or horrible depending on your viewpoint. But you look at any one of them, Delsart's one or this Alberto's one or ours, and it is not at all clear, for example, if W1 to WR are distinct or how they are ordered, right? So, and so in particular, you know the weights, but you don't even know what is the minimum distance, okay? So Delsart didn't bother about that, and it's really not clear from these formulas. So, and that's where I think our formula has some advantage, because later on, so that's what I was saying. It's not obvious if the possible weights that are given by these formulas are distinct, which one is the least, and in general we would like to know, I have these formulas, how they are ordered, which is the least, which is the next one, which is the next one, and so on. Okay, in the simple case when t is equal to 1, that was the older work I presented to you, they were very nicely ordered. But the other extreme case t equal to L, that's a simplex code, and there they're actually all the same because it's a constant weight code. Okay, so that was a bit of a mystery to us. We kept thinking about this. So first Peter and I, we proved that the first one is always the minimum distance by showing the difference between rth one and the first one is given by some positive quantity which counts something, which is some kind of a fracture for a smaller matrix. Okay, in particular, the minimum distance is then given by this formula here. Okay, so that gave us the minimum distance. And as far as the other questions are concerned, whether they are distinct, how they are ordered, we were not at all clear. But we did some experiments and we ended up sort of making this conjecture which said that all the weights W1 to WL with or without hat, they're actually distinct, and they're ordered in the following way. They are strictly increasing up to L minus T plus 1. So if T is equal to 1, they are increasing all the way. But if T is equal to L, then this tells you nothing. Whereas after this L minus T plus 1, by the way, I'm sort of, for simplicity, I'm assuming T is strictly smaller than L. T equal to L is the case of simplex code. There is a very interesting phenomena which occurs, which is called interlacing, which is that the next one is between the previous two, the one after that is between the previous two, and so on. Okay, so you call it sort of a three-part conjecture: distinctness, partial monotonicity, and interlacing. I think the main result of my talk, I have 2 minutes, is okay. So I'll come to that. So this Mahir, he was interested in some other class of codes called grassman codes and flat codes, and he was visiting me, and he told me that he had looked at linear codes associated to the general linear group. Okay, so which are basically given by evaluations of homogeneous linear polynomials in matrix variable at the points of general linear group where the determinant is non-zero, and he calculated the length, the dimension, and the minimum distance. And I kind of recognize, and what was interesting was that so here also one has to analyze the vanishing of these partial traces inside the general linear group, those matrices for which this partial trace is 0. And so you get this some function fr, and turns out that the minimum distance corresponds to r equal to 2, whereas the maximum distance corresponds to r is equal to 1. Okay, because maximizing this corresponds to the minimum distance. So that was something funny, but I realized that this is of course related to the open code, and we could sort of put the two things together. Eventually, what we were able to prove is to prove that this conjecture that Peter and I made is actually true in full generality. So indeed, these weights are distinct, they are partially monotonic, rather fascinating interlacing phenomena. Okay, I should say that you can, because of the way these W's are related, whatever I have said for this W hat is also true for the fracture WR, which you might call the Delsart weight, because of the relation that you have between the difference between two consecutive weights related to difference between two consecutive Delsart weight for smaller parameters. And of course, if you have this and this, then distinctness would follow. It would also follow that this is the minimum weight and this is the maximum weight. Okay. Not only that, you can so this is, as I was saying, and so you actually recover the results of Mayer-Belenjan as a consequence of this. In fact, much more general, because you kind of complement things, and then that would explain, because this T equal to L minus 1 corresponds to the case of the determinantal thing, sorry, general linear thing. So there it is 2, and so on. So you can get the complete weight distribution also of open determinantal code. So I think my time is up, sorry. So I just want to say that happy birthday, Vijay, and thank you. There's a remark that this is connected to a lot of interesting mathematics, but maybe some other time. Thank you. I know this is a little early in the day, but here is a toast to you. You probably recognize that picture less than 2 years ago in Hyderabad. Okay. Thank you. Yeah, Vijay. You tell me. I mean, I like to think, well, see, as I sort of said, so let me say a few more things. So you know the minimum distance, and the minimum distance is roughly asymptotically of the order of the length. So in terms of the distance or the relative distance, they are good codes. But the rate is bad. Okay, unless Q is small. Okay, like Reed-Miller code or Grassmann codes, etc. Another good thing about them is that you can calculate the dual minimum distance, and that's very low. That's 3. kind of like LDPC. So, and you also know some of the generalized Hamming weights, though not all of them. But what we thought was remarkable was you have a pretty general class of codes and you are able to tell the complete weight distribution. So that was something which was interesting, and it ties up with a lot of classical mathematics, which always fascinates me. Thanks.
Next speaker is Prasad. Prasad Krishnan. He's going to talk about shotgun sequencing, information theoretic limits for shotgun sequence.
Okay, so I see that lunch is already served, so maybe I'll get started. So thanks a lot for this invitation to Lalita and other organizers. The last time I was here, I was a PhD student working with Professor Sundarajan. So it's like multiple levels of sweetness to come back here, and it's kind of reunion with so many of people with whom I overlapped with. And of course, the occasion being Professor Vijay Kumar's anniversary. So at various points of time, we have all benefited from his various suggestions and advice, mentorship of various kinds. So I hope, and selfishly hope that that continues for a very long time. So thanks a lot, sir. Congratulations. Okay, so talk is going to be on some kind of an information theoretic analysis of what is known as the shotgun sequencing channel that arises in the context of DNA sequencing. Doesn't seem to work. Okay. Yeah. Okay, so this is joint work with Hrishi, who was a student, a dual degree student at IIIT, currently a doctoral candidate at TUM. Isan, who is currently a BTech honor student at IIIT, and Professor Neeta Parekh, who is at the Computational Natural Sciences Department at IIIT. Okay, so the short outline of my talk. Firstly, I'll look at some literature which talks about the shotgun sequencing channel in the context of DNA data storage, and the capacity of this channel was recently identified. I'll present that. Then we'll move on to our model for the shotgun sequencing channel with erasures. Present what our results are on the capacity. We have bounds, both upper and lower bounds. And then very short proof sketches, which will give a very high level overview of the proofs, and then we'll conclude my talk. Okay, so as many of you will know, DNA is essentially a long molecule which consists of four sort of characters or compounds which are composed of this characters A, T, G, and C. The idea of using this as a DNA as a storage mechanism arose in the last few decades, and people have been trying to actually come up with systems, analyze the theory, etc. So the motivation is that somehow we could use this as a storage medium for archival data storage because of its high stability and also data density. You can store a lot of data within a small volume. Okay. So whenever you have a system like this, we want to sort of think about how much you can store per unit base, and that's where information theory comes into the picture. So the process of reading data, which is or just a sequence which is already available, is fairly complicated. So there is some chemistry involved in it, some algorithms involved in the whole process. So if you have the original DNA here, the process of reading this data is essentially to send it through what is known as a sequencer. Okay. So in the DNA sequencing mechanism, just specifically this mechanism known as the shotgun sequencing is one of the kind of sequencers which are available. So what happens is this whole sequence gets broken up into various strands, and these strands have some overlaps between them. So these are, think of the original DNA as a long string. So these strands, which are known as reads, the substrings, these are all substrings of the original string, and they have some overlaps between them. Okay. So what we want to do is to, this is the output of the sequencer, and then you pass this through these reads through an algorithm which tries to align these reads together to stitch back the original sequence. Okay. So this is essentially going to be modeled as a channel. This was done by other people. So we have this original string which is denoted by X here. It's an n-length string. So when it passes through the shortband sequencing channel, you get some k reads, each of very short length, which is L, compared to the original string. And the goal is to somehow reconstruct the original string back from these collection of reads. The assumption made for the sake of tractability is that these k reads are sampled from the original string at various random locations. Okay. And the length of each read is assumed to be some constant times log n, where n is the length of the original string. Okay. Way back in 1988, Lander and Waterman did a very basic analysis of how many bits can be covered when you go through this reading process, the sequencing process. And the information theoretic analysis for the case when X takes values from uniformly at random from the set of all n-length sequences was done by Motahari and others in 2013, and they obtained some essential fundamental information theoretic limits on what the values of L bar, K, etc. could be. Now in the coded case, instead of picking X uniformly at random from the set of all possible sequences, we are looking at the application where this is going to be used as a medium for storage. So what we want to do is to pick X from a code instead of the set of all possible sequences. And this was considered by Ravi and others in this paper. The capacity of this channel was exactly characterized using various ideas. Code design for this channel or some version of this channel was already available by Kia and Ravi and their groups. So this is known in the literature. This is essential papers that if you want to learn about this area, you should kind of read this. Okay, so what is the capacity characterization given by Ravi and others for the shortband sequencing channel? So the capacity is characterized using the two quantities. The first quantity is C, and the other quantity is L bar. L bar we already know. L bar is the normalized length of each read, normalized by log n. And C here is characterizing how many reads you have. So essentially K, the number of reads, looks like C into n by L. So C is K into L by n. K into L is the total length of across all the reads, and n is the length of the original sequence. So essentially this C parameter is known as the coverage depth, which characterizes how many times a single bit or a single symbol in the original string appears in the reads. Okay. So the expression for the capacity looks like this, and as you can see, if the value of C increases, the number of reads increases, this becomes large. Similarly, if the value of L bar, which is the length of the read, increases, this becomes large. Okay. And further, if the value of L bar is smaller than 1, it's shown that the capacity of this channel is 0. So you need read lengths to be at least log n. Okay, so an interpretation of the, when you do the proof, there is an interpretation that comes up in the course of the proof. That is that this capacity expression essentially looks like the difference between two quantities. The first quantity being what is known as the coverage contribution. That is the total number of bits that are covered by the reads. And the second contribution, which is subtracted from the coverage contribution, is the cost which is involved when you want to put these reads together to form the original sequence. Okay. So because you lose the ordering when you get the reads are not ordered between themselves. So if you want to reconstruct the original sequence, you essentially have to order them, then align them together. Okay, so the capacity of this particular channel was obtained using what is known as related channel. This is known as the Tarn paper channel, again mostly done by the same authors. Okay, so this is the essential literature which is available for this area. Now we move on to our model for the sequencing channel with relations. Okay, so when the sequencing process goes on, so we don't just obtain the reads, we also obtain the quality scores which are associated with each base which is present in the reads. So the reads are essentially substrings of the original string. So if you think of the DNA, you have every read looks like some subsequence of the original sequence. So there are bases which are present at each position, and the sequencer also, apart from sending the base out, it also sends what is the confidence value with which this base is predicted. Okay. And if that confidence value is very large, then we can assume that that position is essentially erased, And that is what really happens when you want to realign the reads back. So we assume that there are some positions, we don't know what the exact base is. So, and then we'll try to do an alignment algorithm to reconstruct back the original sequence. Okay, so this is our model then, therefore. So what you have is the original sequence. Assume that this passes through a noiseless channel. You get all the k reads, but then these reads are sent through a binary erasure channel, and this is the real output of the noisy sequence. Okay. So the real output has k reads once again, but some positions in the reads are erased. Okay, so the next two slides shows what we have as the results. Yeah. That's not always the case. Yeah. Yeah, and so for simplicity, I'm assuming that it's like a binary string. Yeah. Okay, so we show that the capacity of this shortened sequencing channel with erasure probability delta is upper bounded, lower bounded by this quantity here, which is a function of C and L bar as before, and apart from that, this value of delta also. Okay. As a special case, when delta equal to 0, you can recover the capacity of the shortened sequencing channel without erasures. The converse result which we have again is a function of the quantities C and L bar, but apart from that, what you have is 1 minus delta E term here. Here this delta E term is related to the parameter C and delta by this expression here, and what this delta E captures is the probability that a particular bit of the original sequence is erased in all of the reads, across all the reads. So it's not available in any one of the reads. That probability is given by delta E, and that appears in the converse expression in the case of the read length being at least so much. If the read length is smaller, just like what we had in the case of the shortened sequencing channel without erasures, we have that the capacity is 0. Okay. So these are the essential results, and the curve for these results looks like this. So we have on the x-axis the coverage depth C, and we look at the rate achieved as well as the converse bounds on the y-axis. So the achievable rates are given here by the dotted lines, the converse bounds are the bolded lines, and we do this for various values of delta. Okay. And as you can see that there is always a gap, so our converse is not tight, and this is the current state of the art. Okay, so we'll move on to the proof sketch for the achievability. The coding argument follows arguments which are present in the original paper. So essentially, we have not innovated much on the techniques, but in computation wise, we have some innovations. Okay. So it's a random coding based argument with typicality based decoder. And as the random coding goes, you have messages chosen from this set of n2 power nr messages for a code of rate r, and the code word here is chosen from some random code. So what does the decoder have now? The decoder has the collection of reads, and what it wants to do is to basically estimate the message W which was transmitted. So the output of the decoder is going to be the estimate W cap, or it will declare some failure. Okay. And the decoder proceeds in 3 phases. These phases, so as we mentioned before, we want to get back the original sequence, we have to sort of merge the reads back to get the original sequence. So that's the first phase. Then there is the filtering phase and the compatibility check phase, which I will shortly describe. Okay, so to describe the decoder fully, what we need to do is to first understand what happens when the decoder is trying to merge. So the merge process by the decoder is characterized by 3 quantities here. So first you need an ordering, a specific ordering of the reads. So you have k reads, you need to put them in a specific order. Then every adjacent read in that order will be tried to merge together. So in that order, let's say that U was a predecessor read and V was a successor read. And further, apart from the ordering, we also have to specify how much we want to merge, because a read could be overlapping in different zones. So we want to therefore specify how much we want to merge, and that is given by this merge suffix size, which essentially describes what is the part of the predecessor, how many unerased bits are there in the predecessor read, which have to be present when you are trying to do the merge. Okay. So in this case here, there are 2 bits which are unerased in the predecessor read, and you want to try to merge together with this other read. And if a merge should be successful, what we need is that if there is an unerased bit in both the predecessor and the successor read, they have to be identical. Okay. If they are not identical, we can't merge them together. Now, in the case that, in the erasure case, we have that some erasures could be present in both of the reads. So, if there is an erasure present in both our reads at the same position, then we see that there is an erasure after merging. If there is an erasure present only in one of them, but in the other read the bit was present, so we retain whatever that bit was. So, essentially when you are trying to merge, the merged sequence has a little bit potentially more information than the original reads. Okay, so once we specify a certain ordering and a certain set of ways to merge these reads together, the merging suffix sizes, the decoder will attempt to do the merge, and it will end up with what are known as islands, which are essentially maximally merged subsequences. So you merge until you can't merge anymore, and that results in these contiguous portions. Okay. So we also call somewhere in this talk, you will see the term true islands getting used. The true islands are when you have the original reads, suppose you knew the exact sequence they occurred, and you also knew the exact merge sizes, and then the decoder is trying to merge them, whatever results, that's called the set of true islands. Okay, so with this background, we can now describe what the decoder, the complete decoder chain looks like. So you have this collection of reads. In the merging phase, we have to specify some good orderings. So we'll try to specify some orderings based on some typicality constraints, and we will see what those constraints are. So for each such ordering and each such like a typical ordering and typical overlapping suffixes, we will have a set of islands. So we'll collect these set of islands together and check whether each of these set of islands satisfies some further typicality constraint which is on the coverage, that is the number of unerased bits which these islands have. If this is satisfying it, then we will continue to work with those islands, call it as a candidate island. If it is not satisfying this coverage constraint, we will throw away that islands and say that's not good enough. So this is the merge and the filtering phase. So when we come to the compatibility check phase, we will have a collection of all possible candidate islands, and we will take each one of them and look at all the code words which are compatible with these islands. So what we mean by that is that the island is representing, each island is representing some subsequence of some code word. If all the islands in the island set are subsequence of a certain code word, then that code word is like a valid code word to look at. Okay, and we will collect all these collection of code words in this set called xcap. Okay. And the final step is if xcap, which is a collection of all valid code words from the decoder, if that set size is, if the size of the set is 1, then we will have a decoded estimate. If the set is of size 0 or greater than 1, then we will say that there's a decoding failure. Okay, so this is the whole chain for the decoder. Okay, so we mentioned that there are some typicality constraints in the various phases. So we'll see what they are. The first constraint in the merge phase is that this quantity called count of tau should be close to the expectation, where tau takes value from 0 to L bar. What this count of tau is representing is the number of times the merges, that is the merge suffix sizes, are of size tau log n. So we will pick only those orderings and those particular collection of merge sizes for which this is true. So that is what the decoder will start to do the merge process with. In the filtering phase, the typical constraint to be checked is in terms of the coverage. So the coverage represents the number of unerased bits in the set of islands which are present in I. So we will keep only those set of islands in the candidate island set for further processing, which satisfy this constraint that the total coverage should be approximately close to the expectation. And we can calculate these values by just simple analysis. Okay. The expected values of the count, the expected value of the coverage, we can calculate. Okay, so now at this point we have got the set of all good island sets. and then which will result after the compatibility check. We will have this set xcap, which is a set of all code words which are compatible with at least one island in the set of candidate islands. So an error in this scenario can occur in two different ways. First way is that the true code word is not present in xcap. The other way is that code words apart from the true code word are present in xcap. So the rest of the analysis is a bit intricate, and essentially we show that the probability of these two error events go to 0 as long as the rate is smaller than this quantity, provided these constraints are true, that the number of true islands, the total coverage of the true islands and the true merge suffix size counts are close to their expectation, and these events will happen with very high probability. So therefore the decoder will succeed with very high probability as long as the rate is smaller than this. And this gives our achievability result. Okay. So moving on to the converse. The converse had two parts, if you remember. The first part said that if the length of the reads is smaller than a certain quantity, then the capacity is 0. And I'm not showing a sketch for that. Essential, simple reason is that the short length of the reads creates a lot of reads which are identical to each other. So therefore, essentially by looking at the reads, you can't really put them together to get the original sequence. And that's essentially why it fails. The reads don't have enough information about the original sequence. Okay. So now in the case that the reads have a length which is greater than this small number, we use a Gini based argument to give the converse. The Gini essentially is there with the decoder, and it says it gives the information of the true ordering and the true set of read overlaps. Okay. So we assume that the decoder knows this, and therefore the decoder can reconstruct back the true islands. The true islands can be obtained back, and we will denote the set of true islands by this script y island. A script y is a set of reads, script y island represents the set of all true islands. That is the ground truth. Okay. So then what we can show is that the first step of the converse, we can show that the capacity is going to be upper bounded by this quantity here, which is the mutual information between the input sequence and the collection of true islands. Okay. Instead of the reads, now we have the true islands. In the second step, we partition the collection of true islands based on their various lengths. We split them up into a collection, and we show that when we choose the parameters appropriately, we can bound each one of the terms asymptotically. Okay. The final expression takes this familiar kind of expression here, which is that you have these two terms here, the coverage term and the reordering cost term. So we have a bound on the upper bound on the coverage term and the reordering cost term, and the difference between the two gives us the converse. Okay, just to elaborate a little bit, so we start with this, the mutual information between the reads and the input sequence. Then you just introduce the collection of islands. So this is sort of given by the Gini. And then when you split this mutual information by the chain rule, you see that you have this other term here, which is a conditional mutual information between the set of reads and the islands, set of reads and the input sequence given the set of all islands. So once you are given the set of all islands, essentially knowing the reads does not buy you anything, because you have already sort of merged them together and you have extracted the maximum amount of information you can from the reads, and therefore this term goes to 0, and what you end up with is this. So this is step 1. In step 2, as I mentioned, we split up the set of islands into various groups based on this parameter k, which is giving you a sort of a bound on the length of each island in that group. And go through the steps once again. You find that basically just the chain rule again. So essentially you see that you have this expression here, which is an upper bound on the rate of any code. So here in the first term here you have a summation k equal to 1 to j minus 1. So j is just an arbitrary parameter we have entered here. And in the second term here we have all the islands which are of length greater than or equal to j. And the last term here is coming because of the mutual information, split into the original entropies and the conditional entropy. and for a very careful choice of this parameter j, you can essentially show that the second term here goes to 0. So that is islands of much larger lengths don't matter anymore, and the other two expressions can be bounded effectively, giving us the converse. Okay. So essentially what we end up is this kind of expression. So the bunch of intermediate steps I'm just skipping. So what you see here is that the rate is a difference of two terms. The first term is the total length of the expected total length of all the islands. So this is the number of bits which are present across all the islands, and when you multiply it out with this term 1 minus delta e, that represents the number of unerased bits arising out of all the islands. So that's like a coverage term. The second term here is expected number of islands multiplied by log n, which is like a reordering cost. So you have all the islands, so if you want to put them back together, then you need sort of an indexing of log n bits per island, and that you need to spend just for reordering it and putting it back. So that represents a reordering cost. These quantities here, the expected sum of all the islands, the total coverage term, and the expected number of true islands, there is some simple probability calculations you can do to arrive at some expressions, and this boils down into our converse expression. Okay, so to conclude, so what we showed is a random coding argument for obtaining the achievable rate for this channel with the erasures, and we also proved a loose converse for the same channel. Future work includes proving stronger converse bounds. So we have some results which at least recovers the case for the delta equal to 0 scenario. Capacity under other error models. So in the context of DNA sequencing, there are also other errors, including substitution errors, insertion errors, deletion errors, which we have not considered. So one could consider them potentially and get capacity bounds. And finally, low complexity coding schemes. Apart from the 2 or 3 works which I mentioned before, it's kind of open. It's a hard channel to work with, so it's hard to come up with schemes which will actually give rates close to the capacity. So that's a challenging problem. Okay. So if you are interested in the longer versions of this work, these are available in these archive papers. Thanks a lot. That plot did show this. Yeah, the converse is loose, possibly. Yeah. Here. So the bold one, the bold red and the dotted this thing. So we are currently able to close the gap at least for the delta equal to 0 case. So we have a better converse, but that's not written up here.
Connection with the picture or? I'll talk about it. Vijay, you're trying to identify the image. You can check your WhatsApp. I sent it to you on WhatsApp.
One on the right, yeah, it's I think humpy. Missing a lot of marks. So I've given this talk in many places. I think many people have seen it. The only change I think is this image. So that much, no, there's a little bit more changing also. At least this image is changing.
Okay, welcome to the third session of the day. This is Professor Andrew Tangaraj, who will be presenting on missing mass for Markov samples and problems in distributed estimation.
Thank you. Thanks a lot for this invitation. It's an absolute honor to talk in honor of Vijay. I've known Vijay for a couple of decades, more than that now. Mostly our interaction, I think, has been like that. In some conference over a glass of wine. So it's been a very, very happy interaction with him. At one point, we did try to work together, but unfortunately, I don't think I have a single publication with him. So that's one thing which maybe we could have fixed at some point. So this talk is about missing mass, and I guess this picture sort of tells you what we're going to try to do. So there's lots of mass missing on the picture on the right, and based on what you can see, you maybe in your mind can visualize what the missing part could have been. So we'll try and do something like that statistically, right? So statistically, we're going to observe something. Of course, in a situation where you're likely to miss a lot, can you statistically infer what could have been missing? What is possible is the question that we'll address. There are three parts to it. I'll begin with the IID version of this problem, which is quite an old one, and then the Markov version, it's a little bit recent, and then some pointers to how this might inform distribution estimation, particularly in the large alphabet case, which seems to be very relevant and interesting today. Okay. So this is a talk on min-max estimation. I know there's a lot of coding information theorists there. Maybe you've not seen this formalism a little bit. It's sort of related to information theory and all that in a fundamental way, but just to make sure that we are on the same page, I'm going to look at n samples from some distribution. And the parameter I will look at, typically the parameters we see in the communication context are functions of the distribution. So the parameter I will look at loosely, parameter within quotes, also depends on the actual samples. Okay, so it's a slight generalization there. And we'll look at estimators. Of course, estimators will depend only on the samples. And metric is going to be the squared error risk. You can look at other things, but this happens to be the easiest and most tractable in this particular case. In particular, given that it's a statistical problem, quite often you don't trust the model too much. So you want to look at worst case risk, as in max over the distribution, all distributions, the expected value. So this sort of maybe makes you robust over any distribution that it might have been. So this worst case risk is an important metric in this area. In particular, then you want to look at that estimator which is going to minimize your worst case risk. So that's where the min-max comes from, and this is called the min-max rate. And you can imagine this depends only on n, right, in some sense. So, and how it falls with n is a fundamental characterization of the problem itself. Right? So typically you may get 1 by n, 1 by root n, 1 by n part 2 by 3, whatever. So you want to figure out what that min-max rate will be. As you can imagine, in most problems, this might be a difficult thing to exactly characterize. So you can do an upper bound or a lower bound. Of course, there's a minimax optimal estimator that achieves the min-max rate. Upper bound is reasonably easy to see from that expression. You drop the min, right? You pick some estimator. If you manage to find its worst case risk, that's an upper bound. Naturally, lower bounds are a little bit trickier. But even lower bound, one way to think of it is you replace the max with an average, you will get a lower bound. But then you have to solve that min over theta hat, and that will come from the Bayesian ideas. For instance, in this particular case, the conditional expectation would solve that. So you can do something that's the prior method for the lower bound. You can also do other reductions, in particular the reduction to hypothesis testing. Instead of actually finding the parameter, you take two hypothesis parameters in this set. You can do that. That's LeCam, there's FANU, there's lots of other methods for lower bound. Okay, so this is the setting. My talk will be in the min-max setting. Okay, so now let's look at the missing mass problem in particular. So you have n samples. They maybe come from a large alphabet, from some distribution. Typically, you don't want to assume distribution and alphabet are known. So this is a large alphabet scenario, and I'm going to be interested in the distribution, but the part of the distribution corresponding to the letters that I did not see. Okay, this seems a little bit counterintuitive. As it is, figuring out something from what you saw is a bit hard. Now we are asking for an inference or a learning about something you did not see, right? So it's not even apparent that it's even possible, right? So it looks like, what am I cooking up here? It's not possible. But of course, the LLMs today do such low probability stuff, so maybe this also is possible, right? So we can believe such things. Here is a typical scenario, right? You look at Tale of Two Cities, which for the Gen Z audience, it's a very classic novel that people actually read. It has a lot of words, and there are 10,500 unique words. The probability of them vary over a wide range, 10 power minus 6 to 0.06. Supposing you pick that distribution, so this is a large distribution, but I'm going to take only 1,000 samples, right? So clearly a lot of the words will be missing. Right? So this is a picture of the actual PMF. I've of course sequenced them in increasing probability to give a better idea. But I want you to focus on the range of the y-axis, right? It's a huge range. Now, if I look at these 1,000 IID samples and ask which I did not see, you can imagine the higher ones I would see, and then a whole bunch of lower ones I wouldn't see. So that's what I didn't see. And then, I mean, it looks quite like a weird problem. Why would I want to know so much about all this? Can I even know anything at all? But then you look at things that you saw exactly once, then you get this kind of a picture. Right? So you see, what you saw exactly once seems to also spread out over that whole range. I'm not sure the colors are coming out in good contrast, but you can see that what you saw once is spreading out in that whole range. Yeah. No, this is not English language. This is from Tale of Two Cities. Just that. No. So I would take a word, I will divide its frequency by that big number, 136092. That's the, in the sample. Yeah. Yeah, yeah. No. Only there. This is my corpus. This is my language, so to speak. Okay. So this is scene once. You can do scene twice, and slowly you can see that scene one didn't quite concentrate too much, but you can see scene two starts to concentrate a little bit more. Greater than 2, in fact, will be the blue ones, and you can see those are much closer in range. And the question you ask is, can I infer anything at all about this vast thing that I did not see based on what I saw? And I want to have results universal over the alphabet and the pi. So that's also very important, because I don't want to do it for a particular alphabet, particular distribution, worst case over all possible sort of things. So this is the grand problem of missing mass. Like I mentioned, it's an old problem. You can put it into a nice framework. In that notation, you see that missing mass is summation over x, pi x times the indicator that x did not show up in xn. Okay, it's a standard one. Like I said, this parameter, so to speak, depends both on pi and xn. Right? So it varies from sampling to sampling. So, I mean, we are in the large alphabet context, like I showed you last time. So missing mass can be sizable, even though individual pi x might be small. So this is an old problem. Like I said, it was looked at very closely by Good and Turing while they were cracking Enigma, and Good had a publication out of it in 1954 where he described this estimator. They came up with an amazingly simple estimator for estimating the total missing mass. Okay, so you can see this is summation, right? You sum over all the letters that you did not see, what the probability is, and their estimator was so ridiculously simple, right? So what it was, you just count the number of singletons in your samples, divide by the number of samples, and that was put out as an estimator for the total missing mass. Okay, so there's a notation here, this phi, it will show up a little bit in my talk. I will in general call phi k as the prevalences. These are the number of symbols that appear exactly k times in your sample. Okay, so this is the good Turing estimator. It's an old one, and quite a bit is known about this estimator. So looking at it, you would think, I mean, what is the chance that an estimator like this can actually estimate missing mass over all distributions, all alphabet, right? The first time I saw it, I didn't believe it at all. I wrote a little script and I simulated the heck out of it. It was really working very well. And of course it works well because there is a wonderful proof. It's a very delightful little proof to show that the bias universally is low for this estimator over any alphabet and any pi. Okay, it's less than 1 by n. I'm not going to go through the details. You can see ultimately it boils down to an expression like this versus an expression like this, and the difference is just in this guy here, and that's not too high. Okay, so whatever your pi may be, that goes very soon. So it's a very delightful little proof showing that this estimator has low bias. Of course, you can do more. You can also show variance is low. You can have universal consistency in terms of the mean square error. So whatever may be your distribution of pi, the mean square error is upper bounded by 1 by n. This from the paper 2000, and recently it's also been the min-max with the lower bound has been also established as 1 by n. A lot of people have looked at concentration. As you can imagine, these quantities have to concentrate if we are going to be able to estimate them in a reasonable way, and that also has been looked at. So many other papers have looked at variations on this. So one thing I want to point out is, if you change your error to relative, if you divide by the m pi, then you can show you cannot estimate it. Okay, but then the argument that I make against it is, you don't want to be in that relative space where your missing mass is so low. In those cases, you're not really interested in estimating missing mass. It's only in the cases where it's high you're interested. So it's okay. It's okay to look at MSE as well. So this is IID samples. Of course, the interest in applications, you can see the wide range of applications, and always the large alphabet shows up, but equally well, you see samples are not necessarily IID. So people have used good Turing in the context of language models, for instance, but clearly language models, the words are not IID, but even there they use good Turing in the same format. So clearly one of the interesting extensions is to look at Markov, and here is a one slide introduction to Markov chains and mixing. Maybe this is familiar to most people here. I'll quickly talk about it. In particular, I want to talk about the sticky chain. This is very important in my context here. This is a sticky chain on 4 states. You can see what's happening. It tends to stick to that same state with a pretty high probability p, and of course there's a q by n to balance it all out. And then any transition is actually uniform over all the alphabets, and that's what happens. So you can see how the transition goes. So it tends to stick to it with a very high probability and jumps out to anything else with q by n. Okay, so this is an example of a Markov chain that we'll be interested in. This is for n equals 4. You can do it for any other n, right? So you go to a larger n, this will just become larger. So this is the sticky chain. This is the transition matrix. Of course, many things I'm going to say are true for general Markov chains on finite alphabets, but this particular chain is interesting to me. You have the evolution of the state distribution. State at any time t is the initial state time p power t, and then there's a stationary distribution which fixes itself under the evolution. Now the critical property for us is mixing. Mixing meaning whatever initial probability you start with, you can see this is one such simulation, it quickly goes to the pi. Okay, and this you can prove, and that's where the mixing comes from. There's a definition of mixing. The mixing definition we saw earlier, the definition of the total variation distance. The mixing usually is in terms of total variation distance. You start at any state. Okay, I've done the unit states here, but this can go to anything. You start at any state, you do the state at time t, subtracted from pi, total variation is less than or equal to epsilon. How quickly you can get there, that's your t-mix, right? So this is the definition. Usually you pick your epsilon to be 1 by 4. The reason is any other epsilon varies only by log 1 by epsilon. So it's not too bad, so you can pick it as 1 by 4 here. So this is picked as the mixing. Okay, so what is our goal now? See, if the Markov chain doesn't mix, maybe you might think it's very little hope of being able to find the missing mass. That's generally true. We'll show that it's also true. But among the Markov chains that mix, let's say they mix with mixing time t, can we get a universal characterization of how well missing mass can be estimated? Will good Turing work? Does it need to be modified? Okay, so that's the main question that we will ask in the Markov part of the presentation. Okay, so it turns out the vanilla good Turing fails on sticky chains. So that's why I introduced the sticky chain in the first place. You can imagine why, right? Good Turing is counting singletons divided by n. If you're going to stick to the same thing with one non-zero big constant probability, everything you see, you'll see multiple times. So all the time, your good Turing will say 0 as missing mass, while you can increase the alphabet size to how much ever you want and get the missing mass to be very high. So that's the essential problem here. And you can see in the simulation that comes out, the IID falls like that, but then it starts flattening out. But notice I'm going large alphabet, right? So the number of states is scaling with n. Okay, so that's the sort of the large alphabet scaling that people look at in these scenarios. Okay, so this goes wrong. You can prove it. I'm not going to look at it. So a couple of students of mine showed a few years ago that you can do a modified LECAM and come up with a lower bound like this. So if you have a mixing with t-mix, the minimax MSC for missing mass on Markov is going to have a lower bound of t-mix by n. So if your chain is not mixing, you have really no hope of estimating missing mass very well. But of course, if it mixes you, there is potential, right? So even though good Turing is not going to do it, what else should you do to good Turing to make it work is the question. Okay. So for this, it's good to look at good Turing from a slightly different point of view, and this is called the leave one out view. I'm going to do that now. So you have n samples here. Good Turing is phi1 by n, which is number of singletons by n. Okay, you can rewrite this as follows. You can ask, is capital Xi a singleton? So that's your indicator, Xi not in X minus I, right? So this is the leave one out view. What is X minus I? Everything other than I. Okay, so is Xi there? If it's not there, then this is answering the question positively, isn't it? So the good Turing estimator is nothing but this guy, right? So you just count the number of singletons, you sum it over all I, and then you divide by n, you get the good Turing estimator. So this guy, this expression also makes sense in one more way from a standard estimation point of view. This is something that's always done. If you look at this one, no, that's actually a low bias estimate for missing mass, isn't it? Indicator that Xi is not there in X minus A. It's got low bias, but its variance is going to be really, really high. Okay, so you don't trust it. So what do? You average to reduce the variance. Okay, so this interpretation for missing mass for good Turing is a very nice one. The leave one out view, it tells you why it makes sense also. Okay, so why does this help? This helps because now we can view what's going on in the good Turing estimator in the IID case and compare it with what would happen in the Markov case. Okay, so this is my IID, this is the vanilla good Turing. In the IID case, Xi is independent of all X minus I, right? So this works quite reasonably. There's no need to worry about this. Averaging can just work, right? You don't have to scale the averaging or adjust it anyway. All of these guys are the same for you because Xi is independent of X minus I. Now in Markov, that's not going to be true. Okay, particularly mixing Markov, the Xi and Xi plus 1 minus 1 are all very heavily dependent. You don't want to rely on those guys as much as you rely on someone that's far away, right? So you want to do that differently. So Ashwin and Vidya, who are students at IITM long time ago, they are faculty at Georgia Tech now. So they came up with this very nice idea of leaving a window out. So what do? You look at the same guy, you do Xi not in X minus a window. Okay, so you kill a window around I and then only look at what's not there and take that as your low bias estimate for the missing mass. Okay, and then you average that over everything. Okay, so if you do that, then things work out quite well for you. So of course you have to assume that this window size is above the Tmix. Then this Xi and this X minus window are going to be independent. Okay, so that's the intuition. Of course, you have to show that the intuition works, but that's the intuition, and this seems to generalize from IID to mixing Markov quite naturally and nicely. So this is not very hard to implement. You can implement it very nicely. Of course, you need knowledge of Tmix here, which is a bit of a bummer. I mean, it'd be nice to not have that requirement, but you can do a data dependent tuning. Of course, if you do data dependent tuning, you can't prove, I mean, at least we couldn't prove anything much with that. Okay, so this is the windowed good Turing estimator. The first thing is it has to work on sticky, right? So we know the low bounds come from sticky, so it has to work on sticky, and it does. So this is a picture that shows that for sticky chains, the mean square error for the windowed case with the window size, it falls with n. Okay, so that shows that, and this one shows that confidence interval is not the same plot. But basically, earlier we had a flat for sticky with good Turing. Now it's falling. Okay, so for sticky it works. But then I'm not after one particular distribution, right? I want to show it universally for all alphabet, all distributions, and that also we can show. Okay, for this guy, using the mixing property, you can show that if tau is greater than Tmix log n by Tmix, this log you need because of that Tmix scaling I was talking about, then you would have MSC falling as big O Tmix by n log n by Tmix. So this log factor we give up, and we get that. The proof is a little long. I'm not going to talk about it here. It involves multiple steps, but essentially the principles are more or less the same. In most cases, when you do MSE analysis and this kind of thing, you're after a bias plus variance type decomposition, and you want to make both of those small. Bias in this case, in fact, good Turing analysis is curious in that factor. The bias is actually pointwise small. In every case, everything is small. Variance, of course, you need all the other mechanisms. This needs a careful handling when you want to deal with the mean square error here. The mixing and Markov have to carefully be used. A lot of technical detail there, but it finally gets to this nice form. Okay, so putting all together, this is what we know today about missing mass estimation for mixing Markov samples. There is a lower bound which is Tmix by n. There's also an upper bound today which is Tmix by n log n by Tmix. It's quite okay between friends, as they say, log is a constant, so we don't have to bother too much about it. But it'd be nice to have estimators without tmix knowledge. I have no idea how we can do that. Closing the log-n gap, of course, even though I said it's a constant, it's nice to do it. And Ashwin and Vidya's other students have extended it to like alpha mixing, other types of mixing, not just Markov, non-Markov mixing as well. And there are other interesting quantities in the Markov chain contest. So what I have looked at is what's called missing stationary mass, right? I'm looking at x1 to xn, I'm looking at the stationary distribution pi, I'm looking at how much of that I'm missing. What's often interesting in the Markov language model context is how much of a transition mass is missing. Let's say there is one word you're going to observe with 0.25 frequency or something. You see it quite often. Okay, how much of its transitions are missing? Okay, so those are interesting, I think, and in fact, a lot of language models use that. But I mean, that seems much harder. It's a little bit of a harder problem. Maybe there are ways to do it, but you might have to use more tricks than that. Okay, and there are other Markov problems, and I think there are relationships between these problems, but quite a few Markov problems in the estimation area are quite interesting. Okay, so that's the Markov. How am I doing on time? About 10 minutes? Okay, good. Okay, so let me talk about a recent work that one of my students did. It was presented in Allerton a few weeks ago. So this is asking more questions of the missing mass. Okay, so we have the missing part of the distribution. The missing mass is summing up all those things and giving you one number. Can I be more ambitious, right? So can I ask more interesting questions? Like for instance, maybe a question I want to ask is this pi miss, which is all the pi that I'm missing, is it close to uniform? Okay, so this is not just missing mass. You can even ask this question of things that you saw once. Okay, if you remember my large alphabet plot, right? The things you see once are actually over a wide range of probabilities. But typically when you estimate distribution, you will assign one probability value to everything you saw once, right? So I guess in IID you can't do much, but you may want to at least know how worse off you are because of that, assigning just one value to everything you saw once. Of course, once you see 3 or 4 times, I think it's okay. I mean, you won't have too much of variance there, but the 0 and 1, there is quite a bit of variance, and maybe you can answer this question and do something better. So for these kind of things, it turns out you have to generalize missing mass. Okay, so supposing I ask for a squared error distance, right? It will have this form, no, pi x minus delta whole squared, and there you will get this pi x squared. Okay, or maybe you want to ask relative log distance. Okay, so you want to put this, then you're going to get an expression like this. So this is showing you that to be able to figure out closeness to uniformity, you have to generalize missing mass. Generalize it to something like this, not just pi x. You want to have some function of pi x, and you want to be able to say how to estimate such things, right? If you can do that, maybe you can figure out something more interesting about what's missing. And this is something that one of my students looked at. In particular, he looked at the case where the g of x is just a power, pi x squared, pi x cubed type thing, and then g of x is this our familiar x log x, which is of interest to us for multiple reasons. And he had some nice results. For instance, for the order alpha missing mass, alpha is an integer, of course. So there, he was able to show a min-max MSE of 1 by n per 2 alpha minus 1, and the lower bound is using the what's called the Dirichlet-Pryor method, and the upper bound comes from a modified good Turing estimator. So you can see we use phi alpha here and divide by n choose alpha. So if you put alpha equals 1, you get the familiar good Turing. For other alphas, you do something slightly different. Okay, so you can more or less repeat something similar to get order alpha missing mass. Actually, we don't have too much estimators for other things. Okay, any other function g looks very complicated. We may not be able to do anything more there. Okay, so the question that we asked at Allerton, which showed up in the paper at Allerton, was this question. This natural distribution estimation we do all the time, right? Things that appear the same number of times, you assign them the same probability. Can we compute the error of that? Okay, so that's the question we asked. I want to show you this plot once again, just to say that, you know, the things that you see once actually are over a very wide range in terms of the probability. Okay, so if you assign one probability to them, you may be losing quite a bit. Can we measure that? That's the question here. So can we measure the error in natural distribution estimation? So is that possible or not? Particularly for unseen and sparsely seen words, this could be interesting. The ultimate goal, of course, is to inform distribution estimation, right? So see if you can adjust distribution estimation, or at least know how bad you will be doing there. Okay, so this is the formalism here. You look at SL as the set of letters that appeared L times, and then phi L, my prevalence, is the size of SL, right? And then there is an error metric that we invented. Of course, you can argue that this is an easy error metric. I'll agree. That's why we invented it like this. So you sum over all pairs in SL pi I minus pi j whole squared, and then you divide by 2. Okay, this is arbitrary. So this is the thing. You can see that if this is close to uniform, this guy will be small. If it's away from uniform, this guy will be large. It's not unreasonable that way, but the squared error is maybe not nice, like we were discussing in the morning. Maybe L1 is better here, but that seems harder for us to analyze. Square errors is easy to analyze, and this is a paper with Hari at Allerton, like I mentioned. So this is a reasonable metric. I'm just showing it to you with various distributions to claim that this metric is reasonable. The question is, can we estimate this guy? Okay, so if you look at what happens to this metric, if you manipulate it a bit, you see that it becomes a very nice difference between the order 2 missing mass and the order 1 missing mass squared. Okay, we know how to estimate the order 2 missing mass, we know how to estimate the order 1 missing mass. We should be able to put together an estimator for this, right? So this is probably doable, and Hari managed to come up with a very nice estimator, which is sort of some polynomial in phi L and phi L plus 2, and all these adjustments are to give a low bias and make sure the bias is of a nice form and all that. Essentially some sort of estimator like this, and you can show bias is low, you can show a sample complexity, and interestingly, I think the sample complexity for L equals 0 depends on the alphabet size. For L greater than 0, it doesn't depend on the alphabet size. So that's a nice thing that we saw. We picked up the tail of 2 cities distribution, and we showed that this it's consistent, and the simulation wise it ends up being consistent in some way. So we can estimate such errors, and these are of interest. Okay, so I have 5 more minutes. I'm going ahead of time. But anyway, let me summarize and maybe share some thoughts on what I think is interesting in this area. Missing and sparsely observed parts of distribution are very interesting in alphabet, particularly because even though you derive your methods from IID, Markov, etc., you use them in contexts where there are long-term dependencies. And clearly, I think there is some additional information available which your model on which you derive the estimator is refusing to use, but you may have that information, and what to do with it, how much will it improve things is an interesting question, right? Particularly for things you don't see and you see very, very rarely. So then if you look at the old world of language models, people do a lot of ad hoc tricks to introduce some additional knowledge into the estimator to adjust. So maybe one can explore that. That seems like an interesting thing to do. Extensions to mixing Markov chains are still interesting. There are still open problems there. How to handle mixing. In fact, estimating mixing time in a Markov chain also is a bit involved. And if you can come up with something which will cleverly avoid the estimation, that would be very interesting. I think that's a nice problem. Overall, I think, like I mentioned, I think the interest today is to go beyond Markov and look at long-range dependencies. Are there a lot of intriguing problems out there? These LLMs are doing fantastically well, but of course, they are burning many forests as they do it. So let's see if we can come up with some interesting statistical ideas which will maybe inform these things better. Okay, thanks a lot for patiently listening.
We take questions for Professor Andrew now.
With the ones close by, yeah. Both sides, yeah. You have to count for every eye. That's what we do. It's approximately IID. You have to show a DTV type approximate independence there. So you can show that. So so the way to think of it is mixing gives you a DTV, right, between those distributions. And then the function that we have is a function of the distribution in some sense. And any two functions also, once they mix, they will be closable. So that's the idea. You can show that in the Markov case.
Other questions?
Yeah, right. Yeah, yes, it is sort of in that context. Oh, high dimensional data. Would that be okay? No, high dimensional data is. Yeah, okay. Yeah. 2D Markov. Yeah, I mean, you can do that. These guys have done it for, like I said, Ashwin and Vidya students pushed it to alpha mixing or something like that. I don't know if that's enough. I, So general principle, I think what they also feel, I also feel that when you have a mixing, there will be a version of this result. It seems like that is true. You may have to adjust the estimator and the window and all that, but there should be a version of this result when you have mixing is the, I think is the general principle. Support becomes fundamentally different because you cannot do any such result for support if you don't assume alphabet size. See, because if you don't assume alphabet size and you're trying to, then there's no lower bound on your distribution, right? So I can't distinguish between 100 things missing with 1 by 1000 and 1 lakh things missing with 1 by 10 lakh or something. I can't distinguish between those cases at all. So support size. Uh, you can do that, but yeah, you're right. I think you can get an estimate through that, but I think there are better estimates for support size and they don't use these methods. They directly do something else. Here you don't have to assume. In the missing mass you don't have to assume. It's interestingly. For support size you have to assume because you're trying to get, I'm not, see in missing mass it won't matter even if it is 1 lakh or something because I'm adding up everything. No? And if it's very small, it's going to be very small still. In the support size it changes from 100 to 1 lakh. So you will give a big, it's just the metric you're choosing. If you normalize that support size or something, maybe it won't matter again. But that normalization comes from the lowest pi assumption, right? So, okay, thank you.
We next have Professor Naveen Kashyap. He'll be talking to us about code word stabilized codes.
Okay. All right. Yeah. Okay. Good. Okay. And now for something completely different, because I think quantum codes have not yet made their appearance yet, and Vijay's most recent interest is in quantum error correction. So we run a successful reading group on this. We've been doing it for the last year and a half or so, thanks to his students and mine, and postdocs. So yeah, so this is, so I apologies in advance to people who don't have any exposure to quantum. Unfortunately, this is a half an hour talk. I cannot give you that exposure to quantum, but there is a connections that I would like to make with classical coding. So let's begin. So the title is Code Word Stabilized Codes, which is another bridge. So that means there must be a standard first bridge between classical and quantum, and that is this usual notion of CSS codes, which forms a very standard. Everybody understands, like people who've been working in quantum, everybody knows what a CSS code is, and that's a very standard way of bridging from classical to quantum codes. But this is a lesser known technique, a lesser known construction. So let me spend some time on it. This is joint work. Serendipitously, we started with Saurabh Sudevan, who is a PhD student at IISc Kolkata. He visited us and then gave a talk, and then my student Ashwin picked it up, and Nupur was a postdoc in my group. Yeah, so this is, I think, an opportune time to present this material. So firstly, congratulations, Vijay, on this milestone, and also congratulations to Vijay for being awarded the National Science Chair for this year. So yeah, so it's like, and I think like it's Vijay seems to be unravaged by time. It's like he relies on the stabilizer code for the time operator. All right. Okay. So like yeah, so this is a different framework which enables us to construct a quantum code. There are two ingredients to this. For CSS codes, there's basically again two ingredients, but there are two classical codes. One has to be nested inside the other. Here is there are two ingredients to the code-wise stabilized code frameworks. One is a graph, a simple graph, and this from that which you will get a graph state from it, and a classical code. So it's a graph and a code put together will give you this framework for construction. Will give you a construction of a quantum code. So I'll describe that, give constructions and applications. It'll be like main thing is to just kind of at least give exposure to people who have not seen some who have seen this bridge, that is the CSS bridge between quantum and classical, to something different. All right, this is usual stuff for people who are familiar with the notions. This is very standard notation. People who are not familiar with it, again, sorry, this is not the place to pick it up. But like yeah, these are poly operators. So you have X, Y, Z, and I, and so this is like, so we have the poly group and n qubits. So like throughout we'll be using everything is, we're talking about the codes on n qubits. So n is like the number of qubits overall always. Poly operators X, Y, and Z. So this notation will be useful for us in descriptions. So these are like the Z operator acting upon when I subscript it by a binary sequence X. That is it operates only on the support of X. Okay, the Z operators only are acting on the qubits in the support of X. Okay, the qubits indexed by the support of X. Similarly here, when I have same thing with like a subset of the qubits, so Z is acting only upon that subset of qubits. So these are two different notations. Okay. So Z, by the way, if people don't know, it's like a phase, like it's insertion of phase. It's a selective insertion of phase. It's like a conditional insertion of phase into a qubit. When the qubit is 0, no phase gets inserted. When the qubit is 1, the phase gets flipped. All right. So then there's also again standard stuff for this in the quantum perspective. Poly operators also have a symplectic representation as binary vectors. So basically, there are 4 poly operators X, Y, Z, and the identity, and then they're given 2-bit representations. The 2-bit representation is chosen in a way that kind of makes this sort of a group isomorphism between the pairs of qubits and F2 squared, F2 cross F2, and the poly group, the single qubit poly group, X, Y, Z, and I. So nothing much like, so for example, X is given where is it? So there are 4 poly operators as I said, X, Y, Z, and I. X is given the representation 1, 0. Z is given the representation 0, 1. Identity is given the representation 0, 0. And Y is given the representation 1, 1. Okay, Y is basically the product of X and Z. That is why that is this. Okay, so then you extend that to n qubits in a natural way by basically concatenating these. So you always keep the separation between what is called the X part and the Z part. So poly operator will have what is called an X part and a Z part, and like the X part is indexed by X part is determined by this binary vector A with n bits, and the Z part is determined by the binary vector B of n bits. So the poly operator looks like something like this: X sub A times Z sub B up to some global phase factor. The weight of this poly operator is weight is just simply the number of the poly operators are formed by taking tensor products of these elementary operators, and the number of non-trivial tensor products, number of non-identity operators within that tensor product is called the weight of the poly operator, and that is also corresponds to the symplectic weight of this vector A, comma B in the symplectic representation. Something maybe more familiar to people at least with exposure in theory. This notation NKD is a binary linear code, block length n, dimension k, minimum distance d. Where if I put 2 square brackets, it becomes a quantum code. A quantum stabilizer code, to be honest, to be clear. So it is a quantum code on n qubit Hilbert space. The number of qubits is n. it encodes k qubits. We call them logical qubits. N is called the physical qubits. Number of physical qubits, number of logical qubits, and d is the minimum distance. And it is a pure quantum. It has this property that if I have a poly error, which is of small enough weight, that a non-trivial poly operator of weight strictly less than d, that means number of the qubits upon which it non-trivially acts is less than d, then the error operator takes a code state. An error operator takes a code state to the entire code space gets taken to an orthogonal space. Error operator takes the code space to an orthogonal space. So that's useful for error correction. Anyway, that's sort of, so it's basically these errors are then correctable. So that means that these errors are then correctable, or actually detectable, I should say. So strictly less than, so errors of weight strictly less than d are detectable. Therefore, that is why we call that distance of the code is d. All right. So here now something again back to some things that everybody should understand. We have a start with a simple. So as I said, in the CWS code construction, there are two ingredients: a graph and a classical code. So the graph is a simple undirected graph on n vertices, and this n is always going to be around. Okay, n is the number of qubits, block length of the. We have all of that. The n qubit. So we have a simple undirected graph. So associated to that graph, so graph has vertices and edges. So associated to each vertex of that graph, I put a stabilizer. I put a poly operator. Okay, a poly operator associated to each vertex of that graph. S sub I is a poly operator associated with that vertex. It is the product of tensor product of the x operator acting on that vertex, acting on the qubit indexed by that vertex, times the z operator is acting on the qubits indexed by the neighbors of that vertex. Okay. So these are poly operators. It is not at all difficult to see that they commute. Okay, so that like and so as they commute, so they form a stabilizer group. The stabilizer. So this is these like the entire graph has n vertices. So there are n stabilizer generators, we call it. This group is generated by these n stabilizer generators. There are n stabilizer generators. These are independent generators. And the theory basically says that so the code space, that is the +1 eigenspace of all of these generators. So maybe I'm jumping a bit ahead. The +1 eigenspace. So since all of these operators commute, they have a common eigenbasis, and all of these like standard theory. This is all completely standard theory. So there's a common +1 eigenspace for all of these operators. Since there are n of these operators, so that +1 eigenspace has dimension exactly equal to is one dimensional. Okay, that turns out that the +1 eigenspace is one dimensional. One dimension has a complex vector space. So the theory basically says that this is what is called a stabilizer state. It is still a quantum code, but it encodes no logical qubits. Okay, it is a quantum code on n physical qubits which encodes no logical qubits, but it's a stabilizer. The stabilizer generators, another way of viewing the stabilizer generators is that they, in symplectic notations, they correspond to the rows of this matrix. Identity at the beginning, followed by the adjacency matrix of the graph on the other side. Okay, that's the adjacency matrix that correspond to the Z. That's the Z part of the stabilizers. The X part of the stabilizers just are the identity. So here's one quick example. Like so we have, as I said, so we start with the graph. This graph has 4 vertices. So corresponding to each vertex, we will have a stabilizer generator. So for the first vertex, this is just a stabilizer generator, X acting on the first vertex. So each vertex has a qubit associated with it. X acting on the first qubit, Z acting on the second qubit, because the first qubit there's only one neighbor of it. The second guy is X for the second vertex. The stabilizer generator corresponding to that is X acting on that qubit, Z acting on its neighbors. Similarly with the third and the fourth. So, okay, you have 4 independent stabilizer generators, and correspondingly, the common eigenspace for that is the stabilizer state, is a graph state. So what we do with that? So associated with every graph, there is a notion of a graph state. Then like the next ingredient I'm bringing in now, you take a classical code. It need not even be linear at this stage. Take a classical code on a block length n. N is the same thing. Everything is like number of vertices in the graph is the same as the block length n of this code. You take a code of block length then with 2 to the k number of code words. Okay. If k is linear, I mean, if the code is linear, then k would be the dimension, but it need not be linear. And you take that, you start with that graph state, and you knock it around by z operators indexed by the code words. Z operators subscripted by the code words. Okay. You take code, you take the basic state, the graph state, and then you knock it around with these poly operators, these poly z operators. And the poly z operators are those operators specifically formed by index, basically only acting upon the qubits indexed by code words, indexed by the support set of code words. You take the span of all of these states, and that is what is called the QW, that is called the CWS code. Okay, it is a 2 to the k dimensional quantum code. It's not hard to see that these are all of these things will give rise to a set of linearly independent states, orthogonal states. And as a consequence, it's a 2 to the k dimensional space. So this, I should say, that was first defined by Andrew 2009. So it was mainly as a curiosity for a long time. It was basically because it was sort of a construction that methodical construction of quantum codes were not stabilizer codes. Stabilizer codes by that time had like a fairly good theory had evolved by that time for codes, which are the equivalent of linear codes in the classical setting. But non-stabilizer codes, they arise from non-linear codes. If this code binary, if the binary codes to C we choose here is non-linear, then the resulting construction gives you a non-stabilizer code. Okay, so that, and it gives us a methodical way of constructing non-stabilizer codes. Okay, so the point is that like if C is a classical n comma k linear code, D I am not mentioning here yet, then the corresponding, this construction gives you a code on n physical qubits and k logical qubits as we have just seen. Okay. So the idea is generally, now what we do is to choose our graph and the code, classical code, to obtain a CWS code with some good properties like good minimum distance and so on. Okay, okay, that is what like finally the game now is. It turns out that this is not an easy game to play. So there has been, so Cross's paper had like a bunch of sort of examples of constructions, and sort of most people, I mean it was sporadic such examples, but like recently there has been a bit more of a development in this area. Let me just kind of try to see whether I can cover some of that. How much time now do I have left? 15 minutes. Good. Okay. So the first, I want to give like just a theorem again. So the point is, so if I start with a graph on n vertices, and I take an n comma k binary linear code, then the CWS code construction already gives me an n comma k stabilizer code. Okay. The stabilizer group for the graph state I'm denoting by S. Then, if I wanted to get the resulting code, the CWS code will have quantum distance, minimum distance d, if and only if for all n qubit poly operators whose weight, that is, which act non-trivially on at most or strictly less than d qubits, this applies. That is, the z indexed by all code words times the poly operator, this poly operator should not be a stabilizer. So stabilizers should, so these kind of operators should not be in the stabilizer group. Okay, so this is the property, this is the characterization. This is a characterization that assures the minimum distance. Okay. So our goal is now to find G and C that allows us to build upon this characterization. It's better, sometimes it's easier to see, okay, there's a picture that Ashwant is responsible for many of these slides, and I think this is a picture that he has also drawn. So yeah, it basically summarizes the same thing that I have just mentioned. But maybe for at least this classical audience more familiar with codes, I will give a vector space description of the same thing, a classical vector space description, which will be maybe better to understand, easier to absorb. But here's a simple example. If I start with the 5 cycle, the graph is a 5 cycle, and the code is a repetition code on 5 bits. It's a linear code. Then it can be verified that there is no poly operator of weight 1 or 2, such that this for which this is a stabilizer. All z's multiplied by the poly operator e of weight 1 or 2 will never be a stabilizer. So as a consequence of the previous theorem, this shows that like the resulting CWS code is a 5, 1, 3 minimum distance 3 stabilizer code. Okay. And this is again well known, understood. This is a well understood stabilizer code. It's the smallest stabilizer code that has minimum distance 3. It can correct a single error, but it comes through this construction as well. Okay, maybe the proof is not important. All right, but I want to give this restatement of this theorem in terms of classical vector spaces. So once again, the ingredient was like I have a graph. I have a graph on n vertices and a linear code. This time, let it have a generator matrix G. A stabilizer group for the graph state. Now the stabilizer group is the stabilizer group I have told you already is given by the rows of this matrix, the first matrix on top, identity followed by the adjacency matrix of the graph. Okay, that's the rows of that in sense is like will represent each stabilizer generator. The bottom part is basically coming from this linear code. So I'm augmenting that stabilizer check matrix, we call it as check matrix, with this matrix that comes from the linear code. The generator matrix, the generator matrix is stuck into the generator matrix of the linear code is stuck into the Z part of this H matrix, and the X part is given to be 0. Okay. So I take it this matrix. This is the matrix that I have. So this matrix is purely defined by the ingredients of my construction. I let V be the row space of this matrix, so the code generated by this matrix. Okay, then what happens is that so this is the characterization that this code, the CVBS code that I get from these ingredients has minimum distance D, if and only if if and only if I think this should be for all non-zero V. So the minimum symplectic weight, the minimum symplectic weight of vectors lying in the row space of this matrix, non-zero vectors lying in the row space of this matrix, should be at least D. Okay, so this is a simple. I mean, if you want to take out nothing else away from this talk, at least this is a way of saying that this is a good way of getting quantum codes with desired properties, and there's a characterization of how to get desired minimum distance. Described purely classically. No, these are what are called pure codes. Stabilizer codes need not be pure. Okay, so okay, yeah. So this D is really at least D. It is not really exactly D. So there is but it is in. No, we don't deduce that. We don't care about it really. We just use this notation anyway. D just means that up to D errors are detectable. Strictly less than D errors are detectable. That's all. You don't say that whether it is the maximum number of such errors or not. Okay, that is not. Yeah, so it's mainly terminology. Difference in terminology. Okay. All right. Okay. So how do you then choose G and C so as to get good CWS codes? So one thing is to note is that if all the code states have to have some property like this, which comes from the purity of the code, that means that the basic graph state itself should have a property like this. That is like the error operators that act on strictly smaller than D number of qubits must take that graph state to a pure completely orthogonal state. Okay, so the graph state itself is a pure code. It is a pure n, 0, D quantum code. This is what is called a D-1 uniform in the language of quantum, in the language of quantum information. This is called a D-1 uniform state, D-1 uniform quantum state. So basically, so we'll talk about some constructions now. The n qubit state is said to be M uniform if all possible M qubit marginals are maximally mixed. Okay, this is like technology here. So the Bell states, for example, are 1 uniform. Another way of viewing it is that an n qubit state is M uniform if and only if it gets taken to an orthogonal state by all Pori operators of weight at most n. Okay, so actually this should be strictly less than n. So all Pori operators with weight strictly less than n. Yeah. So the idea is that to begin with, what we already need, like already the thing says that like if you want to have if you want to get a good CWS code, the graph state that you start with must already have this property. The graph state that you start with must have the d-1 uniformity property. So you must choose your graph in such a way that it must at least have this d-1 uniformity property. So how do you choose that? Like there are ways of doing it, and so that is one part of it. But even if you choose a good graph, what about the second part of the thing? Like, can you choose the code itself? So that you get a CWS code of the largest possible dimension, for example, with a choice with your sums. Your heart is set on a certain minimum distance. I want to find the CWS code with the largest possible dimension for that minimum distance, or largest number of logical qubits. That actually is NP hard. So what we do is things like this. We do give some sufficient conditions for giving CWS codes of reasonably large dimension. So we start with a d-1 uniform state, a graph state that is d-1 uniform with some additional property. In this case, we assume that it is constructed from a d-1 regular graph. It's not always the case that d-1 regular graph will give you a d-1 uniform graph state, but it is the case that if you start with a d-1 uniform graph, regular graph, which gives you a d-1 uniform graph state, then as long as your binary linear code, the second ingredient for construction, has a classical minimum distance strictly larger than d times d-1, the resulting code, quantum code, has minimum distance d. This is something. This is one possible way of doing this. This is purely constructive. This can be done constructively. Okay. So that gives you, for example, codes like this. If I choose my graph state like an 8 cycle like this, it turns out it is 2 uniform, and this repetition code satisfies the property, the sufficient condition of that theorem. It gives you an 8, 1, 3 quantum code. Okay. This condition is a bit sufficient, but is overstrong. There are ways of reducing that condition. You take these type of lattices, these type of graphs, what are called d-dimensional lattices with periodic boundary conditions, basically tori. These are known to have uniformity properties. You start these as the graph states, and then you have to pick a code that is that gives you a nice, which has the additional property that will guarantee that the resulting CWS code has a guaranteed minimum distance. So we do all of that. We have some construction. This is all our recent constructions. So we take this lambda n is basically the n cycle. It is the periodic lattice with one-dimensional periodic lattice with a lattice with periodic boundary conditions. Lambda n is just the n cycle. And a specific construction of a cyclic code given by this gives you a pure quantum code like this. So this is a family of pure quantum codes. Another construction that we have, like this was done by by Nupur. She did the same construction, or like we started instead with a 2D cluster state, like a 2-dimensional lattice with periodic boundary conditions. The graph state corresponding to that is called a 2D cluster state. It is 4 uniform. And it turns out that then she used 2-dimensional cyclic codes in conjunction with that cluster state to come up with quantum codes which were like this, n squared k5. So for example, we would get a 225 physical qubits, 186 logical qubits, 5 quantum code. So anyway, this competes well with the best known codes in the literature. These are all what are called pure codes. Pure codes are useful for various reasons. I mean, they're kind of, so it's not clear whether the best known codes in the literature are pure. Finally, let me so this is something very recent, about a week back, we had a discussion with our student Ashwant, and we think that we have this kind of a GV bound for CWS codes, anytime you have parameters n, k, and d satisfying, there is a quantum GV. There's already a quantum GV, which looks very similar to this, except for the -1 at the end. That is like if I take n, k, d with these parameters, then there exists a stabilizer code, n, k, d stabilizer code with these with the same. Okay, that is a quantum GV bound. So if I put this -1 in, then it gives me a slight variation on the quantum GV bound, but with stronger conclusions. Says that take any n, k, d binary linear code. So NKD satisfy this. So by the Gilbert-Vashamov, there's always classical Gilbert-Vashamov. There is a binary linear code also with these parameters. But take any classical binary linear code with these parameters. Then they're always, we can find a graph on n vertices for which you can get the corresponding CWS code to be an n comma k comma d stabilizer code. The proof, of course, is non-constructive. This graph is used an addition random graph, and say that if you take an addition random graph with non-zero probability, this will satisfy. All right, applications, maybe I'll just give one quick application. How much time? 5 minutes? 2 minutes? 1 minute. All right, let me just do this because I think this is maybe useful to know that like others have also been looking at this and find this CWS code construction. So the problem, in the classical setting, many of us know that the problem of determining the minimum distance of a classical linear code is NP-hard, is well known to be NP-hard. So this was extended to that of classic for quantum codes. Recent work about 2-3 years back by Upendra Kapshikar and Sridhar Kundu. They demonstrated that they showed that the problem of determining the minimum distance of a quantum stabilizer code is NP-hard. Okay. The proof is actually via reduction from the same problem for classical codes. Okay. And that reduction, because they use the classical code as an ingredient in the CWS code construction to come up with a quantum code with the same distance. The idea is just that you start with the n comma k binary linear code, and they construct in polynomial time. This is very important. They have to find that other ingredient, the second ingredient, that graph. They have to find that graph in polynomial time. Okay, so that's only then the reduction will work when you find a nice graph in polynomial time. So find a graph in polynomial time such that they find a graph in polynomial time. They construct explicitly a graph in polynomial time that gives you an order n squared number of physical qubits, comma logical qubits is the same in the quantum code, but main thing is that minimum distance is the same. Okay, so here that means that if I could find the minimum distance of this quantum code efficiently, I'd be able to find the minimum distance of the classical code efficiently. Okay, so then, but we know that finding the minimum distance of the classical code efficiently is not possible, and hence finding that for the quantum code is also not possible. Okay, so this construction in fact applies the CWS code framework. So graph states that are obtained from an explicit family interesting of 4 free, whereas our construction is based on lattices which are full of 4 cycles. At least high-dimensional lattices. All right, so that's maybe where I will just stop. There are other uses for our construction. We believe this allows for sequential encoding of qubits. That is, this kind of our CWS code framework does allows for if you don't have all the k qubits to encode it simultaneously, only one of them, some of them are available and the others are not. You encode the first how much ever are available, you encode them first, and then as the later ones come along, you sort of encode them later. So this allows some sort of a sequential encoding and sequential retrieval framework. Okay, so that's sort of where we are, and these are some references. And once again, thanks for organizing this, the organizers, and congratulations once again, Vijay. It's been a pleasure having you as a colleague all these years. Thanks.
Quick questions for Professor Kashyap.
Correct. That's right. Yeah. Sure. Yeah, that's a good point. It's just that good that code states to orthogonal spaces. The entire code space gets taken to an orthogonal. No. No, it will happen automatically, but because the commute. I mean, here it's not, within this is not a problem. There are zeros at the beginning. Here, yeah, I mean, it's, here I'm not like, okay, this commutes to the num itself. The rest of it, I don't care. I mean, I'm not using a simple, this is not the, what do you call it? I'm not using this in the stabilizer code framework. You have to start with that. It's a necessary condition.
Let's thank Professor Kashyap again. We now have Professor Agrish speaking to us about DNA codes with combinatorial constraints.
It's there in the Dropbox. While they are setting up this, I'd like to thank Lalita and organizers for inviting me. I think I met Vijay first in 2002, if I remember correctly. It was an IISc Lausanne, Dan's 60th birthday. I think that's where I first met you. Though I've heard a lot about you because your cousin Sanjeev Pulapaka was doing MBA at Notre Dame 97 to 99, and he used to talk about you and PR a lot because PR used to drive from IISc and used to come this thing. So yeah, so yeah, that's the thing. And another story, I mean, when I joined IIT Kanpur in 2004. Those were the early days of NPTEL. So we were asked to, opt for courses. And so I obviously opted for coding theory. Andrew had already recorded before anybody else, I mean, coding theory. And when I opted, they said, no, you cannot do it. A professor from IISc has already opted for it and he's doing it. So I said, okay, IISc, there's either Vijay or Sundar. Both of them will do mostly algebraic coding. So my flavor is very, very different. So I found out it was Vijay who was doing the course, and then I argued with them. I not argued, I told them like my flavor is very different from there, and then they allowed me to record. And of course, the course is running now annually, this thing. So yeah. So we all know Vijay did a lot of work on storage systems. So when I was thinking about topic, I thought maybe this would be a good topic because we are talking about DNA storage code. This is a work actually done by my postdoc, Krishna Gopal Banerjee. He has been working on this for last 3-4 years. So I'm going to present results and no proofs, only results. That also reminds me of a joke which is attributed to Chris Seegert. Some of you may know, he was at Cornell. I heard this joke from Tom Suje. So Tom used to say a good talk is one where 1/3 everybody understands, 1/3 only the people in the area will understand, and 1/3 nobody will understand. Okay, this talk is more or less going to follow that because I was told by Lalita that there will be 70 graduate students, so I kind of kept it initially simple, defining the constraints, how they are, and give a simple lot of examples to illustrate how the code construction happens. And then I will go into results without proofs of the properties of those. And finally, I will talk about some bounds. I mean, we already saw spare packing and DV bounds. We'll do that. So let's start the talk. So I will first give a very brief introduction to DNA codes. Thanks to Prasad. My work is easy. I can quickly go over it. And then I will define some of the constraints or errors that we need to deal with when designing codes for DNA storage system. I will talk about a construction of DNA codes satisfying those constraints. And finally, I will conclude with some upper bound based on sphere packing bound and lower bounds based on GV bounds. So as Prasad mentioned that one of the advantage of DNA codes is very high storage density. The second advantage is the longevity. You can store data for a very long time. In fact, in this example that I have shown, a company called Catalog has stored 16 GB of Wikipedia information in the small vial. So very compact and large density and longevity. That's the advantage of DNA codes. Very quickly, data storage process. So basically you have your binary data which is converted into a quaternary sequence. Now these sequence of nucleotides are used as a template for chemical synthesis of DNA. And then we heard Prasad talk about one way of reading this DNA. He talked about shotgun sequences, and then you convert back to the data. So that's the process involved. So what are the common errors that happens when we try to read and write? So one is substitution error. So you can see here the nucleotide A has been replaced by G. So that's a substitution error. In deletion error, the nucleotide gets deleted. So we send TACT, we receive TAT. And in the insertion error, we have additional nucleotide which has been added up. Now let us define a set of quaternary alphabet A, C, G, T. A sequence Z of length L over this set is defined by Z. We call the reverse sequence as if this is Z1, Z2, Zn, this is Zn, Zn minus 1, Z1. That's a reverse sequence. Similarly, we define the complement sequence of Z as if we replace the base by their corresponding Watson-Crick base pair. So A replaced by T, C replaced by G, and vice versa, we get the complement sequence. And similarly, we can define a reverse complement sequence. So this is a complement of the reverse sequence. Take an example. So if Z is a sequence of length 6, AACTGC, so reverse sequence will be CGTCAA, and complement A complement is T, so this TT, C complement is G, A complement, sorry, T complement A, and G complement C, and this is G. So this is a complement, and reverse complement is a complement of this. So C will be G, G will be C, T will be A, and so on. So I've defined three types of sequences: reverse sequence, complement sequence, and reverse complement sequence. So we define, now we are going to define a DNA code over this alphabet. So a DNA code is of length n, size m, and minimum distance, Hamming distance th, where x and y are distinct code words. So take an example. So in this case, n equal to 4, you can see the code word length is 4. There are m code words, and you can verify that the minimum Hamming distance is 3. Now another thing that we need to worry about is what is called a secondary structure. So if we have, yes. Okay, there is a different distance property, edit distance. I'm not considering here, at least the construction where I'm showing here, I'm not, there I will deal with edit distance. So we have done some work. This IISc 2025, we had worked on deletion codes satisfying, substitution codes satisfying these conditions. So another thing that we need to worry about is basically single strand DNA, they can fold on themselves. So you can see something like this can happen. So when these consecutive nucleotides, they combine to each other, that's called a stem. So number of such pairs, that's the stem length. So this is actually called stem, and this is called loop. Now what happens when they basically merge like this? They release what we call free energy, and that free energy is related to what is known as interaction energy. So if Zi and Zj are C or G, that interaction energy is -5, it's -4 for A and T, and it's -1 for G and T. Now, the free energy for a subsequence from I to J is given by this expression. So it's related to the interaction energy with initial value given by this. Now, there is a program, Vienna RNA, which basically uses something called Nusinov-Jacobson algorithm to actually predict secondary structure in the single strand DNAs. Okay. Now I will define. So many questions so far. I've defined reverse sequence, complement sequence, reverse complement sequence, and secondary structure. Now, of course, secondary structures are not good because they are stable that you require more energy to read them, so those should be avoided. Now let's talk about homopolymers. So homopolymers are basically run of same nucleotide. So you can see here G is repeated 4 times, so it has a run of 4. T has a run of 5. So if a sequence doesn't have consecutive runs of a nucleotide, we call it homopolymer free sequence. And again, this has effect on insertion deletion error. So typically we would like to avoid homopolymers runs. So you can see in this sequence, since there is no run of 6, we say this is free of homopolymers of run length 6. Now let's define GC weight. So GC weight is defined as number of basically C and G in the sequence. So you can see in this DNA sequence, number of C and G are 2, 3, 3, 1, that's 9. So that's a GC weight. Typically, we would like in our code the GC weight to be half of the length of the sequence. That's a desirable property. Now, let's talk about constraint based on this properties I have described. So what is a reverse constraint? So before I define reverse constraint, let's define the Hamming distance between the sequence and the reverse sequence. So I have two sequences X and Y. The reverse of Y is YR. So Hamming distance between X and YR, I denote it by DR. Similarly, the Hamming distance between X and reverse complement sequence, I denote it by DRC. And we say a code satisfies reverse constraint if DR is greater than D. If this condition is satisfied, we say reverse constraint is satisfied. Similarly, we say reverse complement condition is satisfied if DRC is greater than D. And as I said, we typically, for a GC balance, we want it to be n by 2. If the sequence is odd weight, then you basically it will be, floor of n by 2 or floor of n by 2 plus 1. So that's what I am writing here. So you can see in this example, this is a code of length 4. There are 8 such code words, and this has Hamming distance 3, and you can verify that it satisfies both reverse constraint and reverse complement constraint. Both, I think in this example, are 3. Okay, so what is the problem that we are looking at? So given two integers L and R, we want to construct a family of DNA codes of length M, size M, Hamming distance DH, which has the following properties. What are these properties? They should satisfy the reverse constraint. That means DR should be greater than this D. It should satisfy reverse complement constraint. So DRC should be greater than D. It should be GC balanced. So GC content should be close to n by 2. it should be free of homopolymers run of L that we can specify, and it should avoid secondary structure of stem length more than R. That means consecutive, this R, there should be no more than R consecutive nucleotides which are binding together. So this is our design problem, and we will come to a construction of satisfying this. The second problem that we are interested is, given a DNA code, so let's say given the parameters of DNA code, if you specify, let's say, the code word length, specify the Hamming distance, specify the GC weight, can you tell me how many such code words exist? Okay. That's the question we will try to answer. So these are the two problems we will try to answer. Okay. Now we consider basically elements over Z6, and I defined two mappings. So the sigma 0 and sigma E, and how these elements are mapped. So I'm mapping this element 0 to 5 using this. So my phi 0 is ACA, phi 1 is CT1, phi 2 is AAC, 3 is AGA, and 4 is CAA, and like that. Similarly, I'm mapping these to this set. So this is how I've done this mapping. If you are wondering how I have done it or why I have done this, so obviously these have been done keeping in mind I have to satisfy the GC constraint. So if you look at this kind of mapping here, the content of GC is 1/3, here it is 2/3. So if I use a DNA code which is a map of both of them, my GC will be balanced. And of course, to take care of homopolymer runs and secondary homopolymer runs, I have chosen these combinations. This is not a unique mapping. This is just one way of getting it done. So I'm defining a sequence of length n, and my psi 0 is defined as phi 0x, phi ox, phi e x2. So alternatingly, I am using the mapping from odd and even. Okay, this is for odd n, so it will end in phi 0 xn, and in case of even n, it will end in xcn. That's how I define my psi 0. Similarly, I define my psi x. Now this is phi e x1, phi o x2, phi e x3, like that. Okay, so this is how I define this mapping. So for any code C, this code word essentially consists of phi ex and phi of 0. Okay, let me give an example to illustrate this. So in the mapping that I've shown you, my phi 0 was AC1, phi 0 was this, phi 1 was CTA, and phi 0 was this, phi 1 was this. Let's consider a sequence of length 2, okay, x1 and x2. Then basically for this, my phi 0 will be psi 0 x1 and phi 0 x1 and phi e x2, right? For a odd this thing. And what is my psi e? This will be phi e x1 and phi 0 x2. So let's take an example. Let's say my code word was 0 0 and 1 1. Okay, my repetition code I take. Then basically, what is my code word? So I would consider phi. So if you look at basically, so my code word consists of phi e and phi 0, right? So I need to consider all possible phi e and phi 0. So if you see, my phi 0 0 0 is, this is ACA, and I put phi, so this phi 0 0 will be phi 0 0 phi e 0. What is phi 0 0? That is AC1. So that is AC1. And what is phi E0? That is CAC. So that is CAC. So that's how I'm getting this. Similarly, I can get for phi 0, 0, 0, I get phi E0, 0, and I will get phi 0, 1, 1 and phi E1, 1. Are you guys with me so far? This is supposed to be in that first 1/3. Okay, okay. So this is how we are constructing this code. Okay. Okay, now things get interesting. I'm not giving you the proof. I'm just telling you the property of result of this mapping. Okay, so this is actually our ISIT 2022 paper, and all the proofs are there in that paper. So if DH is less than 2n, then we have shown that this code satisfies the reverse constraint, reverse complement constraint. If you consider Z of length 2n, so remember each alphabet is getting mapped to 3 nucleotides. So we will get a code word of length 6n. And because we are using alternate map of phi 0 and phi E, we will get from one we will get GC weight 1, or from other we'll get weight 2. So we will get overall weight of 3n. So we will get a GC balanced code. Okay. We have also shown that this is independent of homopolymers of length 3 and secondary structure of stem length more than 2. And finally, this will ensure that reverse constraint is also satisfied. So if any for any row G of this matrix, if GR is a submodule, then basically if Z is a code, then ZR will also be a code. Okay. So if you ensure this property, then this result follows. Now let us define the distance. So I define 3 distance: D0 xy, DE xy, and DE0. So you can see it's a Hamming distance between phi 0 x and phi 0 y, that is D0. It is the Hamming distance between phi E and phi EX and phi EY, and this is the Hamming distance between phi EX and phi OY. And I define my this is for any alphabet in Z6. If you have a n length sequence, I can just add component wise this, so I get these distances. Fine. So now I'm defining basically minimum distance as minimum of these distances. Okay. And I can show that for any code over Z6, the minimum distance is given by this. Okay. Now let us basically talk about some of the parameters of the codes that we achieve for. So if we take a code C of parameter M, M, and D, using this mapping, we can get a code of length 3n, size 2m, and Hamming distance D. Okay. We can increase the alphabet, or we can increase the code size by not only considering this code, but also considering the complement of this code. So if we do that, we will basically get code of parameter 3n, 4m, and dh. Okay. However, by doing this, most of the properties are satisfied, but the secondary sequence, secondary structure may not be satisfied if we do this concatenation. Okay. Finally, we also obtained a GV bound on this in this paper. So we have shown that for this code, DNA codes of length 3n and Hamming distance D, if it satisfies reverse constraint, reverse complement constraint, it's a GC balanced code. It has a homopolymer of run length not more than 3 and avoids secondary structure of stem length up to 2, then basically lower bound is given by this. And this is because we have codes which have this size. So this is an example I already talked about. if we do concatenation, we can increase the size of this code. Now, we also looked at, how much time I have? 3 minutes. Okay, let me then just jump this. So basically, this is another construction based on quote unquote Reed-Muller type. So if you look at the structure of G matrix, it is all one, and you have this, and this here. We have something, we are calling it modified Reed-Muller type Z code. Okay, and this satisfies many of these constraints we talked about. Let's just skip this. Let me just, okay, so we have done some comparison of our code rates. As you can see, basically, if you try to put in too many constraints, the code rates are not that good. These are some of the other results. Got 0.33 here. This was Naveen's original paper where they have considered GC balance, homopolymers of length 4 and stem length of 2. Okay, now let's use my 3 minutes to talk about bounds. Okay, so Professor Sundarajan already talked about SP bounds. So you know SP bounds. We have computed SP bounds to get the upper bound. And Naveen talked about GV bound. So we have used GV bound to compute the lower bound. So this is for the sphere packing band bound. So for integer n, Hamming distance h, GC weight w, the size of the code word is upper bounded by this, where this v is given by this expression. These are the numbers, which is probably little better to look at. This was a result we presented at Allerton 2022, and we also showed lower bound. Again, this was presented in Allerton 2022, and these are the numbers from that. Okay. This is little bit more tricky. This is bounds for homopolymer free DNA code. That means we are not allowing any repetitions of the nucleotides. Okay. The problem here was the Hamming sphere size was dependent on the code word. It was not like independent of this. Okay, so this was a little bit challenging. We presented this result in IISc 2023, and these are the upper bounds. So this is basically the minimum of the Hamming sphere size. These are the numbers from that. Similarly, we improved the bound by, instead of considering the minimum, we considered the average Hamming sphere size. So what we are considering here, you can see, is averaged over all code words. So we use that to get a tighter upper bound. Okay, and these are the numbers we got for that. Similarly, we also did for lower bound. Okay, I'm just skipping it. This looks too small. I cannot expand it. So what you see here is, in the top you see sphere packing bound without any constraints. So there's no constraint. That's a sphere packing bound, and this is a GV bound without any constraints for the DNA codes. Now this is the upper bound, the first upper bound that I talked about, which considered A min, and this is the improved upper bound which we got when we considered the average sphere size. And similarly, these are the lower bound. So these are for the homopolymer free codes. This was IISc 23. Then ICC 2025, we have we computed for a general what we call constant weight sum code, and for a specific case we get the results for DNA codes. We computed a total number of DNA sequence of length n and weight w. So that was this expression. So if you just look at, I'm now going to compare the code rate for different scenarios I've considered. I first considered GC content homopolymer free, and also so these are the number of code words I got for the GC WGC constraint. This was the result for homopolymers. These are the number of code words, and this expression we just showed here. Okay, so let's plot it. So what you see here, this is for homopolymer free. This asymptotically, this code rate I'm getting is close to 0.79. For homopolymer free and GC balance, I'm getting close to 0.75, and this is for the GC constraint. Now, if you see here the zigzag, that's because for n equal to odd, the values are different, and n equal to even, they are different because of there's a I think floor function or seed function. Because of that, it's happening. So finally, an expanded version of this paper has been accepted in a special issue of DNA storage for journal in selected area in communication, and it is available in early access. So there we talk more details, especially about how we create this DNA code set, this mapping and stuff. Okay. Thank you. Sorry.
We have time for questions.
Yes. Right. Right. We have done. So our COM paper we consider over Z5. Okay. So we have done it over other alphabet size also. Yes. No, so we have not really looked. We just fixed our alphabet size, and then we tried to find this mapping which satisfies our constraint. So we not really, and of course you can compare. So you can compare, for example, at least our construction. So let's see. Where is the table? Here. So these were the two that you see. These are from these were over Z5. We used Hamming based constructions, and you can see here the code rates were lower, whereas here when we use that Reed-Waller based construction, which I skipped, we got a higher rate compared to this thing. But I cannot answer a general question as to which is the best alphabet. I don't have the answer. Thank you.
Any other questions? So just one sec. So you were speaking about a GV bound where you were using the average kind of volume of the Hammings, the spheres around.
Right.
So how did you get that bound? I mean, how was it derived? Because the maximum I can see when you divide.
Yeah. So basically, these spheres are all disjoint. So multiplied by this should be less than.
Sure.
So from there we got the SP kind of bound, and for GV thing, what we did was, 1 second. So for GV we have considered the max, right? Max spheres size. So that we replaced by average, right? So in fact, you can see. Just let me show you the graph. That would be for the lower bound. There was not much of a change. Give me a minute. These are the two lower bounds, not much of a difference that we got, but here we got a significant difference when we, instead of consider the minimum, we consider the average. Thank you.
So we'll ask Professor Lalita again about when we come back.
4:15. So we have a buffer time till the presentation starts. So we are just catching up. If we start at 4:15, that is good. So we have the three talks starting at 4:15. One is a talk by Dilip Dharmappa and Sudan Mishra from ISRO. And then we'll have two online talks, one by Professor Kaldabank and one by Professor Tor Helaseth. And then there is felicitation of Vijay. So please stay back for all. Yeah, finally. Sometime back.
PPT we have to handle from here, same PPT. Half part I will give, half part she will give. You just check. If I call, some sound will come. Yeah.
Okay, welcome. Should we close the doors? Maybe, yeah. Welcome to this final session of the day. Happy to introduce the first talk. The talk is titled Design of Interleaved Z4 Linear Sequences for Satellite Navigation. The speakers are Dilip Dharmappa and Sugandh Mishra from ISRO Bangalore. Over to you.
Thank you. Oh, okay. This is I'm audible? Yeah. Namaste. It's afternoon. So I want to ask one simple question and then start. Who are not using GPS here? We are all using, right? We use GPS, we use mobile, we use location, Swiggy, Zomato, those things we use, right? So this talk is all about how Professor P. Vijay Kumar and our team, myself and Sugandh Mishra from ISRO, Professor P. Vijay Kumar, we three have contributed to our own Indian navigation. This talk tells how we have contributed to our own Indian navigation and what is our contribution, how beautiful it is, and where do we stand. It's like we all know that GPS took its birth around gold code. Means we are all from the coding committee, so coding community. So gold code is the standard what we know. Gold code achieves 2 root n, and we are able to achieve 2.6 root n for the length which is not gold code. It is a typical length where gold does not have the codes, or the most of the coding community codes what are proposed does not meet that length. So that is what the challenge we have solved, and proudly we can tell we are at 2.66 root n. This journey is from a mathematical design on board, textbook paper in this IISc, right from here till ISRO and then to the space, and successfully we are able to receive the signal from last 2 years. May 2023 we were able to successfully launch NVS satellite, and IZ4 codes what I am going to present here are already available in your devices. Apple device it is available, and many other mobiles it is available. I'll just start the thing. I will try to introduce about satellite navigation very briefly. Satellite navigation system consists of more than 3 satellites, 4 satellites to be precise. It is finding out latitude, longitude and altitude. We need 3 things to locate ourselves, and there is one more unknown called time, which is also required to find out the distance between we and satellite. By measuring the distance from 4 satellites, we can solve our own position. That is a fundamental concept. It is called trilateration. Now the PRN, the spreading codes or the PRN codes, where it comes is we need auto and cross correlation properties for the signals transmitted to enable the distance measurement. The system performance is dependent on the auto and cross correlation properties. This uses the code division multiple access, and hence fundamentally this system depends on the codes and the code design. Now these are the internationally available satellite navigation system operational as on Earth today. Like there are only 6 satellite navigation systems: GPS from America, GLONASS from Russia, Baidu from China, Galileo from Europe, Navik from India, and QZSS from Japan. I am here to explain about Navik from India, and also I will tell what we have contributed to Navik. Also, I want to just hint that these are the systems available on Earth. We are also in the process of contribution to the system similar GPS or the GNS. All these systems are called satellite navigation system. Together they are called Global Navigation Satellite System, GNSS. So now, if I want to go on a moon, if I want to go on a Mars, then there also I need GNSS. This GNSS will not reach there. So NASA, ESA and JAXA, they are partnering, and ISRO is also planning to contribute through professor's guidance. We are also planning to contribute to standard which is being made, the same type of GNSS system. Instead of having many systems, single system which will be made on the moon. For that we are contributing. That will be presented by Sugandh Mishra going forward. That will be at the second part of the presentation. So coming to this India's own navigation system, we have named it as Navik, navigation with Indian constellation. It provides civilian signal as well as restricted signal for authorized user. The service area it covers the Indian landmass, geopolitical Indian landmass plus 1500 km around the Indian, it means sea and other things, everything is covered. Now what existed before we started this work is there is a L5 band and S band which was existing signal, and we wanted to explore, means we wanted to come to the mass market. So I'll just tell, okay fine, sorry. The L1 band is the latest signal in the navigation system. In the Navik system, L1 band is the latest signal. Okay. Coming to the spreading code, how spreading codes will help in the satellite navigation system. This system uses code division multiple access. Hence, obviously, the satellite identification. Uniquely, I can identify my satellite. If I have a code cross-correlated, other codes are cross-correlated, then I will be able to tell which is my code. So that is how, with the help of cross-correlation property, I will be able to identify uniquely my satellites. And another thing is, because of the autocorrelation, until unless, like we know the M sequences autocorrelation, until unless they are aligned properly, we will not get full maximum value. Using this property, we do precise ranging. We will know exactly how much this signal, I send a signal, it will go to the satellite, it will come back. Now I will find out, I will correlate in the receiver. If both are matching exactly, then I will know how much this signal transit time. By knowing the transit time, speed is equal to distance traveled by time taken, I will be able to find out the distance exactly. So that is what we do in the receiver. The picture is depicting the time difference. We measure time difference to know the range between me and the satellite. Once we know the time difference, we know the pseudo range, means I know the range between me and satellite. Once I know range between me and satellite with 4 satellites, I will be able to get 4 simultaneous equations. By solving these 4 simultaneous equations with 4 unknown, I will be able to get 4 unknowns very easily. That is my latitude, longitude, altitude, height, and then time. All 4 unknowns I will be able to get at the ground. This is how all our receivers in our mobile and all the GNSS receivers work. Now, there are some desirable spreading code properties which are very, very important. Means to our knowledge, when we see a paper in academia, in the coding community, there are some properties which are seriously addressed, but there are much more properties which are to be addressed for a spreading code to go into an actual satellite navigation system. With Professor's guidance, we were able to have this journey very smoothly. It was, you can just, I'll just explain one by one what are the things required. One particular thing why Navik is in L1 is all our GPS, first when they left the signal in 1960s or 70s, what happened is they sent the signal in L1 band. So from then onwards, all the receivers in the world are available L1 band reception capability. Now, Navik was not there in L1 band, we were there in L5 band and S band, which is slightly away from L1. So to come into the means to come into all the mobiles, to come into the mass market, to have more number of users, we plan to have a signal in the L1 band. Now, what was the challenge when we plan to have signal? What are the design requirements? We wanted to have interoperability. Means my receiver, when it is taken to some other part of the globe, that should work. Then only means I should not change the receiver. That is called interoperability. I should be able to operate with other satellite navigation systems. Then only any chip manufacturer will come forward and they will tell, okay, this is a standard template. I will just add your PRN code and I will make your receiver. So to have that interoperability, we needed the fundamental property of the code, that is the code length, number of bits in the code. This fundamental property was required to be 10230, 10230. And this number is neither 2 power n minus 1 It is neither a prime nor a prime power nor a square of the prime. All these things are usually designed in the coding community. 2 power n minus 1. These kind of lengths are designed in the coding community. Okay, sir. Yeah. Done. So I am already 7 minutes late. So professor said that. Okay. I'll just go to the actual problem. Okay. The problem is all the systems, existing GNSS systems, they were using truncated sequences to achieve this code length 10 to 30, and existing codes, let it be gold code, Kasami sequences or whatever sequences, they don't have this particular length. They were not addressing this length. Now, how does other giants like America, China, how do they achieve is they go to a prime number nearby, and then they take the something called they take the legendary sequence shift and XR. They call it as wheel sequences, and then that will give 2 root n. From there, they come to 4.4 root n in the cross correlation. This is where the existing technology was available, and what we did is we took Z4 linear sequences which were naturally 2046. We used a factor like 10 to 30 can be factored as 5 pieces of 2046. We took 5 2046 sequences, interleaved them intelligently to obtain the full length without any truncation or padding, because of which what we achieved is you are able to see in terms of root n I have put, we are able to achieve 2.63 root n, the middle table IZ4. We are able to achieve 2.63 root n for the cross correlation, second row, while other sequences are at 4.41 root n, and the Welch limits are at 2 root n, if you can tell. Then we are very nearer to the Welch, and this is our design. Coming to the other properties, there are other properties called odd correlation. There is a property called correlation with Doppler. There is a property called interference with the other system. I should not interfere to the existing system, existing GPS. I should not interfere. So all these properties were computed, and we can see in the box clearly 4.41 root n versus 2.63 root n. For us in the communication in our offices, what we tell is in dB we will tell, okay, 3 dB improvement, 6 dB improvement. What we got is 4.2 dB improvement we got, and that's a huge one. So that is adapted to the Navig satellite system. These are the other properties. There will be a natural Doppler between your code and means your receiver and the satellite. There will be a Doppler. For that Doppler, when we apply the Doppler, the code properties changes. You can see the green color in that graph, which is very, very low. You want as low as lower correlation. So our IZ4 codes were able to achieve the lower correlation, and we were having interoperability with other system. With GPS, we were able to have 24 dB correlation. So that was also we were able to achieve. So coming to the since 2019, we have the collaboration, and with professor guidance, we are able to pull out this design. This is the starting 2021, where ISRO, after this design, we had both ISRO and IISc, ISRO chairman and IISc director had a meeting, and these are the snapshots of that meeting to commemorate the success that what we have achieved with respect to 4.4 dB, 4.2 dB, whatever success we were able to achieve, and we were able to use it for our system. Then the actual satellite was launched in 29th May 2023, first satellite. Now 2 satellites are available. Now going forward, all possible NVS series satellites will be having the signal, and naturally IZ4 sequences will be there inside that. And the second image is we have Vijay Kumar sir behind our ISRO chairman Somnath sir, and the first one is Sivan sir, ISRO chairman, and we have ISTRAC director and other colleagues, and we had in 2024 we had at SAC we have SAC director. We had MOU, we have 2 MOUs, and we have 1 patent, and we have 2 more patents in line. These are some snapshots. So professor gave one talk that is there in the last one. In the SAC Ahmedabad, professor gave one talk. Hardware architecture will be explained by my colleague Sugandh Mishra. Sugandh madam, you are available?
Hello, this is Sugandh Mishra from Space Application Center. Am I audible to everyone?
Yeah, you are audible.
Thank you, Dilip ji. Would you be able to change the slides, or shall I share screen from here?
I'll change it.
Okay, thank you. Great. Hello, everyone. And it's an honor to speak on such an august gathering, in front of such an august gathering. And I'll discuss the practical aspect that take and signal design mathematically developed to the sky. So first I'll discuss about the hardware architecture. Any IZ4 code or any PRN code is available as a code generator in any GNSS receiver. So hardware should be easy to implement, as well as it should have used very less number of FPGA resources. So we developed three different architectures. A quaternary shift register based architecture, which has 5 G4 linear sequence generator, followed by an interleaver and a flipper. Then we came on an intelligent design, which is binary shift register based. So we use two binary shift register with a 5-bit flipping register, and it is a gold light architecture. All the receiver manufacturers have liked it, and then we have adopted it as a part of our interface control document. Similarly, for the secondary or the overlay code generation, we have used a secondary shift, a similar kind of architecture using the kind of shift register. Next, please. Yeah. Now, once the code is designed, next step is to qualify it. Because taking any design into space is a huge responsibility, as the same signal is going to be there transmitted by NAVIC satellites for the upcoming 10-20 years. So the responsibility is to validate the design before we start the transmission. For this set, we have developed a NAVIC L1 simulator which mimics the live sky condition, generates multiple satellite signals with L1 signal, and we tested it with in-house developed L1 receiver. We acquired the IZ4 codes for all satellites, get the position on ground, and once we confirm that, okay, this is working correctly, then an evaluation committee has rigorously reviewed all the mathematical design properties of this IZ4 code. And once all these 6 months of evaluation has passed, then we adopted IZ4 codes into the NAVIC design. Next slide, please. Yeah, so there was a ISRO IISc level meeting where we have shown that, okay, as India, we are self-reliant, Atmanirbhar in the domain of the coding theory, and we can produce our own indigenous codes for our own indigenous navigation system. Since then, IZ4 codes are being continuously transmitted from NVS-01 and 02 satellites, and in future, all upcoming NAVIC satellites with L1 signals will carry the IZ4 codes as PRM codes. They are continuously monitored and tracked by ground stations, and as well as in the mobile chipset, we have seen the support for NAVIC L1. Next slide. So whenever we transmit any signal through the satellite, we create an interface control document, publish it on ISRO websites for the public availability, so that any GNSS or NAVIC receiver manufacturer can download this document, understand the algorithm, signal architecture, and various aspects of this signal, so that he can make a receiver for it. Thus, IZ4 codes have become part of this ICD and section number 4. You can download it from ISRO website. And this table that I am showing, it's describing the architecture of IZ4 codes for NAVIC L1 data and L1 pilot signal. Next, please. Yeah. So, since the concept of NAVIC since 2008 and 9, when ISRO has started working on NAVIC, and now in 2025, there is a wide difference in the availability of NAVIC in the user market. Now there are multiple chip manufacturers which are providing support to NAVIC signals, including L5 and L1. There is a latest iPhone 17 has a NAVIC signal, Google Pixar has NAVIC signals. Then there are multiple phone companies that they are adopting NAVIC L1. So use of L1 has increased the adaptability of NAVIC and adaptability of NAVIC in receiver system. Next, please. But our collaboration with Professor P. Vijay Kumar and IISc in general has not stopped at the design of IZ4 codes only. We are continually working with him, and we have designed on multiple things. Like Currently, we are going on a mission-focused research project through IISc. It's a 1.5-year project. Under this project umbrella, we have generated codes for lunar PNT, which I'll cover in my next slide. Then we have generated not just one or two, we have generated 6 binary and 5 quaternary families. All are relevant to GNSS nodes. If you see the lengths 5115, 2046, 844, 7161, 10230, these all are being utilized in different GNSS signals, some in GPS, some in Galileo, some in BDS. Why we have developed all these many families? For potential exponential use of in future NAVIC signals, we are planning to expand NAVIC to a MEO constellation maybe, and there may be more services. So we have created a code bank that is useful for NAVIC and not NAVIC during by a suitable agreement. Maybe we can offer these to other agencies as well. Next, please. So in this slide, I would like to summarize what we have been together during the past 5-6 years. So in 2029-2020 timeframe, we have generated the IZ4 codes, which are taken very positively by both IISc and ISRO management, and created a groundbreaking signal design in GNSS community. Then we have developed another set of IZ4 codes with a slightly different variation for future NAVIC SPS signals. Then 2023-2024, we have developed a CSPRNG kind of design, a cryptographically secure PRNG design, which is kept as a potential candidate for future application. Then in our mission-focused project, we have designed multiple, not just binary, but quaternary PRN codes as well for GNSS community. Now, our recent design effort is designing binary PRN codes for lunar PNT. And I hope there will be many signals that will follow with our continued collaboration. Next, please. Now, what is lunar PNT and what is lunar net? So, as the name suggests, lunar PNT means providing position, navigation, and timing services on lunar surface. Along with PNT, there is a plan to provide communication services as well. So, when the GNSS system has come on Earth, every country has their own version, which are often not that interoperable. But now, because the design has been so mature, all the countries have come together to make a network of interoperable and cooperating networks, which is called as LunarNet. You can understand it like lunar internet. So NASA, ESA, and JAXA, they have collaborated together and they created a LunarNet, a lunar internet. So the main aim here is to provide communication and PNT services across the moon and beyond. Every country has their own instantiation of LunarNet nodes, like JAXA has LNSS, then ESA has Moonlight and LCNS, then NASA has Lunar Communication Relay Navigation and Systems. Now, because all these the systems are collaborating, so the signals they are generating, they are interoperable in nature and they work together. Next slide. So for that, they have come up with an Lunar Augmented Navigation Service. And under this service, they have designed an interface standard. So any country, if they try to put their satellite across moon, and if they want to participate in lunar PNT, they should adhere to these standards. These standards, when the standard was being crafted, it captured our attention. And we have seen that we saw that time that there is a scope for code design there. In the draft version, they have only specified the length, but they have not specified the code family. We took this opportunity and designed code for it. Earlier, the code length for the I signal was 1023 and for Q signal was 5115. So we designed a code set for it and presented in the ICG, which is an international committee for GNSS service providers. Then in January 2025, they have provided the final version of the standard, where they have decided the code length to be 2046 and 10230. Luckily, we have covered all the lengths. So we have a design for all these lanes. Next, please. So IZ42, that is 2046 lane code, is our proposal for lunar PNT signals, which we can say it's India's signals or India's contribution to the lunar PNT signals. It's an indigenous design. It's a very simple shift register based design. And one shift register based architecture can generate not one or two, 512 ports just by changing the initial conditions. Next, please. Now, for IZ410, for 10230, Mr. Dilip has already covered the properties, how good the design is. I'll cover IZ42. Now, if you see the IZ42 even correlation, odd correlation properties, we have compared it with respect to the BDU navigation system, that is BDS. It's B1 signal because B1 signal has the same code length of 2046. So our code performs in the worst case scenario, non or 2, up to 8 dB better than the worst case scenario of the BDS signal. And now, in real case scenario, it's not always the worst case scenario that come up. There are average scenarios as well when the signal is received by the satellite. So we have calculated the percentile numbers, RMS numbers, and in all the parameters, our codes are performing much better than the BDS signals and comparable to better than the truncated gold codes which have been chosen by the current AFS standard design. Next, please. So for this work, we have granted one ISR, joint ISRO-IISc Indian patent, which was granted to us in 2020. We have also filed a PCT for the same. Then for our recent efforts after the IZ4 course, for the 6 binary and 5 quaternary families, we have filed another complete specification of an Indian patent on very recently on September 2025. Now we have done one more work that is not covered in the presentation. It is interleaved gold design, which is we are still doing it. We have filed a provisional Indian patent for it very recently on October 2025. Next, please. The publications, I have shared the links in the presentation. If presentation is available to you, you can download. So we have presented initially in ISIT 2021, then IEEE Transactions on Information Theory, a much more detailed paper. There is an archive paper which deals with the IZ42 design. Then in the ICG, we are regularly presenting our work as a status update. We have presented ICG 2021, 2024. So that's all the presentation publications that we have done till now. Next, please. Now, any great work cannot be accomplished without the encouragement, support, and guidance of so many people behind it. I would like to thank some of them here on this platform. I would start with former ISRO Chairman Shri A.S. Kiran Kumar, who has taken interest in our novel design and supported us. Then Director SAC Shri Nilesh Desai, who has been instrumental and very supportive to us since 2019. He is also a co-PI in some of our work. Then Director IISc, Shri Rangarajan sir. Now Director ISTRAC, Dr. A. Anil Kumar sir. Then our SatNav Communication and Navigation Program Office Director, Dr. Manish Saxena. CBPO at ISRO, IPTEL and IISc. Senior administration at ISRO scientists who have taken part in the evaluation of the design, who have taken their suggestions to improve the design. Then senior administration at IISc and IISc faculty who have helped us in signing the MOUs and then creating a JPIP, managing the funding. We thank all of them for allowing us, for supporting us to do this good work. We believe we continue to serve our nation through our design. And I would like to thank Professor P. Vijay Kumar also for guiding us throughout this journey. Next slide.
Okay, thank you.
Thank you.
The speakers' presentation. Thank you, sir. Thank you, madam. We are a little out of time. I think, is it okay if we proceed? No questions? Maybe you can ask questions later on. Okay. Thank you. Thanks a lot. We're going to move on to the next talk. Can I hear from Rob? Rob, are you there?
Yeah, you can.
Oh,
Here I am.
okay. Hi, Rob. Good
Hi
morning.
there. Would you like me to share my slides?
Yes, can you do that, please? And maybe even
I'm going to
log
try.
on if that's okay. Yeah, we can see you. Yeah. In the meantime,
Looking
I'll
good.
briefly introduce the presenter. Professor Calderbank needs no introduction to this audience. I'll just say a couple of things about him. He won the Shannon Award in 2015. He's a member of the National Academy of Engineering, American Academy of Arts and Sciences. Currently, he's a distinguished professor at Duke University. And he's giving a talk on a very, very interesting topic, seniority as an advantage. Over to you, Rob.
Okay, thank you very much for the very nice introduction. Let me just check. Can you all hear me?
Yes, yes, very well. Please go ahead.
Very well. Okay, good. One of the advantages I think of getting old is that you feel that you're entitled to talk about seniority as an advantage. And the other thing that I'd like to say about the talk is I'm going to talk about wireless communication, and I want to emphasize the connection with India. In fact, in the second part of the talk, I'm going to be talking about joint work with Sandesh Mathu, who came to me from IISc, student of Chokalingam. So I have a great appreciation for IISc. George Ordwell had something to say about seniority. And this is a slide where I've looked at the progression of wireless standards. So we have a new standard every 10 years. And we have in the past changed waveform. So we changed waveform from TDMA to CDMA and then to OFDM. So we do make changes. And the context for my talk today is 6G wireless. And I'm going to talk about the advantages of signaling in the delayed Doppler domain. And so I'm going to be talking about choice between different waveforms. And I don't want you to think about this choice as I like this set of wiggles better than that set of wiggles. I want to think about the choice between delayed Doppler signaling with ZAC-OTFS and OFDM as an architectural choice. The choice is between preventing ISI or intercarrier interference through carrier spacing, or embracing and acquiring that interference. If I were to tell a story about a different technology, I would tell it about data storage, where in the early 90s, we had magnetic disks, we wrote in tracks, and we spaced transitions far enough apart so that they didn't interfere. As time went on, we needed more and more data on our computers, and we could no longer prevent intersymbol interference. We had to put them closer, the transitions closer together, acquire the intersymbol interference, and equalize. And I can guarantee you that none of your laptops has a storage technology where you've prevented ISI. And maybe the same will happen for wireless. So here's the plan of the talk. I'm going to tell you a little bit of background about delayed Doppler signal processing, and then I'll just conclude with 3 applications. And so here, one of the pillars of 6G is supposed to be AI and machine learning. And the point of this slide is that today we design wireless systems using mathematical models. So we estimate channels. But as channels become more complex and Doppler becomes more significant, you can ask the question, might it be possible to operate in a different way, model-free? And I'll try and explain what that means. And so here, how do you think about a wireless channel, a doubly spread channel? Well, you send a signal, X of t here, and it arrives at your phone, the user equipment, UE. It gets there by bouncing off different reflectors. These reflectors, if they're not moving, they just introduce a delay. If they are moving, they introduce a Doppler shift. And that's shown in the cartoon on the right-hand side here, where the signal X is shifted in delay and shifted in Doppler, and it's attenuated a little bit. That's the height of the columns. And if I were to make try to make a difference between the model-dependent perspective and the model-free perspective, I would say this, that in model-dependent perspective, you're trying to estimate physical channels. In the model-free perspective, you have an input-output relation that tells you how the input and the output are related. In the ZAC-OTFS modulation, they're going to be related by convolution. So it's going to be just like an LTI channel. And the idea here is that you don't care how the I/O relation, how the effective channel happened. You don't need to sort that out. All you need to do is to acquire that. That's what I mean by model-free. So we're making a distinction here between physical channel and the effective channel or the input-output relation. I'm trying to say that what is important is the interaction of the physical channel and the modulation you have chosen. And the carrier for ZAC-OTFS is a pulse in the delayed Doppler domain. And so it's really a radar waveform. And here I'm going to go back to 1953 and Philip Woodward, who 5 years after Shannon's publication on communication, wrote about information theory and how it relates to radar. And he had this wonderful idea that you should think about radar as a game of 20 questions with an unknown operator. So the idea is that a question is a waveform you send out into the void, and an answer is a return, a radar return. And by correlating what you transmitted and what you received, you learn about the scatterers in the radar scene. How should you design a question? We're going to be talking about this waveform in the time domain, which we call a pulsone because it's a pulse strain modulated by a tone. So what constitutes a good question? Well, you guys teach signals and systems, LTI channels, pure delay channels. You want to send a pilot, you send a time domain pulse. You wait for a little bit, you acquire the impulse response, then you equalize. What should you do with radar? What should you do in the delay when you're trying to map scatterers in the delayed Doppler domain? Well, the suggestion is that you use a pulse in the delayed Doppler domain. You used a pulse in the time domain for LTI channels, pulse in the delayed Doppler domain for doubly spread channels. Now, when you ask a question, what constitutes an ambiguous answer? Well, how do radars work? You send a signal S, you get a received return, and now what you do is you correlate that return with shifts in delay and Doppler of the signal you transmitted. Those correlation values give you the ambiguity function. So radar is all about ambiguity functions. And there's an identity due to Moyal which says that the volume under the ambiguity function, you can't do anything about that. What you can do is you can move the ambiguity surface so that targets become visible. And that's what radar engineers do. Now, when your question is a tone or a chirp, your ambiguity function is a line. What does the line mean? It means you're looking for a target, and it's somewhere on the line, you just don't know where. Now, what Woodward did in 1953 was to start off with a chirp, or in this case, a narrow Gaussian pulse, which has an ambiguity function which is a line. And he said, you know, that a line doesn't give me very good resolution. So what Woodward did was to look at a train of narrow Gaussian pulses modulated by a broad Gaussian. And what he showed is that the ambiguity function transforms from being a line to being a lattice. And lattices are much, much better for detecting targets because you can actually, they're much, much better for detecting multiple targets. You know, if you have multiple targets and they live on your ambiguity surface, which is a line, you're not telling them apart. But when you're a lattice, it's much easier. So, all right. I have to say a little bit about how we're going to make signals. We're going to make signals in the discrete delay Doppler domain. I'm going to tell you a little bit about the signals in a minute. We're going to apply shaping filters, transmit filters. We're going to move to the time domain. We're going to transmit in the time domain. We're going to do match filtering on receive. And we're going to bring signal processing back to delay Doppler. So those of you who are physicists will say, but you can't have a pulse in the delay Doppler domain because that violates Heisenberg uncertainty. And indeed it does. So we're mathematicians, so we cheat. How do we cheat? We make quasi-periodic functions. So what happens here is we say, you're a communication engineer. You know your worst case Doppler spread, you know your worst case delay spread. My modulation is defined by two parameters, tau p, which is the delay parameter, and nu p, which is the Doppler parameter. I'm going to live with the fact that the product of tau p and nu p is 1. So my signals are going to live on an ellipse, a parameterized family of signals that lives on an ellipse. Because, you know, we say that, okay, you don't know exactly what your channel is, but you know the worst case. You know what your Doppler spread is, you know what your delay spread is. And we make a pulse inside that square in the middle of the slide. And then when we move by tau p in delay or nu p in Doppler, we introduce a phase. So our pulse in delay Doppler, it's quasi-localized in that central box, but it's not improperly localized because it's supported on the entire plane. And now, of course, we don't transmit signals in delay Doppler, we transmit them in the time domain. How do we get to the time domain? We get there using a transform, the Zach transform. And I've shown you the time domain waveform. We do pulse shaping. The width in Doppler is 1 over t. The width in delay is 1 over b. So this little pulse takes up area 1 over bt. How many pulses do you have? Well, you have bt pulses. That's the time bandwidth product. And so what I'm describing really is a basis for signals that are limited in bandwidth to b and limited in time to t, which I think is nicer than the prolate basis. The offset tau 0, so the pulse train, the pulses are separated by tau p. Tau 0, the offset in the box, tells you about the offset of the pulse train. The offset in Doppler, nu 0, tells you about the modulating tone. There you go. And, you know, this waveform looks actually quite a lot like Woodward's waveform. And the ambiguity function has the same characteristics. So this is a waveform that you can use for transmission, and you can also use for sensing. Integrated sensing and communication is one of the new things in 6G. So the you know, how do you when you're using it as a radar, you start from the resolution that you want, you work backwards to the delay and Doppler period, and then this is your radar. All right. Now, what's special about this modulation is that here on the left-hand side, I've sent my pulse. What I get at the receiver is a collection of replicas. And the replicas are related to the original pulse by the scatterers they encounter on their way to your phone. This condition that the delay period is bigger than the delay spread and the Doppler period's bigger than the Doppler spread implies that the modulation is predictable. What that means is if you sent a signal any other place, if you sent a pulse any other place, you get the same collection of replicas. So you can send one pulse, one pilot, you can acquire the channel for all of the carriers. And so that's what I mean by embracing interference. This is a picture of the transmitter. The important thing is that there are inputs X, there are outputs Y, and the relationship between the two is given by convolution. It's not quite convolution in the LTI sense because there are phases, but morally speaking, it's the same. And this modulation is the only modulation that has that property where you can read off the effective channel. Now, those of you who teach signals and systems, you teach aliasing. And what I want to do in the next couple of slides is to just tell you, when we think about wireless communication, we think about time selectivity or frequency selectivity. And what I want to describe in these slides is how these phenomena are related to aliasing. So here, we're aliasing in Doppler. So this light purple ellipse, think of that as the physical channel. And think about being in the dark purple area. And so if you're in the dark purple area, you're actually experiencing two replicas of the quasi-periodic function. The signal that you receive is a linear combination of two variables. If you weren't purple, if you were green, if you were another time, so you moved along the delay axis, you'd be dark green. The signal you receive would again be a linear combination of two variables, but your selectivity means these two linear combinations are linearly independent. You can't predict one from the other. That's what time selectivity is. So Doppler aliasing gives you time selectivity. If you don't have aliasing, you're flat. You don't have selectivity. You have this kind of picture. So aliasing in Doppler, time selectivity, aliasing in delay, frequency selectivity, no aliasing, beautiful flat channel. What you've engineered is a two-dimensional Gaussian channel. And you see, for those of us who are old, we remember coding for Gaussian channels. Here, the model-free business, what we've done here is we've chosen a channel where we actually don't have enough time or bandwidth to estimate the channel. We just read off the I/O relation and proceed on that basis. What this picture shows is that operating model-free is actually fairly close to operating with perfect CSI. All right, now let me tell you some things you can do. First of all, coding. I've just engineered you a perfect Gaussian channel. Now, we actually spent the 90s figuring out how to reach capacity on the Gaussian channel, LDPC codes. And so here's a picture of SACO TFS versus various flavors of OFDM with perfect CSI, with diagonal CSI. OFDM doesn't give you a perfect Gaussian channel, so you do a little bit better with SACO TFS, and also you're more amenable to techniques like shaping, differential communication. In the early 2000s, when people, and Vijay was one of these people, thinking about multiple antennas, people thought about differential communication. How does that work? Well, in frame 0, you transmit a pilot. You estimate the channel. In frame 1, you transmit data. You decode the data. You use the decoded data to re-estimate the channel. Keep going. Every so often, you insert a pilot frame to control error propagation. So this is this picture shown here. And the point of this slide is that you can do exactly the same thing with SACO TFS. At each frame, there's a correlation calculation that you can do that reveals the effective channel. And because the effective channel only changes at the speed of the reflectors, you can go a long number of frames. And so in the middle, you're just sending data. You're not sending pilots. And so you have an opportunity to save energy at the transmitter, for example. There we go. And now I want to just conclude by talking a little bit about discrete radar. So when I was talking about chirps before, or tones, chirps, FMCW is a chirp. Continuous radar, there's a certain, you're doing these continuous cross-ambiguity calculations. Discrete radar, we're going to bring everything back to discrete delay Doppler. And so we're going to have M delay shifts and N Doppler shifts, and we're going to work modulo Mn. And we're going to work modulo Mn, so we're going to work modulo this little Heisenberg-Weil group of delay and Doppler shifts with M delay shifts and N Doppler shifts. And it's a beautiful group. In a sense, what I've come to think of in groups is that there's only one group. It's the Weil-Heisenberg group. It appears in quantum as the Pauli group. It appears here as shifts in delay and Doppler. And what is the advantage of discrete versus continuous? So in the continuous world, you have a chirp. Your ambiguity function is a line. When you do cross-ambiguity calculations, complexity is order b squared, t squared, where b is the bandwidth and t is the time. When you have discrete radar, and you think about the self-ambiguity function, you sent a pulse in delay Doppler, you shift it in delay, you shift it in Doppler, you take, you correlate, you take it in a product. Most of the time you get 0. You only get something non-zero, something with value 1, when you shift by m, shift by the delay period, or you shift by n in Doppler. And so your self-ambiguity function is supported on a lattice. It's like a bed of nails rather than a line. And if you're looking for multiple targets, this is a big advantage. Now, there's another advantage of designing your waveforms. And so you, so this was this discrete thing. We are going to reduce computational complexity by designing waveforms that are common eigenfunctions of maximal commutative subgroups of the Heisenberg group. So this is very like quantum, where we use commutative subgroups of the Pauli group to design codes. Why would we do that? Well, think about calculating. So when you calculate a cross ambiguity, it's like you're evaluating an inner product. X, shift, X. Now, if your X is an eigenfunction of a commutative subgroup, when you apply a shift from that subgroup, all you do is introduce a phase, and then that phase cancels. So there are many of these calculations are the same. If you're in the same coset of the commutative subgroup, it's the same answer. You don't have to do it. And that's why you can reduce the complexity. And it's a significant reduction in complexity. So, conclude. The idea of using a pulse and delay Doppler is that you're predictable, and predictability amplifies the value of machine learning algorithms. They like to see things that are predictable. If you can buy time, you can do a better job scheduling. Actually, something I didn't talk about was you can also do grant-free multiple access on the uplink in the presence of mobility and delay spread. Integrated sensing and communication, I haven't gone into many details, but the idea is because you're communicating with a radar waveform, it's easy to integrate sensing and communication. So perhaps I should stop there and wish Vijay all the best, and to thank you all for attending my talk.
Thanks, Rob. Let's thank the speaker. We have time for maybe a couple of comments or questions. Anyone? Any questions?
Hi, Rob. Thanks for the great lecture and also for getting up early in the morning to make our time. Appreciate that. Thank you.
Well, thank you again for the invitation. And I actually loved the previous talk. I would very much like to get the slides.
Yeah, I think we'll share some version of that with you, Rob, for sure.
Okay, thank you very much.
Thank you. Thanks a lot for your time. Let's thank Rob once again.
All right, gotta go to the airport. Take care. Bye-bye.
The final speaker in this session is Professor Thor Helleseth. I believe he is online as well. Has he joined? Okay. Thor, can you hear me?
Yes, I can hear you.
Oh, okay. If you can share your screen and get started.
Yeah, I'll share my
do that. Okay.
See on my screen, yeah.
Okay.
So here, yeah.
Professor Thor Ellis has been a frequent visitor to IISc. I think almost everybody here knows him. He's also picked a very interesting topic. Topic is just Vijay, friend and collaborator. So we're going to hear on that topic from Professor Thor Ellis. Thor, take it away. Please go ahead.
I can't see so much. Oh, can you see my screen?
Yes, we can see your entire screen. I think if you
Okay.
click on your
But I'm trying to see my screen, yeah. Oh no, this was not exactly. Oh, sorry, I think I need to.
You can reshare also. You can you can stop sharing and reshare again.
Yeah, I stopped. Okay, so I stopped sharing. So I'll just look at this one and maybe make this full size on this one, full screen mode.
We can see your slides now, Thor. Go ahead.
No, you can see my slides. Okay.
Yes, yes.
So then, even if you change it, you can see the next slide now.
Yes, yes.
Yeah.
Please go
Okay,
ahead.
then I will have the pleasure to, and I feel honored by inviting to give a talk in connection with Vijay Kumar's 7th birthday. And as you see, the title will be quite non-scientific partly, but it will be a mixture of scientific and non-scientific part. So actually, we also have a couple of pictures, and the first picture actually it's a picture of the speaker or me here, and the speaker and the VDA, and actually in the middle we found a statue of a very famous Norwegian. This is Roald Amundsen. He was the first person on the South Pole about 100 years ago. So we are in good company. He was a polar explorer, so he was different from our field. I will start with saying a little bit about the history behind the collaboration between me and VDA. And then I found another picture. So this is again me, and this is VDA. This is taken about in 2017, I think. And in behind we have Solomon W. Golom. And in a way, he was like the connection point why we started to work. And the reason for this is the following. Sol Golomb, he is a great pioneer in sequence design. Since this is a conference on sequences and codes, he's probably very, very familiar. And in Bergen, we also had a famous professor that was on sequences. That was Ernst Selmer. He wrote this book in the 60s on sequences. And Sol Golom, he wrote a book on shift register sequences approximately at the same time. So in the 60s, these were the main books in coding theory, except that this Golom, this is the 3rd edition. So this is actually published in 2017. And they are both experts in number theory. They are experts in coding theory and in crypto. And of course, Golom, he worked at the APL, and he did a lot of work, and he got a big prize, the Medal of Honor by Obama about 10 years ago. And he also got the Franklin Medal. That is that about 100 people with the Nobel Prize has also won that medal. So he is extremely famous for his contribution to sequences and sequence design. And the story or the connection is that Sol Golom, he was a Fulbright scholar in Oslo, in the University of Oslo in 1954 to 55, and he worked with one of the professors there, Ernst Selmer. And Selmer, he came to Bergen, and he became my supervisor for my master's and PhD. In 1970, Golom visited Selmer to give a guest lecture, and he gave a talk on cross-correlation of M sequences, or maximal length sequences, which is quite famous in sequence design, very, very useful. And Selmer liked the talk so much because Golom presented some open problems, and Selmer suggested to me, as a master student, that I should write a master thesis on this problem, on the cross-correlation between M sequences. So I started on doing this one, and I got my master's, and I continued as a PhD student on the same problem. And because of the good connection with Solgolom, when I was a PhD student, I was very lucky to get a sabbatical leave. And because of the connection with Golom, I was there in 1977 and 1978. I should mention that Vijay, he actually came to USC as a PhD student. He was a PhD student of Scholz. And Vijay came there in 1979, so I just missed him by 1 year. But still, I made a collaboration with Vijay, and I first had a sabbatical in USC in 1977-78, which was a fantastic place for sequences. They had 3 Shannon Award winners in the same floor that I was working as a student. So I was really impressed by the working research environment at that time. And Vijay, as I say, came to USC in 1979, and he completed his PhD in 1983. So the first time I was able to meet Vijay was at the IEEE Symposium on Information Theory that was held in Saint-Jovite in Canada. And of course, we had a lot of research interest on sequences and codes, and actually Vijay visited me in Bergen some years later, about 1990. And my next upcoming sabbatical for me was in USC in 1972. And Vijay was, he got a permanent position at USC. And I also had a sabbatical there in 1988. So I worked a lot with Vijay in these years and for many years to come. And we became very good friends and had a very interesting working relationship. So when we started working there, I remember we had the first discussion, what should we work on? Should we work on sequences or should we work on coding theory? The first thing we actually did was a project on encoding theory, because one of the hot topics in coding theory at that time was the weight hierarchy of codes that was came up on the agenda a few years ago. So we wrote a couple of papers on this very quickly in the beginning. And of course, the importance of this was to estimate the complexity of trellis decoding of block codes. So for this reason, there was a lot of interest in this at that time. But the things we actually started working quickly on was sequences and codes over C4. And the motivation for this was that, okay, so when we written these coding papers, then Vijay told me about some recent work they had done at USC that he has done with his students. First, a year before I came, or actually the same year as I came, they published a nice paper with Bostas, Hammonds, and Kumar on 4-phase sequences. And some of this work was extended in the PhD thesis of one of the authors, namely Roger Hammonds. And actually, the thesis was a very good thesis. Among other things, he came very close to the solution of a 20-year-old open problem, which was about the duality of the nonlinear Kurdoc and Preparata codes. The Kurdoc code is nonlinear, the Preparata code is nonlinear, but somebody had discovered, actually Victor Zinoviev, that these codes obeyed the McWilliams identity, but McWilliams identity was only true for linear codes. So this was a mystery for 25 years. And when Roger Hammonds were supposed to write down the thesis, among other things, this famous result, the 3 other researchers, Robert Collebank, the previous speaker, Neil Sloan, and Soler, independently discovered similar results about this duality, approximately at the same time. And of course, typically when 2 groups of people find the same result, you can have a lot of fighting who were first, but they decided to, since they were approximately at the same time, they wrote a joint paper. So actually you see that I think the only thing that they discussed was, without any problems, was that the first author was Hammonds and then Kumar, and then the other 3 group is is there. And they made a very nice joint paper. It was submitted to the IEEE transaction on information theory. And the interesting thing is that I knew the results because of before some of the authors, but because Vijay told me about this result before it was rediscovered. At that time, I was also the associate editor of the IEEE transaction for the coding theory, and actually the editor on TP wanted me to handle the paper. And I remember telling him that, well, I'm sabbatical, I'm sitting in the office next to Vijay, so maybe I'm too close to the authors. But he said that this paper will obviously be accepted, so I want somebody that knows the work to be able to polish it. So I sent it to very good referees, and the paper was of course accepted. And actually, one of the referees actually nominated the paper for a prize. And this paper won, published in 1994 by Hammonds, Kumar, Kola, Sloan, and Soler. They won this 1995 IEEE Prize Award, or IEEE Information Theory Prize Paper Award is probably more the correct title on this one. And this paper suggested many open and interesting problems related to coding and sequence design. And for this reason, I was also very inspired to continue working on some of the open problems that followed after this paper, and I worked together with Vijay on these things. I'll say a little bit about the status on sequences at that time in the 90s. I'll just give a crash course on, very simple course on sequences node. So I just give you a little bit background on the sequences. So there was a lot of sequence families at that time: the gold sequences, Kasami sequence, Kurog sequences. There was a family A sequence, and this one in last in red is one of the family of sequences we discovered at that time. If you have an M sequence, this is just generated by linear recursion. You start with, in this case, you have a linear recursion of degree 3, st plus 3 st plus 1 plus st, which means that if you start with 3 bits, and then the recursion will say that the next bit is the sum of the 1 2 units ago and 3 units ago. So the sum of these two is this 1, the sum of these 0 is this 0, etc. And this will be a periodic sequence with length 7. It cannot be longer than 7, because if you start with 3 zeros, you get zeros forever in recursion. So if you start with a non-zero, the longest period you can get is 7 before things repeat. And these sequences is called M sequence, and you can find them for all n. And actually, I'll give you another one. This is one recursion in the previous one. You can associate a polynomial to this one, and this polynomial is called primitive. And for primitive polynomials, you get M sequences. The other one is a decimation of this sequence. If you take every third term in this sequence, 1, 1, 1, 0, 1, and then you get 0, 0. So in a way, so you have a lot of M sequences, and what you try to do is you can use this as building blocks in many communication systems, and it has been used infinitely in many applications. And some of the basic things on sequences, you have it for all lengths of form 2 to the n-1. So this is one of length 4. So this is the linear shift radius that generates it. It's always balanced. The number of zeros are the same as the number of ones, except for a missing 0. And it has some called a run property. So if you look at consecutive zeros and groups of consecutive zeros and say consecutive ones, these numbers are usually the same as long as the number is bigger than 1. And every time if you have an M sequence, you decimate it by D, you get another M sequences. And as I said, I worked on these problems to find a cross correlation between these. And what is the correlation? Well, if you have two sequences over a period, you define the cross correlation between the sequences, but by just counting shift the one sequence by tau and the other one you don't shift, and then you compare the sequence A shifted with the sequence B, and you count the number of agreements minus the number of disagreements, which is the same as this formula here. And if the sequences are the same, the autocorrelation. The famous thing is that if you have M sequences, the autocorrelation is perfect in the way that if you compare the sequence with the shifter itself, you get 0, and otherwise you get with the shifter itself, if the shift is 0, you get 2 to the m minus 1, the length of the sequence. If the shift is out of phase, you get -1. And of course, there is a lot of application of these sequences, and it's just. But as a mathematician, I'm mostly interested in the mathematical aspects. And actually, I think my first paper I wrote on these sequences was from 1976, and the last one on the cross correlation was from 2023, I think. So there are still many open problems there. But one of the things that you can use it for is to find good sequences with good correlation, so you can find a lot of sequences that you can use from CDMA. So if you have a family of big M sequences, you call the sequence ST, to number it, you put an I subscript there. So this family consists of cyclically distinct sequences of the same period N over an alphabet with Q symbols. And then normally if you have two binary symbols, then when you compute the correlation, you'd use -1 and compare the shifts of to see if you have an alphabet of size Q, you replace -1 by a primitive Q root of unity, and you define the correlation in this way. So you look at all possible shifts of one sequence with all possible shifts of the other sequence. And you look at the maximum correlations you can have, except then when the sequences are the same and the shift is shift is 0, because then the correlation is the same as the length. But in the other case, you want the maximum of all the other correlation comparisons to be as small as possible, and this has practical reasons. You need a max to be small to ease the synchronization and to minimize the interference between the users, and then you have the size of this family tells you how many users you had. So in the old days, you didn't have as many users, but as soon as mobile communication exploded, you need much more users than you needed, and in modern system that used to be the problem. And if you go back to the history of this one, the most famous family of sequences is the gold sequences. Then you just take an M sequence of length odd of length n is 2 to the -1 when m is odd, and you take a decimated sequence which of the same period where the decimation is 2 to the k plus 1 when k and m are relatively prime. And then you take the family consists of both of the sequences plus one of the sequences with all the shifts of the other. So you have 2 to the n -1 shifts, and then you have the two other sequences. So the size of the family is the 2 to the n plus 1, which is the length plus 2, and the maximum correlation. This was computed by Gold in 1968, published in the IEEE transaction. So this was one of the first papers I read as a master student in this way, and this was a nice mathematical proof of this thing. And this has many applications. This is in the GPS system. So this used to be the family of sequences to use as one of the building blocks. There was another family of sequence that was popular. That was one by Kasami. And then you took an M sequence of length 2 to the m -1, and m was 2 times r. And then you took a decimation 2 to the r plus 1, and then you took the decimated sequences of shorter lengths, and you kept this sequence, the long sequence, and the long with all the decimation of the short one. And then you get this, the number of sequences were much smaller. They were 2 to the r. So this was like the square root of the size of what you had for the gold sequences, but the correlation was better. But in a sense, you could show that this one was optimal for given M and N, and similar, the gold sequences were optimal when things were M. In the end of the 80s, or maybe around then, someone constructed families of sequences over C4. And then you could take an M sequence, primitive polynomial, and you could lift this, what you call Hansen lift. So you took the binary polynomial f of x and binary polynomial minus f of minus x. And now you consider you multiply this together and you forgot that the characteristic was 2. You computed modulo 4. And then you get this polynomial, which is a polynomial with all the exponents are even. So if you divided all exponents by 2, you got a nice recursion and modulo 4 that looks like this. And then this will generate 4 to the M sequences over C4, because you have M flip-flops here, and you have 4 possible for each of them, and you forget the 0 sequence. And all of them can be shown to appear 2 to the M minus 1. So if you take 1 from each cyclic shift, you get the size here, which is 4 to the M minus 1 divided by 2 to the M minus 1, which is this. And you can compute the theta max. So this is also very good, because you have much more than you have in the Kasami, which are the square root of n, and the same for the correlation. But now, in a sense, you are doing modulo 4, but Kasami was binary. So you can do a trick with these sequences that was discovered at that time. So you just took the same generator polynomial for an M sequence, and you did this d minus x minus, and then you just got this sequence modulo 4, and you could make all of these sequences, write them, all the terms in the sequence you can write in a binary form. So if S is a sequence modulo 4, A and B are binary sequences. So these sequences you get from here, it gives a family which is much better. It's binary. It has similar correlation to the Kasami, but the Kasami had like the square root of n. So this is a much larger. So even if the Kasami is optimal, it's optimal in a special sense. So this is more optimal in a way, and a better family. So in a way, if you compare this is the situation you normally had. So one of the first things we did was to find this family that we call it this standard family that was later adopted by the standards, and we call it S2, and this had good correlation sequence. I note that this had n cube. It had much more sequences than you will normally find if you use the golden Kasami, which normally is linear. Here, and still the correlation is. So it's much larger. Of course, you have to pay a small price since the maximum value increases a little bit. So actually, so I mentioned a couple of things that Vijay and I worked with in these sequences. So one of the things was this family of sequences, and this was this paper we did here constructed a low correlation family of sequences that we could use from CDMA. And this was adopted in this 3D standard in 2001. But the paper that we published was actually published in 1996 with me and Kumar and the previous speaker, Kola Bank, and also Hammond's student was heavily involved in this one. And as mathematician, I didn't think more about this. I thought it was a beautiful paper, because this was a large family, had nice correlation, and Vijay was also happy about this, and all the authors were happy about this one. But a few years later, we were in a conference in the Krieger Park, and then one of the big people from the Motorola gave an invited talk, And he talked about the new family of sequences they selected to use in advanced applications instead of gold. They used the gold sequence, but for some advanced application, they used this family as too. And this was selected as the standard. And I remember Vijay and I, we were sitting next to each other and listened to the talks, and we saw he made a drawing of the sequences. And we said, this looks familiar. And when he called it sequences S2, we were quite sure that this was actually the sequences that we published in this 1996 paper. So we were very proud of this one, because what I heard is that if you work in a company, you have to fight for your company to get the standard, so it's easier for you to develop products further. But we did not do anything. We just wrote the paper, and then 3 years later we saw that this would be selected. So I don't know who selected this, but it was a very nice choice, because we knew this was probably the best, close to the best that it's possible to do for these type of things. And actually this is so this is more the setting. This is the sequence you use. You actually use the sequence here that you usually call family A, which is the lifted. It's like a lifted family of sequences. And then you have these two shift register. This is essentially the gold sequences. This is the gold sequences with 0 and 2s, and this is also with 0 and 2s. But this has 0, 1, 2, and 3. So these are the sequence, and it's very easy to select the position so that you can construct the cyclically distinct families in cyclically distinct sequences in the family. So this we like to do this work. Yeah, this is maybe a better figure. Another thing that Vijay and I spent a lot of time on was a chapter on sequences. Because when I was having sabbatical at USC, I came in there in autumn of '92, and I was invited to Vera Place to give a lecture, and I gave it a talk there, and she asked me to write a chapter on sequences, because she had a project of writing a handbook in coding theory that contained chapters. So I talked with Vijay, and we decided and we were willing to write such a chapter. And we worked on this chapter. It took a long time. We worked on the chapter for 6 years before it was published. I had a family that I visited frequently in California at that time. And they always asked me what I was doing. I was writing on a chapter, but they never saw the chapter before after many, many years. And they really didn't believe that it exists, because many times I was writing with Vijay on the chapter, and even when I got back from the sabbatical, I had to go back to California to work on our chapter. But we were there. We've always found another interesting problem. So sometimes we worked the 2 weeks I planned to be there on the chapter. No, we did not work on the chapter, but we worked on a more interesting problem that we found. So when I got back again, I had to schedule a new trip the next month. So the reason why we were slow in the chapter was that these sequences of a C4 contain so many interesting problems that we liked even more to work on. But finally, we completed the chapter. And then we was asked to do another chapter, also more elementary one. And this one, I think we completed almost in a couple of weeks, which was much easier, because we had a more advanced chapter. This was almost 100 pages. So we really had this as a project, and this is one of our most cited paper for both of us. It's probably the top 5 of the paper for both of us. Another thing we worked on was that when we worked on finding sequences with large classes of codes, we came into a problem to find exponential sums and find new bounds for this in Galois rings. There was a famous bound that was called Carlius-Yama bound for Galois fields, but we wanted to construct sequences in Galois rings, and Caller Bank, he sent us a lot of slides and faxes at that time about some ideas he had for related codes there. And Vijay and I, we worked on this problem, and we all together we came up with a proof that had some very good bounds on these Galois rings. And this had the effect that even if the S2 family, if that had been too small, if people need more sequence in the future, this paper would always make us possible to construct a lot of practical sequences for CDMA in this direction further. So it was a very nice mathematical paper, but it was also quite useful, and it was really a pleasure for me to work with Vijay on this one, and with Colabanks, who's played an important role in this. Another thing, we worked on a lot of other things, many families of codes, decoding of codes, weight hierarchy for the C4 codes, designs in C4 codes. We also worked on ternary and binary sequences with autocorrelation, with good properties, and also with cross correlation. So we had a lot of problems to work on. I think we did more than 40 publications in journal and conferences, and also many books. And we also organized a lot of workshops together. So this was really a very nice time. We worked on this problem for many years, and we had a contact all the time. So now it's a non-scientific part also. If you work with people with many good ideas, it's nice to work with friends, because you trust them. You can share all your scientific ideas and be completely open. And so we had a long friendship here. Here is one of the memories I remember. Back in 1997, there was a conference in coding theory in Svalbard in Norway. This conference was held at 78 degrees north. And if you look at this picture, you see what this is. This is me. This is me. I was quite younger at that time. I think I was pretty close to. I was even 50. Oh, okay. I had a gun, a rifle, because this was 78 degrees north, and there were polar bear could be polar bear in this area. They were mostly in this area in the winter, but they could be here in the summer too, and then they were out of place. So for this reason, you had to rent or borrow in the hotel. You could borrow a gun and bring it with you when you went outside the local village. So that's why I had a gun protecting Vijay and the other students. I also had a student and two of my former students here. Yeah. So, but of course, the fact of having tourists with guns there was a standard joke that people said that the probability of being shot by a tourist at Svalbard is higher than the probability of being killed by a polar bear. The other thing about this conference, it had 50 people, and five of these, 10% of the speakers or the participants, were actually Shannon Award winners. So this is probably one of the conferences with the highest quality in this sense, that if you know about other conferences with more than 10% Shannon Award winners, you just tell me. But this was a very nice conference. This is Vijay on his way to taking the Norwegian Coastal Express down to from Tromsø, 70 degrees north to about 68 degrees north, where I celebrated my 70th birthday like 7 years ago. So this is Vijay. So it's a nice place to do research. And this is a group picture for my 70th birthday conference. And here you see here is my wife, here is myself, here is Vijay, and there is Sudha, Vijay's wife here. So we had a nice experience here. Here's the typical boring experience in Vijay and me in conference mode. This is when I'm not really sure where this conference. I think this could be maybe Golom 70 or 75 years conference. I'm not completely sure. Of course, when we go to conferences on exotic places like Svalbard, we sometimes bring our wives, and sometimes we have to go shopping. And one of the shops, the wives across, there's a bank here, it said man parking of husbands, essentially. So our wives were shopping across the street. So this is also typical events you have to do in the non-scientific part of a conference. Another thing, this is in 2019. Then Vijay's daughter, Anu, had a traditional Indian wedding, and I was there in Indian, dressed up in Indian way, my daughter, Ingvild, and my wife. So we spent 3 full days in an Indian wedding. We really enjoyed ourselves. And it was a fantastic experience. So, and another thing, of course, I've been visiting Vijay for many times, and he lived in California and also in India many times. His daughter Anu was 2 years the first time I think I visited him in 92. And when she got married, she always called me Tor Uncle. When she was a little girl, she always called me Tor Uncle. And in the Indian wedding, there is a tradition that the uncles, here are 3 of them, including myself in the middle, and the bride. And the tradition is that you have to carry the bride lift it up to the scene where the bridegroom is. So I was quite honored about this being an Indian uncle, and I was ready to do the expected task of me. So I really enjoyed that part also. Another thing, picture of Vijay is actually this one. This is me, and this is taken in my small boat. I sometimes go out for local fishing in my summer house, and Vijay has been many times in Norway visiting me, been in my summer house and in the boat, and when it's raining, you have this on head. This is for protecting against rain. This type of hat. So he looks pretty much like Darth Vader in this picture. So this is one of my favorite pictures of Vijay. So in conclusion, this was a little bit special talk, but Vijay is an extremely talented researcher. I've been working with him very closely for many years, and it's very impressive what he can do on the blackboard and do research just on the spot with a good idea. And he has a very nice personality, and I've written a lot of recommendation letters for him. It's always nice to write. It's so easy to write. I always conclude with that. Always have a good, nice conclusion, which is easy. And Vijay and my friend, and I'm really happy calling him my friend. And I and my family have enjoyed all this long-term collaboration for all these years. We are really happy. We had a lot of time for scientific work with a lot of good ideas or many rich memories together in the non-scientific environments. And as what I can say is, Vijay, congratulations with your 70th birthday, which was September 22. I know that exactly.
Thank you.
So,
Thanks for
thank you
this
very much.
wonderful talk, Tor. I don't think technical questions are correct for this. I think I would invite Vijay to say a few words, maybe. Okay.
Okay.
Hairstyle has changed considerably.
Yeah, little bit. Yeah.
So
Tor, thank you so much for such a warm
Okay.
talk with a lot of kind words. I think you're too kind, and I think you're far, far too modest. I think I learned a lot of things from you. I think not only in research, your style of research, but also what a great person you are, and what a great family you, Shasti, and the kids are. So very kind of you, and it's it's been my pleasure, and same with Sudha, who just walked in.
Huh?
Really enjoyed the collaboration. Thanks for the great
Huh?
talk.
Okay.
Look forward to catching up with you at our next.
Yeah.
Perhaps it'll be on Zoom.
Yeah, that would be very good. Yeah.
Thank you.
Okay. Thank you.
Thanks. Let's thank all the speakers in the session.
Thought I'll say a few words as well. I think Vijay has a fantastic taste for selecting good problems. In the years that I have been here, I've seen him pick 3 successes, amazing successes, and he started from scratch on each of those and took them to the highest levels. I think the first one of those is the diversity multiplexing game trade-off. Second one is codes for storage, and the third one is the DRDO project and the infrared sensing that he brought into the project. I think it's very easy to underestimate the importance of that infrared sensing contribution that Vijay made. I think we were all trying vibration sensors at that time and we weren't getting anywhere. I think it was Vijay that thought of this and then started all the way from how it ought to be modified and then the signal all the way up to the signal processing and the deployment and the taking it to the field. So that's actually an amazing work that Vijay has done. I think what Vijay brings is an uncanny knack to bring very delightful outcomes where I think deep and elegant mathematics influences or finds utterance in hard practice. I think he has had 2 successes in getting things standardized. They are already highlighted here. The first one of them, S2 codes, is something that I came across when I first started working. I was working on WCDMA 1999. These had just come in. And I think Vijay's inroads into that without any effort, no political wrangling or anything of that sort, just based on the merit of the work, it made it to the standard. I think that's just amazing. And the second one is, of course, the work that got into the NAVIC standard. One hit is amazing. I think 2 hits is just wonderful. And Lalita said that she tells this to all her students, the kind of success that we should be seeing. I actually tell this to everyone that comes us and asks, what has IISc done? I cite Vijay's examples as 2 big examples that have come out of IISc. I think as the other thing that I would like to speak about is amazing stamina and attention to detail. So SPCOM 2010 was the first time when I saw the kind of things that he was doing, which if I were organizing, perhaps I wouldn't be doing, but every attention to every detail. Then of course, he made EC department run like a well-oiled machine, again as chairman. And the one that SP building rewiring, I think he knows the layout of the wires far more than the person that actually laid the wires. And the last one is perhaps the way he steered the curriculum changes for ME, the program that we had. I think to get everybody on board and to agree on the changes was not an easy thing. And you mentioned that you have never seen Vijay flustered. There was one occasion then when he was a bit flustered, but I think he pulled it through, and it was a big success for us to change the curriculum. And of course, the stamina was not just in the academic arena or administrative arena. It also ran to the field. So Vijay and I ran the 2009 half marathon together. This was at Srirangapatnam. I think Vijay beat me hollow. He was 54 years then. I was 36. I think he finished a full 20 minutes before me, and I was exhausted. Vijay came and asked, can I help you in some way? Yeah, so I think just as someone said, my one regret is that I've not worked on a paper with Vijay, but as Bruce also pointed out, I think that's one of the things that we probably do in the coming years. He still has another 5 years thanks to the National Science Chair of the ANRF. We have had several opportunities though, but the one thing that I cherish is that one course that Vijay and I taught together. It was an information theory and coding course. We did it only once, but I think it was a wonderful experience to work with him. By the way, I also liked the way in which Vijay handled the beginning of his class. In my first year here, I actually attended many lectures. I was almost a student, as many of the students here would testify. And I sat in Vijay's course in the first semester here. And he would go and write down several things in the first 5 minutes. There was an eerie silence in the class. And then he would dramatically turn around and say, good morning, and start with the lecture, or good afternoon. So I could, the recapitulation of all the things is something that I still do, but the turning around and saying good morning in a dramatic way is something I've not been able to do. And then lastly, thanks a bunch to Vijay as well as to Sudha for the many evenings together at their home, but also for hosting us on that eventful day when water entered Vijnanpura. We had a 1-year-old at that time. They gave us, they opened their home to us, and also they still had the apartment. They opened their apartment in Vijnanpura to us for us to dry all the things that had gotten wet in the flood that entered our home. So thank you very much, and Vijay, happy to have you here for another 5 years. All the best, and I think this is a new beginning.
Yeah, thank you so much, Rajesh. I will keep it brief because I guess I don't want to drag the program on. I think Rajesh is, I mean, Rajesh is an excellent researcher. I think everybody in the room knows that. And talking about being meticulous, he's been the dean for the EACS division, and I think he's done it like a, smoothly oiled machine on steroids. I think he's been really, and also he's been very thoughtful in terms of making sure that everybody is recognized. And he nominated me for the National Science Chair Award. I think if not for his nomination, I would have made it. And it's been a great to be a colleague, and I enjoyed teaching the class with you also. Thank you.
Good evening. So first of all, happy birthday and congratulations on your National Science Chair, well deserved. I told him in the email, a perfect and fitting birthday gift, and that is not only for him, for the science community or our own community in the department and the area. And I think many people have talked, at least touched upon many things that I would also like to touch, but anyway, some detail. I think the first thing that comes to my mind Vijay came in was he came to SP building, and I know how it looked like and how he changed that. And the main thing was when he set up the office, equal share of setting up the office was Sudha's. She used to come, she used to be part of setting up the lab, making things up, and I used to see her more often. Initial days of his setting up the lab. If I'm right, I think you played a key role in his establishing in the department also, not necessarily in the house. So that is a great thing. And he gave a big trigger, which is for SPCOM conference. I think Rajesh touched upon this. I know this in a little more detail in the sense that SPCOM, Hari knows that it has been running for a long time, and it went dormant for about 4 to 6 years. Yeah. No, no, it was regular, biennial, but then in between it took a beating or whatever, there was a slack, and 2 to 4 years or 6 years it was not run, and it was to be done, and everybody will keep asking. It used to be a great conference like SLMR, Allerton, and now ITA, it's a new invention, but SPCOM happened much before that. So everybody used to ask what happened to that, and that needed to be taken up, and he give a big impulse. A system has to be rebooted. It should be an impulse, not a small push. And he gave that as a big bang. 2010 SPCOM, which is the best so far, that I still remember after 2010, even till today. But that momentum that he gave at that 2010 still continues, and it's a big what do you call character for the department and the institute for this conference. So a great contribution in my opinion. And another thing is, as a chair, very calm, very quiet, very detailed. I think a lot of T's he talked about. I would say one word: meticulous. I think maybe Sudha may know also, very close at home also, very meticulous. And to the extent that I still remember, if he walks inside his meeting room with a bag, he will open, the first thing he will take out will be his pouch. And that will have pencil, pen, eraser, even today. Which even in my school days I did not have. So that is a contrast, and that's how he impressed. And SP building is too big a change. Having a good roof, a good floor, best, a good toilet. And last one, it's a small thing. When I was chair, he used to be my mentor because past chair. And he's again knack for choosing things with nice taste, right? I used to go for choices. In MP20, we were making that auditorium choice of various things. And towards the end, I was supposed to choose this table that is there, that vignette sheet on top of. There were about 20-30 choices, which I was not sure what I should pick. If he remembers, I went to him, which one I should choose. Then he looked at here and there and said, take this. And he looked to me a little off, too bright, too shiny and all those things. He said, take it, it'll be very nice. And that is what it is there in MP20 and MP30. And that is very kind of unique. Even the curtains, I used to ask him, which one will go with the overall dressing of this thing. So he's minute to the detail and very friendly, and he doesn't carry the weight around in any circumstance. I think it's very nice human being tendency that one can look for any person, and it's a great academic, scholarly achievements. I need not say much, but I think one which triggers me most because of my space connection or my interest in ISRO is his contribution in terms of code design, and ISRO person is here. He would vouch for his contribution, and I could locate him in GSLV launch in an early morning launch in the TV. I used to watch all the GSLV launches, most of the ISRO launches, be it in the midnight or the morning. One of the morning GSLV launch, I could see they were scanning the VIP gallery. Then I asked him next day, Vijay, I saw somebody like you, were you there? He said, it's very surprising. Then I said, yes, I saw you. And that is the level of contribution that he could do, both for academic as well as the country's good being. And with that, I would say it's a great opportunity for me to share this with all of you. And thanks, Vijay, for all, and good luck to you for all in the coming years. And Sudha, thank you so much. Right.
Yeah, thanks, Jokes. I think thanks very much for the very kind words. I was completely blown away that Chokes said, were you there at ISRO? I had no idea how. I mean, you must be following these proceedings very carefully to spot. I would have been up on the screen for maybe 2 seconds to spot me. So I was completely blown away. Chokes, of course, is a remarkable researcher, and he talks about being quiet and modest. He himself is an epitome of that. I think one of the things is that whenever I walk on my way to the office, he'll always be there in his office. Very consistent and remarkable achievements with MIMO and now with OTFS. So, and a great colleague. Very nice to interact with you. Thank you very much.
So Naveen, do you want to speak? Floor is open. So I have vague recollections of interactions with Vijay, mostly non-academic. Some of them were academic, as in I was in a students' committees and all that. I remember
some conversations around that, not too many, but I remember the non-academic conversations. That's the only thing I'm going to say. Maybe that's a little bit of an interesting thing. One thing I remember is, I think it was I can't recall when we were talking about drinking. I don't know why I'm remembering this. And I said something about how I don't drink too much when I'm in India. I can't get this, something. And then he didn't say anything back. He said some story about his childhood, or I can't recall, something about chupke chupke pite hoge. I don't know if that story has been repeated to many people. Do you know? I mean, I can't recall the details. It was a sly reply saying, "You're not really telling the truth." You know, he didn't quite tell that to me straightly. Something about how somebody said chupke chupke, and somebody thought chupke chupke was a drink, right? Not a. Am I right? Vaguely. Okay, you can tell the story. I thought that was a very nice way to get back to someone when I don't really believe you, but you know what? This is what it is. Some such thing he said. I think that's one thing I remember. Something else is about family. He was asking me about something, and I said, yeah, when I travel, I miss being home or something like that. And he said, oh, that's good. You're very lucky or something like that. I've had such conversations with him. Other conversations around choices you make as an academic. I think one thing that runs deep inside him, not too many people mentioned it explicitly, is very strongly committed to contributing to Indian causes. I think there is a deep commitment. I've had multiple conversations with him on that topic because my own career has also shifted a little bit into that direction. But he has very strong opinions on that. I've had multiple conversations with him. I remember one conversation where I think he was saying something about I think it was a something about what choices should faculty make. I mean, should we go more into a vague recollection again? Should we go more into technical research and rigorous stuff, or should we do directly something in the national cause or something like that? And I think my reply to him, which he really liked, I think at that time, I have a memory of that. My reply to him was, I think doing academics is very good, right? It's already a solid contribution. Not everybody needs to do everything. If you do your institutional work well, take care of your institution, something like that. I said, I can't recall. Like, he was very happy. He was like, oh wow, that's a great answer. Now I'm okay. I'll carry on. All that. I've had multiple conversations about NPTEL, PS degree program, various other things with him. One thing I think he's very proud of is his contribution to NEP 2020. Nobody mentioned it. Maybe I'll mention it. He was on the committee. I remember him saying many things about that role to me, what he did, how he read the document very closely, how many others maybe didn't read the document very closely. So that's sum total of my memory. Most of it is travel to ISIT. I think that's where we meet and have conversations over wine and beer or something like that. It's been wonderful, 20 plus years of knowing you, Vijay. I think so humble in spite of having so many achievements and talking to everybody so nicely. So many other memories are there, so I'll leave it there. Thanks a lot, Vijay.
Yeah, thank you, Andrew. And I think likewise, I've always enjoyed the conversations with Andrew, and they've been mostly ISIT, I think. And Andrew is committed to the nation as much as anybody else. I think fantastic work at NPTEL. Went and visited the office, very impressed by it. And then this data science thing that he spearheaded, simply amazing. So it's always been fun. About this chupke chupke, what is our time? We are seriously behind time. Are we seriously behind time? Then we should. Then I will save it for another. We'll save it for another.
Yeah, Asuda. I think, yeah, my own recollection of when I first met Vijay probably was some ISIT or something like that. But prior to even meeting you, I think I met some of your students, Vinay Devlalikar, in 1997 or 6. Yeah, I had come to USC because I had somebody in the math department there. Do you know Mahesh Nagarajan and Mahesh? Anyway, okay, yeah. So he used to be in the math department there, and but then I think they all used to share a house. I think when I was a roommate of his or something, when I visited them, Sorry? Your roommate, okay. So they were all like hanging out together. Yeah, so I'd, no, that was the first time that I think heard your name being mentioned anyway. Yeah, so it's been, quite, yeah, it's been really a great honor and pleasure to have had Vijay as a colleague over the years. Yeah, I mean, his attention to detail, many people have already commented on. Yeah, I mean, besides all that, picking out whatever, like, I mean, getting the SP building, many people have already said, but he also went like to the extent of picking out the tiles for the bathrooms, right? Like, so it is to that, it's not only we are talking about paint and things like that, or like flooring, but that level to which he goes to the shops, like he went to multiple place shops in, these hardware stores to pick out the Jigni, yeah, exactly. That's right. Jigni, man. Okay. That also. Of course. Yeah, yeah. I mean, there was a discussions about what type of flooring to be put on the staircase because like it shouldn't be slipping. All, attention to detail. Yeah, I mean, there's nothing that you can. I don't think you can beat Vijay in terms of that, and it's absolutely incredible. And yeah, I think Rajesh wanted to point out that the MP building would not have really come up without his intervention. Like he managed to wrangle the funds out of Balki. A task in itself. I mean, it's an achievement in itself. Incredible that, like, I mean, over and over again as a chairman going to beg for money for a building and, managing to get all of that and like getting it, he handed it over to you, I guess, when you took over. But without without him, it wouldn't even have been there, I guess, in the first place. We would have still had that old dilapidated, rundown building that nobody used. Yeah, so I mean, these are things that I mean, I have several memories of Vijay, like talking to Vijay at conferences. We even shared a room in Ascona, and Hawaii. Yeah, that's right. Yeah, that's right. Yeah, okay. Yeah, I think it's yeah. We have not. Many others have expressed this regret or that have not had an active collaboration with him, and I guess I should regret this the most in the sense that I should have, being the closest in this department into his research interest, should have had that. We've had, I guess, the closest we've come is like a couple of years back when Professor Manjunath in the math department gave me a problem to think about, and I mentioned it to Vijay over the course of some beers with the department meeting, and man, he got excited. Like it was a sequence problem, correlations, excitement. Like over the course of the evening, he just worked out something like furiously scribbling. I mean, over beer after beer going down, and then the next day or the day after, like he gave me the solution, and then yeah, it more or less was correct, and it was it was fantastic experience. Closest collaboration that I've had so far. It never got written up, but Manjunath was very happy with that answer. But yeah, it has been really fun to have been around him and learned a lot from him. And his style of supervision of his students is really, I mean, it's a great success to see all his students be here for him. And that says, I think, a lot about his style of supervision as a student. I mean, about his style of as a supervisor. The entire Korean mafia was here for the 60th birthday. I remember this very well. Yeah, so one thing that they did in the 60th birthday, which I guess was not done now this time, is that like the testimonials from all his professors at USC. Yeah, of course, they were much more connected. Yeah. But anyway, yeah, thank you for, I think, all of you to have organized this wonderful event. And again, once again, congratulations, Vijay and Sudha. Hope, I don't know, you've got 5 more years of him being at work now. I don't know what you're going to do. So, anyway, thanks a lot. Yeah.
Yeah, thank you, Naveen, for the kind words. I think we still have time. We're with this bi-weekly seminar on quantum. So I think there's plenty of time to collaborate. I've always enjoyed Naveen, and I like his very straightforward way of speaking his mind in whatever the situation is, and enjoy the research interaction. What was I going to say? Yeah, somebody mentioned Sudha. Yeah, so she's been my go-to consultant. That is true. And what you guys called meticulousness, she calls chadastam. Mari ekku chadastam ani cheptunnaru. So that is, I thought I should actually mention that. Okay, but anyway, yeah. So thank you, Naveen. Thank you.
So we have last 5 minutes. Anybody wants to share, please?
Oh, happy birthday, Vijay, and congratulations again. I'll just tell you two quick stories, right? And interacting with Vijay over the years. The first one is, of course, everybody mentioned the signal processing building. So when it was being refurbished, repaired. So one evening, so Vijay, I was an assistant professor then, and Vijay had put me on this building committee. So one evening, he said, Gaurav, let's go and make an inspection of this building, right, which is supposedly coming down. So, we walked inside, and I remember there was a false ceiling all around the building. And so we had a walk around, and then Vijay was in two minds. I said, Vijay, the false ceiling needs to go. And he's like, no, we have to take care of the debris and all that. It's going to be a nightmare. And everybody knew the signal processing building was a mess, right? This was our department's talk. So suddenly we came to a point where there were two false ceiling boards that were separated by a little gap. And Vijay was just standing there looking at it. And suddenly I remember pigeon came out and flew out. And then I think the next day you called me or on the spot, but you said, Gaurav, the false ceiling is going, right? So that was one thing that I remember, pigeon initiated transformation. And the second thing I'll tell you, because I'm a semiconductor chip guy, I haven't had the good fortune of talking to Vijay about many technical things. But once I had a question, because I'm very lucky that in the department I can go to many colleagues and ask questions. So I was working on a radar. We have a radar that we've built, and we wanted to do some phase coding on it. And this is something that I'm not very comfortable with. So I asked Naveen, of course, because we have adjacent offices, and I always bug him as the first person. So then Naveen said, why don't you talk to Vijay, because he's been looking at coding, in this context. So I went and I had a wonderful 1 hour in his office one day. He kindly made the time, and he explained many things to me about the work he had done with ISRO and how that could translate to radars. And I came back with a very good understanding. So thank you, Vijay. And I wish you and Sudha all the very best ahead. Thank you.
Thank you, Gaurav. It's been fun interacting with you. I do remember that I used every resource that I had with regard to the new building, and I would often pull, Gaurav and others and Rajesh into committees, whether they liked it or not, with anything to do with the two buildings. Thank you. And also, we share a common heritage of IIT Kharagpur. Thank you for the kind words. Before I forget, I just want to thank all the speakers who came today. Sudhir Ghorpade. He was supposed to he would have been in Norway at this time, but he actually put that aside and came here. Thank you so much. Thank you so much. Very kind of you. And then Adresh Banerjee all the way from IIT Kanpur. Thank you so much for coming. Please raise your hand if you are here. Andrew Thangraj coming from IIT Madras. Delighted to see you. Yeah, Prasad Krishnan, thank you. And Prasad, thank you. Enjoyed all your talks. Arvind, yes, Arvind now from Chennai. So yes, he's a traveler. Yeah. Nikhil, yes. Where is Nikhil? Oh yeah, thank you. Sitting quietly in the back. Thank you so much for coming. Huh? Prasanna? Yeah, okay. Yeah, thank you. And so glad that Bruce Hyde could be here for this event. Thank you so much. That was an unexpected delight. Some other PhD students that I forgot, Balaji coming from Chennai, thank you so much for coming. And Ravi Teja, okay. And another person who's helped a lot with energy is sitting quietly in the back. Thank you, Pallavi. Yeah. Okay, I think if I forgot anyone, please accept my apologies in advance. But I do thank you very much for being a part of this event.
So we are running out of time, but we have two surprise video messages, so we don't want to miss that. Volume is not volume. Start again. Volume is oh. Is it the maximum? Mobile also better, right? We have WhatsApp, right? You can play from the WhatsApp. That's it.
Maybe already 70. Feels like just yesterday we were using learning discrete maths and doing JE Prep. Can't believe you're already 70. It feels like just yesterday we were in your study learning discrete maths and doing JE Prep. I think your colleagues and students would know more of the technical details of what all you've worked on, but I just like to say how proud I am every time ISRO does something and I say, I think my father worked on that. Yeah, what a career, and happy birthday. Have a great one.
Hannah, we're so excited to celebrate you and this incredible milestone. My dad doesn't do anything in half measures. In fact, I think if you search for the phrase going above and beyond on Google, you'll just get a picture of my dad. When I was little, I started playing football, and my dad was excited. But he didn't just come to my games and cheer me on from the sidelines like a normal dad. He went to referee school to become a referee just so that he could actually be a part of my games. When I started struggling with math, my dad took over from my teachers and would coach me every day after a long day of work. But math came easily to him, so no big deal. But then came physics, and he said, no problem, I can help with that too. Finally, one day, I told him I was having a tough time with organic chemistry. And I'm not gonna lie, he hesitated a little bit that time, but he still agreed to help. And if you're sensing a pattern here, yes, there's a good reason why I ended up in marketing. And of course, my dad didn't just help. He bought his own copies of all of my textbooks. He would study ahead of me to make sure that he was prepared to teach me everything I needed to know, and he would stay up late before every exam with me. He took on all of my stress, so I never had to feel it alone. And that's just who my dad is. He's always prepared, always all in, and always there for the people he cares about. And I know many of his students and colleagues in the room know that feeling really well.
Hi, Maya. We wish we could have been there with you in person to celebrate this occasion. One thing that's always been obvious is your curiosity and your passion for learning and sharing new things. Even when it's just talking about my work, it's never just the superficial, hey, Vinay, how's it going at work? You truly want to understand whether it's talking about your running shoes or your work with ISRO or how best to entertain Asha. You truly want to understand how things work and learn new things. This has been most evident in the last 2 years in how you play and engage with Asha, whether it's in person or over a video call. I can confidently say that you're one of her favorite grandparents. Well, at least you're definitely in the top 4. Speaking of the young lady, she has a special message for you as well.
Happy birthday to you. Happy birthday to you. Happy birthday, dear. Happy birthday. Happy birthday to you. Yeah. Thank you for some animals.
So we'll wind up the session with a song from Nikhil. Yeah. So he used to conduct kacheris in the lab. So and the song yeah, the last one.
देखो मुझे सब है पता सुनता है तू मन की सदा देख मुझे सब है पता सुनता है तू मन की सदा मितवा मेरे यार तुझको बार बार आवाज मैं न दूंगा आवाज मैं न दूंगा चाहूंगा मैं तुझे सांझ सवेरे जुल्फे है जैसे कांधे पे बादल झुके हुए आंखें है जैसे मेरे प्याले भरे हुए मस्ती है जिसमें प्यार की तुम वो शराब हो चौदहवीं का चांद हो या आफताब हो जो भी हो तुम खुदा की कसम लाजवाब हो चौदहवीं का चांद हो बाबू समझो इशारे हॉर्न पुकारे बम 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 यहाँ चलती को गाड़ी कहते हैं प्यारी पम 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 री बापा 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 री बापा. Thank you.